In this video, I'd like to briefly talk about the C++ standard exception class hierarchy. C++ provides a class hierarchy of exception classes. These exception classes are used throughout the C++ standard libraries. The stdException class is the base class, and all other exception classes are ultimately derived from it. stdException provides a virtual function named what that returns a C-style string with a description of the exception that occurred. We can create subclasses of the exception classes and then implement the what virtual function so that it displays whatever exception message we want. Let's take a look at the exception class hierarchy. Here's the C++ standard library exception class hierarchy. The classes that are in orange are the C++ 17 additions to the class hierarchy. Notice that the common base class in the center is stdException, and then we have many classes derived from it. Exceptions that are runtime errors, logic errors, bad allocation errors, out-of-range errors, and many more. We aren't going to study these classes in detail, but we can create our own user-defined classes that are derived from these exception classes. This can be very useful in some situations, since by being derived publicly from stdException, our classes are now part of this hierarchy and can be used wherever a stdException is expected, since your class is an exception. Also, thanks to dynamic polymorphism, all you have to do is implement the what virtual function and it will be bound dynamically at runtime. Let's see an example of how we could create an illegal balance exception for our account class, but this time let's derive it from stdException. Here's a simple example that shows how we could create our user-defined exception class named illegal balance exception, and this might be thrown if the account is created with a negative balance. Notice that we derive the class publicly from stdException, and we simply provide a default constructor and a default destructor. Finally, we implement the what virtual function and return a C-style string describing the exception. This is a really simple implementation. We could provide all sorts of error information, codes, descriptions, and so forth as class attributes and initialize them in the constructor when we create and throw the object. There's a keyword here that I haven't talked about yet. That is the noExcept keyword. This tells the compiler that the method will not throw an exception. So don't throw exceptions from these methods. The destructor is noExcept by default. If you do happen to throw an exception from a no-throw method, the program will terminate. The exception will not be handled. Let's see how we might use the account class hierarchy that we've used throughout the course. Here's the code for our account constructor. We're checking to see if the account balance is less than 0, and if it is, we're throwing an illegal balance exception, which is our user-defined exception class derived from stdException. This code should look pretty familiar, since it's more or less the same code that we wrote when we created our own standalone illegal balance exception class. Now we can try to create an account object. In this case, we'll create a unique pointer and create a checking account object dynamically. Notice that we're creating Mo's account with a negative 100 balance. This is not legal, so we expect that the account constructor will throw an illegal balance exception object. And that's exactly what we're catching in our catch handler. In this case, the catch handler fires and we call ex.what, which will display illegal balance exception. That's pretty powerful and not too difficult to understand or use. Well, that's it for exception handling. The challenge exercise for this section is next, and although it involves some more advanced exception handling techniques than you'll find in most courses, I think you'll be able to do it just fine. Let's get to it. Hello, welcome to the Section 18 challenge on exception handling. Congratulations on finishing this section. This challenge is a very straightforward challenge, but it's going to be using some interesting techniques. One of the things that I want you to do in this challenge is to derive your own exception classes from the standard library's exception class, and then integrate that into the account class, and then test your code. Now, I've got you started here. I've created a challenge project, and again, I'm in the Section 18 workspace in the challenge project. And under here, I've got all the source code for the account class that we've been working with throughout the course. This is the description.txt file, which is the one we're looking at right now. And I'd like to read through this in a minute, and then I'll talk about different exception classes. Okay, so for this challenge, what we want you to do is to integrate your own user-defined exception classes into the account class. The account classes are provided for you. You can see them over here. Also, the illegal balance exception class already has been created for you, but it does not derive from the studException class. You have to do that yourself. What I'd like you to do is derive the illegal balance exception class, like I just said, from studException and implement the what method. Okay, that what method is that virtual method that returns a character string, a C-style string, and provide an exception message there. Now, this exception object should be thrown from the account class constructor whenever we get a negative balance. Okay, so in other words, if you try to create an account with a negative balance, we want to throw this, very much like what I did in the slides. So that's one class. The second class is a class called insufficient funds exception, and you can see that right here. Again, I want you to derive this from studException and implement the what method for it to provide a message. This exception object should be thrown if a withdrawal results in a negative balance, so you're overdrawn. Okay. You should throw this exception object from the account's withdraw method. That's it. Pretty straightforward. The harder part of this assignment is not so much implementing these classes, it's testing them. And you'll have to do that in your main. All right, so let me go over this illegal balance exception class right here. There's no CPP file, it's all in the header file. And I've created a class called illegal balance exception. It's got a default constructor and a default destructor. And I've got those curlies here. You could replace those with equal default if you like. I think I do that in the solution, but you don't have to. So that's it. Now, what I want you to do is public inheritance here, studException, and then implement the what method. You'll notice that that's already there. And if you go to account CPP, in the account constructor here on line 3, I'm checking to see if the balance is less than 0. If it is, I'm throwing illegal balance exception. Okay, so that's part one. The second part is I want you to create, let me go back to my description real quick. I want you to create another class called insufficient funds exception. Same idea as illegal balance exception. It's going to be derived publicly from studException. You're going to have your constructor, your destructor, and you're going to implement that what virtual function again. And then that exception will be thrown here in the account CPP withdraw method right here. So you can see that if the balance goes negative, you want to throw that exception object. Okay. Now, where do you catch these things? Well, let's go to our main. This is where you want to test your code. This is where you want to create your checking account objects, your savings account objects, and so forth. Create them with negative balances. Put $100 in it and then withdraw $200 from it. So you get an insufficient funds exception. So that's the kind of thing you want to do here. You want to be sure you do that in a try block, and you want to be sure that you're catching those exception objects here. Okay, so that's really it. It's not a lot of code to write. It's just writing them in precise locations and getting it to work just right. All right, so good luck. I'll see you on the next video where I'll show you my solution. Okay, welcome back. This is my solution to the Section 18 Exception Handling Challenge. I'm in the Section 18 workspace in the Challenge Solution project. And again, this is my solution. There's different ways to do this. If you did it a different way, that doesn't mean it's wrong. It's just different. Post it and we'll get some comments from everyone. So in this case, let's take a look at what I did. I've created the illegal balance exception that we had earlier, but I changed it a little bit because what we want now is we want the class illegal balance exception to be derived publicly from studException. Okay, so that takes care of that part. So now remember, an illegal balance exception now is a studException. I've got my public modifier here. Here's my constructor. I'm just using a default constructor and I'm guaranteeing no exceptions being thrown from it. I've got a destructor here, again, a default destructor. And here's my virtual what function. And here's the prototype for it. It's virtual. It returns a pointer to a character, which is a C-style string, and it's const. The function itself is const and won't modify anything. And again, I'm guaranteeing no exceptions being thrown from here. And all I'm returning here is any kind of C-style string, in this case, illegal balance exception. And this is what we're going to print out on the other side when we catch this exception and print out the message. So that takes care of illegal balance exception. Now let's take a look at insufficient funds exception, which is right here. And neither one of these needs a CPP file because we're doing everything right in here. So here's the insufficient funds exception, pretty much the same pattern. My class is insufficient funds exception. It's derived publicly from std exception, and I've got insufficient funds exception, again, no except default constructor, default destructor, and there's my what virtual function, which simply returns insufficient funds exception. That's it. Now, if I go to my account CPP file, you can see here in my account constructor, if I'm trying to create an account object with a balance that's negative, I'm throwing illegal balance exception. And down here, my withdraw method, if the balance goes below 0, I'm throwing an insufficient funds exception. Okay, that's it. Pretty straightforward. Now, let's take a look at the main where we can test some of this. So here's the main, and what I'm doing here is I'm creating two unique pointers, one to Mo's account, one to Larry's account. And then the first thing I want to do is I want to try to create Larry's account with a negative balance. Right now, I expect this to throw an exception, and I want to catch it right here. I want to catch the illegal balance exception and just simply print out x.what, right? That's going to call my virtual function, and hopefully it'll say that I've got a negative balance or an illegal balance. So that's one test case here. In this test case, I'm going to try to create Mo's account as, they're both savings accounts, by the way. I'm creating Mo's account as a savings account with a $1,000 balance. And then I'm displaying it. I expect that to work. Then I'm withdrawing $500 and displaying it again. I expect that to work. Now I'm withdrawing $1,000. I don't expect that to work. I expect that to throw an exception because that would create an account now with negative 500. I'd be overdrawn. So I don't expect this to display. Okay. And this Larry's account here, we really don't need. Sorry about that. That was a carryover from before. Okay, so that's better. So in this case, we're going to catch both these exceptions, an illegal balance exception and an insufficient funds exception. If either one of them throws, then I catch them and just display their what. Okay, so let's run this. And here's my output. First one is I've got an illegal balance exception. That's what I expected because I tried to create Larry's account here with negative balance, right? Then down here, remember at this point, I don't display Larry's account because Larry's account hasn't been created. So what I do is I just skip down to here, and now I'm in this piece of code here. So the first thing I want to do is I want to try to create Mo's account with $1,000 and display it. And you can see right here, Mo's account with $1,000. There's no interest rate because I didn't supply one. Then I'm going to withdraw $500 from Mo's account and display it again. So now you can see Mo's account now has $500 balance right here. Now I'm going to try to withdraw $1,000. That should not work. So I shouldn't see Mo's account displayed again. Instead, I should get an insufficient funds exception being thrown. And that's exactly what happens here. This catch block fires the second catch block, and ex.what is displaying insufficient funds exception. That's it. Most likely your code is very similar to mine. Your test cases may be different, but that's okay. You can test this by using nested try statements as well. You can have one try inside another. You can try to create the object, and then once you've created the object, you can create try statements within that try statements that are exercising some of the withdraw methods. So that's it. I hope you had fun in this section and in this challenge. In this section of the course, we'll look at how C++ uses streams for I/O. First, we'll learn what streams are and how they help abstract the complexity away from working with different types of input and output devices. Then we'll learn about some of C++'s stream manipulators. These are functions that can affect how we read and write data to and from streams. Then we'll learn about some of C++'s stream manipulators. These are functions that can affect how we read and write data to and from streams. We'll learn about stream manipulators that affect Boolean, integer, and floating point values. And then we'll use some manipulators that work with any type of data to help us format our output. These manipulators give us the ability to align text, fill blank areas with specific characters, and set the width of output fields. Then we'll do a challenge where we'll use the manipulators to format a report containing information about tours to South America. After the stream manipulators, we'll learn about input files, how to open them, check to see if they were opened successfully, read from them, and then close them. We'll read from them using both formatted and unformatted I/O. And we'll do 2 challenges using input files. The first is to create an automated grader that will grade student quiz responses from a text file and produce a report of the results. For the second challenge, we'll ask the user for a word and see how many times that word appears in Shakespeare's play Romeo and Juliet, which is stored on a file and disk. Then we'll learn about output files and how they work. We'll learn to open them, write to them in both formatted and unformatted modes, and close them. And then we'll do another challenge that creates a copy of Romeo and Juliet but adds line numbers to the play. Then we'll wrap up this section by looking at string streams. This allows us to use in-memory strings as streams and use the same I/O techniques that we use with files with in-memory strings. It's very powerful. And we'll also see how we can use string streams for data validation. As you'll see in this section, IDEs differ in where they store files for use within the IDE. In the last video of this section, I'll show you how to set up external text files for reading in Visual Studio, Code Blocks, CLion, and Xcode. Okay, we've got a lot to get to. Let's get going. In this video, we'll learn about how C++ uses streams and files for I/O. Writing an I/O library for any programming language is an extremely difficult task. There can be all sorts of devices providing data to your program, and your program can send data to many types of devices as well. These devices may be physical devices such as hard disks, the console, and the keyboard, or they can be virtual devices such as some connection to a web server. C++ provides a stream abstraction to work with I/O devices. A stream is an interface that's independent of the actual device. So from the programmer's perspective, we can code to the stream interface and not worry too much about what device is connected to the stream. A stream is exactly as you would expect. It's a sequence of bytes. C++ provides different types of streams, depending on whether we want input or output, but we can also use a stream that does both. Let's see what this looks like visually. In this slide, you can see that the C++ program is on the right side. The upper stream is an input stream that provides input to the program from some input device. This device can be the keyboard, a file, a connection to a web service, and more. The lower stream is an output stream that takes output from the program and sends it to the output device. Again, the output device can be a file, the console, a connection to a web service, and more. So let's see some of the C++ header files that we typically include to allow us to work with I/O streams. In this slide, we can see 3 of the most commonly included header files that allow us to work with stream I/O. There are others, but these 3 are the most commonly used. First, we've already seen and used I/O stream. I/O stream provides the definitions required for formatted input and output to and from streams. The fstream_include file provides definitions for formatted I/O to and from file streams. And the IO_manip header file provides definitions for manipulators that allow us to format I/O streams in specific ways. We'll use the IO_manip functionality first in this section. When we include these header files, we'll have access to many C++ classes that we can use for file I/O. So let's see a few of them. The iOS class provides basic support for formatted and unformatted I/O. It serves as a base class for most other classes in the I/O stream hierarchy. The ifstream class provides high-level input operations from files. So if you want to read from a file, you can declare your object to be an ifstream object. The ofstream class provides high-level output operations from files. And again, if you want to create a new file or write to a file, you can declare it as an object of ofstream. The fstream class provides high-level I/O on file-based streams. Fstream is derived from ifstream and ofstream using multiple inheritance. If we need to do both input and output to a file at the same time, we can declare an fstream object to do it. Finally, we have the string stream class. This is a very useful class that provides high-level I/O on memory-based strings. Just like we can use insertion and extraction with cin and cout, we can use them with strings to get input and provide output into a string in memory. That's pretty powerful stuff, and we'll see some examples later on. Finally, let's visit our old friends cin and cout and see exactly what they are. The fact that we've used them all along without worrying about how to create them, how to connect them, and so forth is a testament to the design of the C++ I/O library and the device independence model. cin, cout, carr, and clog are global objects. They're initialized before main begins to execute, and all you need to do is include IO stream to use them. cin is the standard input stream and is by default connected to the keyboard. It's an instance of the iStream class. cout is the standard output stream, and by default it's connected to the console. It's an instance of the ostream class. This class should sound familiar since we used it when we overloaded the insertion operator in the overloading operators section of the course. cin and cout are generally buffered streams. This means that input from cin won't be automatic until the user presses enter, and output to cout occurs only when the stream buffer fills up, or we provide a std line, or we flush the stream. Now, carr and clog are the standard error stream and the standard log stream respectively. By default, they're both connected to the console. They're both unbuffered, which means that we get input or output from them as we need it. Best practice is to use carr for error messages and clog for log messages. Those of you who are familiar with the Unix terminal shell or the Windows command prompt know that we can redirect these streams easily, so input comes from a file or output goes to a file. I won't be covering this in this course, but if you're interested, do an internet search for redirecting I/O and you'll see how easy and powerful it can be. Okay, so that concludes this video. In the next video, we'll see how we can use the I/O manipulators to help us format our I/O. In this video, we'll learn about some of the C++ stream manipulators. C++ streams have many useful member methods that can be used to control formatting. There are methods that work on input and output streams, but formatting output is much more common. An important concept to understand is that when we manipulate a stream for formatting, sometimes the settings we make will be set for the remainder of the program, other times they'll only affect the next object placed on the stream, and sometimes their effect is immediate. When we go over the individual formatting methods and manipulators, I'll show you the effect each one has, as well as how long the effect lasts. Most of the stream formatters come in two versions, a method version and a manipulator version. The method version is simply a method call that you use with a stream object. For example, cout.width10. I'll explain what this does in a later section, but for now you can see the syntax. It's calling the width method on the cout object. There's also a manipulator version, which is designed to be used inline as a stream insertion. In this case, setw10. As you probably guessed, the manipulator versions are simply overloading the insertion operator to make this easy to use. To use the manipulators, you must include iomanip. The code we'll write will focus mainly on manipulator usage, but I'll also show you how to use the methods. In the next few videos, we'll go over some of the most commonly used stream manipulators. Here's a preview. We'll first start by looking at formatting Boolean types. We've already seen this used in the course in a few places. We can use bool alpha and no bool alpha to display Boolean values as either the strings true or false, or the integers 1 and 0. Then we'll look at formatting integer types. These manipulators allow us to display integers base 10, base 16, or base 8, as well as to decide whether we want the base prefix to show, and in uppercase or lowercase. We can also decide if we want positive numbers to show the plus symbol in front of the number. Then we'll switch over to floating point numbers. Again, we've already seen some of these manipulators used in the course. We can use fixed point, we can set the precision, we can show the number in scientific notation format, and again, we can decide whether we want trailing zeros printed and whether we want the plus symbol displayed. Then we'll learn how to output numbers and strings in fields of fixed width, and we can see how we can left or right justify them within that field. We'll also be able to fill empty space within the field to a specific character. Finally, there are several other formatters that can be very useful. Endline we've already seen and used. Flush can be useful when we want to be sure that we flush out any stream buffers, but it doesn't add a new line like endline does. The last few we really won't talk about much, but I'm including them here for your reference. Skip whitespace, no skip whitespace, and whitespace are typically used with input streams when you have very specific use cases about dealing with white space. Okay, so in the next video, we'll start with the Boolean formatters. I'll see you there. In this video, we'll see how to format Boolean types to output streams. Note that we're using cout in these examples, but any output stream will work, including file output streams, which we'll learn about later in this section. By default, a Boolean value is displayed as a 1 if the value is true, or as a 0 if the value is false. But sometimes we'd like to display the strings true or false, and we really don't want to write if-else logic all over our code every time we need to do that. Instead, we can tell our output stream to display Boolean values as 0, 1, or as true, false, whichever we want. First, let's see an example of the default behavior for Boolean values. First, we display the value of the expression 10 equals 10. Since this is true, a 1 will be displayed. Then we display the value of the expression 10 equals 20, which is false, and as you see, a 0 is displayed. Now let's use a stream manipulator to switch this to true-false mode. In the first statement, we're setting the output stream cout to bool alpha mode. This means that all further output to cout will display true or false as strings. And you can see the output from the same program now displays true and false. It's important to understand that with Boolean formatting, once we set it with bool alpha or no bool alpha, then all further Boolean values will be displayed that way. We can toggle back and forth as appropriate as shown in this slide. We can also set the format for Boolean types using the setf method. In this case, we have a bunch of flags that can be used to set and reset formatting directives. In this example, we can pass std ios bool alpha or std ios no bool alpha to the cout object to change its formatting. Finally, we also have a method named reset ios flags that expects the flag to reset. In this case, we can pass in std ios bool alpha, and it will reset the stream to whatever the default is for that flag. In this case, it will go back to displaying Booleans as 0s and 1s. Although you sometimes see this type of code in production, it's more common to see the manipulator version, and that's what I'll focus on in this section. So let's head over to the IDE, and we'll do a couple of examples using bool alpha and no bool alpha. Okay, so I'm in the IDE, I'm in the section 19 workspace in the manip_boolean project. And in this project, I've got a bunch of simple test cases here that just display certain values to standard out or cout. In this case, those values are Boolean values, and we're going to manipulate them using the no bool alpha and bool alpha manipulators. So here's the default. What we're doing here, we're going to use this same test case throughout. You can see what we've got here. We've got, is 10 equal to 10? That's either true or false. Obviously, this is true, so this will always display true. And 10 equals 20 will never be true, so that'll always display false. In this case, we're using an expression, but we could certainly use a variable, anything that evaluates to a true-false value. So by default, this will display true, which is a 1, and this will display false, which is a 0. Okay, so by default, that is the way that we display Boolean values, as we saw in the slides. So why don't we run this program, and then we'll start modifying it just a little bit so we can start displaying the actual string true-false. Okay, so let me run this, and you can see right here, I'll move this over here so you can see what's going on. No bool alpha is the default. I didn't set it, but it was just a default. You can see I've set nothing here. All I'm doing is those two cout statements. And I'm getting a 1 here, and I'm getting a 0 here, exactly what I expect. Okay, so now let's make a few changes here. So you can see what I'm doing here on line 14. I'm inserting std bool alpha onto cout. It's a manipulator. This will switch the default formatting in this case now to true false. Now, it's important to understand, and we'll show you on lines 19 and 20 that this is true. Once we set that, everything else, whenever you need to display a Boolean value, this is the setting that'll stick. Okay, so if we need to go back to 0, 1, we have to do that manually. All right, so what we expect here now is to actually display the word true and the word false. So let's give this a run. And here you go. You can see the original two statements, 1, 0, but now we're seeing true, false. Okay, so here, all we're doing is showing that once we set it, it's set, right? So here it's set to true, false, and we just displayed two statements to see out. Now we've got another two, and we expect those to be true, false as well. There you go, true, false, true, false. It's going to keep doing this until you change it. And that's what we're going to do here on this lines 23 to 25. I'm using stood no bool alpha, so this is toggling it back to the default of 0, 1. And at this point, we should be getting 0, 1. So I should get, again, 1, 0, true, false, and then 1, 0 again. And that's exactly what I'm getting. 1, 0, true, false, and then 1, 0 here. Okay, so that's pretty straightforward. And believe it or not, what you're seeing here holds for every one of the manipulators that we're going to see. So it's the same kind of behavior, not the part of once you set it, it's set. Some of them just work for one insertion, but we'll talk about those. But I'm talking about the syntax and the general flow here. It's pretty much the same for all of them. So let me comment out these lines 28 to 30. And in this case, I'm doing the same thing, except I'm not using the manipulator. I'm using the setf method. So you can see I'm saying stood cout dot setf. Setf is the method, and it expects a stood iOS bool alpha. Now that looks maybe kind of intimidating and nasty. It's not so bad. Stood is the namespace, iOS is a class, and bool alpha is a flag that's defined in that class. Okay, so C++ is doing exactly what it was expected to do. If you just type bool alpha, it won't know where to find it. So you have to say it's stood namespace, iOS class, bool alpha flag. If you're using namespace standard, then you don't need to put stood here, or anywhere here that you see it lighting up, right? You could just use iOS bool alpha. Okay, so in this case, again, I'm setting it back to true, false, but I'm doing it with this method now. So you should see those last two statements display the words true, false. And there they are right here. You can see there's true and here's false. And then the last one is used to reset certain flags. All of these flags that we're going to use have default values. Okay, so when we talk about left and right justification and the way we display numbers or the way we display Booleans is in this case, they have default ways of doing it. We know the default for Booleans is the numbers 0 or 1, right? So there is a manipulator here called reset iOS flags. And again, it's in the stood namespace. So reset iOS flags, and then you pass into it whatever flag you want to reset. And it will reset that not to bool alpha, but it'll reset it to the default behavior for displaying Booleans, which in this case will be numbers, right? 0, 1. So when we run this, we expect that to be reset to the default. And what's nice about this is, suppose you've got a modifier that has, there aren't any like this, but suppose you had 8 different values, right? One of them is obviously the default. You don't have to worry about which one to set. You could just basically call this with the flag you want, and it'll reset it to the appropriate behavior. So let's run this, and now we expect those last two statements to print out 1 and 0. And there you go. So that's it. The basics of everything else we're going to do with the manipulators are here. We can use them in line. We can use them with functions. And what we'll do next is we'll talk about integer output. So we'll be right back to do that. In this video, we'll see some of the stream formatting options available for integers. Integers have 4 basic formatting options, and let's see what the defaults are for those options. First, integers are displayed in base 10 by default. This makes sense since base 10 is what most people in the world use as their base system. However, we also have the option of displaying integers in base 8, which is called octal, and base 16, which is called hexadecimal. Remember, computers work in base 2 or binary, and that's difficult for humans to understand. So we need alternate base systems. Base 10 is what we learned in school, and that's the way we count and do math. But it's not so intuitive to convert decimal to binary. The alternate bases are often used in computing since they allow us to group information more like a computer would. For example, since octal is base 8, we can group consecutive binary digits into groups of 3, starting from the right, and we can easily convert between octal and binary and back again. Hexadecimal is base 16, which allows us to represent locations in memory since each hexadecimal digit represents 8 bits or 1 byte. If you recall, earlier in the course, when we displayed addresses, they were displayed in hexadecimal format. We also have the option to display the base as a prefix for hex and octal values. For hex, we start with 0x followed by the hex number, and for octal, we start with a 0. This clearly tells the reader that the number is hex or octal, since in some cases, it would be impossible to tell otherwise. The default is not to show the base. We can show the letters and hex numbers as well as the hex prefix in upper or lowercase, and lowercase is the default. And finally, we can choose to display the plus sign when we have positive integers. The default, as we've seen already, is not to display the plus sign when an integer is positive. This might sound complicated and intimidating, but it's easy as pie. Let me show you how we can use the IOStream manipulators to change the way we format integers. First, let's see an example of displaying integers using different bases. Here we initialize num to 255. That is 255 in base 10, just like we're used to doing. Now we can use the base manipulators to change the way the integer is formatted. Remember, even though the output changes, 255 is still stored in num and we're not going to change it. First we use std_dec, and that means decimal, and that displays the number in base 10. We really don't have to specify this at all since the default, but I wanted to show you how to do it, and this will display 255. The second display statement uses std_hex. In this case, we display FF, which is the hexadecimal value for 255. Also note that the F's are in lowercase, which is also the default. Finally, we have the oct manipulator, and we display 277, which is the octal value for decimal 255. Once we set the base using the manipulator, that base will be used for all future insertions of any integer on the output stream, so that setting will persist. Now, if we see 255 and 277 out of context, it would be virtually impossible to tell whether they were base 8 or base 10. So that's where the show base manipulator comes in handy. I'll show you that in the next slide. So in this example, we have the same code, except we're using the show base manipulator. Now, when we execute the same code, notice that 255 is unchanged, but the hexadecimal FF now has a 0x prefix, and it's in lowercase. Also, the octal 377 now has a 0 preceding it. Now it's very clear what the base of each of these numbers is. Also note that the show base is applied to all further integer stream insertions, so it also persists. We can toggle back to not showing the base by using std_no_show_base. Sometimes we want to be able to display hexadecimal digits in uppercase as well. And sometimes we want to display the 0x prefix in uppercase. We can do this with the uppercase manipulator. In this case, we're using show base and uppercase. And then we use the hex manipulator and display the number. Notice how we display 0xFF and all the letters are uppercase. Like show base, uppercase will be used for all further hex output, and we can toggle back to lowercase using no uppercase. Now let's see how the show positive manipulator works. If we use show pos or show positive, then we'll get a preceding plus sign on positive integers. You can see in the provided code that we have two integers, num1, which is initialized to 255, and num2, which is initialized to minus 255. Without using the show pos manipulator, if we display these integers, we get 255 and negative 255. Note that there's no plus sign in front of the positive 255. However, when we use the show pos manipulator, now we see the plus sign in front of the positive 255. This can be useful sometimes depending on the application. Some accounting software wants that plus sign in front of the number. Again, this setting also persists, so it'll apply to any other integer stream output. And again, we can toggle back to not showing the plus sign with the no show pos manipulator. That's it. I told you it was easy. There are also several variations using the setF method, and we can also reset to defaults using std reset iOS flags and providing the flags we want. I encourage you to do as I do. That is, not memorize any of these things, but just know where to look them up. The C++ reference documentation is pretty good and everything's there. Unless, of course, you want to memorize them. That's up to you. Okay, so let's head over to the IDE and try some of these combinations out. Okay, so I'm in the IDE. I'm in the section 19 workspace in the manip_integer project. And what I'm doing in this project, just manipulating integers, just like we did in the slides. I'm converting them to different bases, and then I'm playing around with some of these manipulators. So let's start by, first of all, including IOStream and IOmanip. We need to do that in order to use our manipulators. And I've got an integer here that I've defined and initialized to 255. It's called num. Okay, so let's start right here. Here what we're doing is we're displaying num, and again, it's only the one variable we're going to use throughout this example. We're displaying it in decimal format. Again, we don't really need to do this here since it's the default. And then in hex, and then in octal. And so when we run this, we see 255 FF, which is the hex, and 377, which is octal, just like we saw in the slides. So that's pretty straightforward. And now, like I said, sometimes if you see those two integers or those two series of numbers, you really don't know what the base is. So we can use the show base manipulator right here, as I'm using right here on line 18. And now when I run it, we'll see the base. So now we're going to see the 0x right here in front of the hexadecimal number and the 0 in front of the octal number, which is pretty nice. That way you know exactly what the context, right? So you know this is hex and you know that this is octal. And obviously, you know that this is a decimal up here. Okay. I'll tell you a funny story. A couple of years ago, I was interviewing a candidate for a C++ programming position, and he was an entry-level position. You know, you ask him to write code and to ask him some questions about the language. So I asked him to write a program that accepted an integer and converted it to a hexadecimal number. And every other candidate that I've ever asked that kind of question to goes off and writes a function and does all kinds of stuff. This kid went over, wrote the program in like 30 seconds and told me he was done, and I couldn't believe it. So when I went over there and just ran it, his output was correct. And what he did was this, which was pretty clever, right? All he did was ask me for the integer, did a std hex, and printed it out. It was very, very clever. Very bright kid. I never would have thought about doing that in an interview. But anyway, he got the job, and he did really well in the end. So that's a good way to think outside the box. Sometimes you don't want to go for the fancy algorithms. Just do it the easy way. I'm all for that. But anyway, so here now, what we're going to do is, notice that, let me run this again so that you can see that the 0x and the FF here in the hex number are lowercase. If you need to have them in uppercase, we can use std uppercase, just like we are here on line 25. And when I run that now, you'll see that, oops, let me put that comment back. So when I run this now, you can see that now it's a 0xFF, and those are capitalized. That only applies to hexadecimal numbers because the hex numbers are the only ones that have letters in them. Okay. The show pos or show positive modifier right here. So let me uncomment this code out. And what this does, it only works with decimal values. And if the number is positive, then it displays the plus sign in front of the number. By default, we don't display a plus sign in front of the number. So let's run this, and you can see that right here on the 255, you can see that plus sign right in front of it. And that's exactly what that does. Notice that it has no effect on hex or octal. It only works on decimals. And in this case, there's a method called setF. And what we can do, and this isn't a manipulator, this is a method call. So we're saying std_cout.setF, so setF is a method. And then we can pass in these format flags. And what this will do is it'll set it to show base or no show base or uppercase or no uppercase, whatever you really want here. So it's an alternate way of doing what we did up here. Okay, and you tend to see this style more often than this style, but you'll see this sometimes out there. I just wanted to show you. Okay. Also, we can use std reset iOS flags to set these back to normal. So for example, this one right here, std iOS base field, that'll set your integer base back to decimal. Okay. Show base will set it back to the default for show base, which is not to show the base, right? That's the default. Again, remember, this resets it back to the defaults. This one, show positive, says it sets it back to not showing the positive, and the uppercase, it goes back to not showing uppercase. Again, so don't let that confuse you. We're not setting it to those flags. We're just telling it to set it to the default. Okay, so in this last example, I'm just using a real simple input statement. Let me uncomment that code out. And I'm asking the user for an integer, and I'm putting it right back into that num variable that we had before. And I'm just using default to display it as a decimal, and then as a hex, and then hex uppercase, and then hex again. And the point here is so that you can see that these settings stick. So this uppercase will still be uppercase, even though we've already used it, because they are persistent. And then no uppercase. And then finally, octal hex, we're going to show the base, and octal at the end. So again, really, really straightforward. Let me run it. And we can use a number like, let's say 135. And there you go. In integer is 135. The decimal value is 135. In hex, it's 87. And you can see the show base here because I've got no show base, right? Because that was my default. Right here, I set it back to the default to not show base. And that's why we're not seeing it. Notice that when we're not showing the base, this uppercase has no effect at all, which is exactly what you would expect, right? So that's it. In the next video, what we're going to do is we're going to look at the manipulators for floating point numbers and see how they work. In this video, we'll see some of the stream formatting options available for floating point numbers. Formatting floating point numbers focuses mainly on the amount of precision used to display the number. By default, the precision is set to 6 digits. We'll cover the specifics of what that exactly means in this lecture. We can also set the number of digits to display to the right side of the decimal point. By default, there is no fixed set size. We can also choose to show trailing zeros up to a certain number, and we can also decide if the floating point number 4 should be displayed as 4, or 4.0, or 4.00, and so forth. But by default, these trailing zeros are not displayed. And then we have some of the same options that we had when we used integers. By default, a lowercase e is used when we're displaying floating point numbers using scientific notation, and the plus sign is not displayed when we display positive floating point numbers. All of these manipulators persist once they're set. So first, let's take a look at how precision works. By default, the precision used to display floating point numbers is 6 digits, and rounding always occurs. In this example, we have the number 1234.5678. If we display this number, C++ will use 6 as the default precision and start at the most significant digit, which is the 1, and it will display 6 digits starting from there, rounding at the end. In this case, 1234.57 will be displayed. If C++ can't display the number in the given amount of significance, then it'll use scientific notation, and we'll see that in a bit. Here's another example. We have a large number, 123456789.987654321. I did it that way just so it's really easy to keep track of these digits. If we display this number, C++ will try to do it with 6 significant digits, but this won't work, since it will display 123456, and the number displayed wouldn't be accurate. So in this case, the number will be displayed using scientific notation. And notice 1.23457 has got the 6 digits of precision. That's the default. And notice that we're still using precision 6, but this time using scientific notation. Suppose we wanted to display the number using precision 9. We can use the set precision manipulator with a 9 as the argument to do just that. In this case, the number will display as 123456790. Note the rounding at the end. Also notice how no trailing zeros are displayed in this example. So that's the way precision works when we're not fixing the number of digits to the right of the decimal. When we use the fix manipulator, precision is handled differently. Now we're looking at precision starting from the right side of the decimal point. In this case, we still have a default precision of 6, but we're also using the fix manipulator. This will use a precision of 6 starting with the digits after the decimal, and will round as necessary. So in this case, exactly 6 digits are displayed after the decimal point, and zeros are added if necessary. As you can guess, set precision to and fixed are commonly used to display currency amounts. We actually did this in a few of the course lessons. In this example, we're still using that very large number, but we're setting the precision to 3 and also using the fix manipulator. So now this will display exactly 3 digits after the decimal point, and rounding will occur. So we've got a 0.988 after the decimal point. In this example, we want to set precision to 3 and also use scientific notation. You can see the manipulators being used, and the display is exactly as we expect. 1.23 times 10 to the 8th. Notice the precision is 3, and we see that with the 1.23. We can display the E in the scientific notation format as a capital E by using the uppercase manipulator. Remember, by default, it's no uppercase. Now let's see how the show positive manipulator works with floating point numbers. The behavior is the same as we saw with integers. If we use the show pos manipulator, then we'll get a preceding plus sign on positive floating point numbers. Note that we can toggle back to not showing the plus sign with the no show pos manipulator. With floating point numbers, we can also use the show point manipulator. This will display trailing zeros based on the level of precision used. For example, if our number is 12.34, and we display it using only the defaults, then 12.34 will display. We're using a precision of 6, but only 4 digits will display in this case. If we wanted to add trailing zeros up to precision, we can use the show point manipulator. Now you can see that 2 zeros are added to the number being displayed. Again, you can use the no show point to toggle back to the default behavior. Finally, if you want to reset the floating point format back to the general format, you can do that in one of 2 ways. You can use the unsetF method, or you can use the reset iOS flag manipulator. There are a bunch of other flags, but at this point, you know what you would need, so rather than list them all here, I'll refer you to the C++ reference docs. Now let's head over to the IDE and we'll format some floating point values. Then in the next video, we'll finish off formatting with setting field widths, justification, and filling. Okay, so I'm back in the IDE again, and I'm still in the section 19 workspace, and I'm in the manip_floating project. And what we'll do here is we'll play around with some floating point numbers. Now let's take a look at the numbers that we'll be using for this example. We've got 3 numbers right here. They're all doubles, and you can see I've got one that's going from 1 up to 9, and then from 9 down to 1 after the decimal point. That'll just make it really easy for us to see which digits are being rounded. I've got another one that's a little smaller, 1234.5678, and I've got this last one right here, 1234.0. Okay, and what we'll do first is we'll just do normal displaying these guys out to the console with absolutely nothing fancy, no manipulation at all, just using pure defaults, and that's what's going on right here. On lines 14 to 16, I'm displaying num1, num2, num3. Now remember, by default, we've got 6 digits of precision. We're not showing the positive sign, we're not showing trailing zeros, and we're not showing uppercase letters in scientific notation. Okay, that's the default. So let's run this first. Now, what do we expect here? We expect num1 to not be able to work, right? I mean, if you think about this for a second here, you can see that num1 has, let's assume we wanted to display 6 significant figures right here. We would display 1, 2, 3, 4, 5, 6, and that would really give us problems, right? Because that's not even close to being an accurate number. So C++ won't do that. What it'll do is it'll display that number in scientific notation, and it will still use 6 for precision. I'll show you how that works in a second. Now this guy can be, right? There's 4 digits right here and then 2. So we expect those 6 digits to display, and those last 2 will be rounded. And this guy here, remember, by default, we don't display trailing zeros. So that's just going to display 1, 2, 3, 4. So let's run this, and we'll verify that we got what we expected. Okay, so let me move this window over here so we can see what's going on. Let me do that again. There we go. So in this case, we're displaying num1, right? And notice what happens. 1.23457. You can see the rounding. You can see all 6 digits being displayed here. But we're using scientific notation because there's no way that it can be properly displayed, or accurately displayed, I should say, in 6 digits. This next one, though, num2, right, 1234.57. That's exactly what we expect. Here you see the 6 digits. And then num3, 1, 2, 3, 4 is displayed. There's no .0 or .00 unless we use a modifier, which we'll use in a little bit. So that's the default. And it's really important that you understand the default and how it begins. So that's using the default settings. Now let's try something. We're going to set the precision to 2. So what we're asking for is 2 significant digits. It can't do that with any of these, right? 1.2, 12, where's it going to stop? So what it'll do is it'll display all 3 of them in scientific notation using a precision of 2. So I'll show you how that looks. And you can see exactly what's going on. 1.2 for all of them. Those are the 2 significant digits of precision, right? Times 10 to the 8th, the 3rd, and so forth. So now let's set a precision of 5. Now we'll be able to do some of them with a precision of 5, but others it won't. So I'll uncomment this block out. And let's execute that. And now you can see what's going on. Num1 cannot be displayed in 5 significant digits here. So the precision is going to be 5 digits here, but it's going to be in scientific notation. The other number up here, I'll scroll up so you can see it, 1,2,3,4.567. There are your 5 significant figures here, right? Your precision is 5. So what it's doing is it's rounding that 5th one, which is 0.56 to 6. And then again, the last one is 1, 2, 3, 4. We're not adding any zeros or anything. So that's the default kind of behavior. So that really gives you an idea of what's going on. In this case, we're going to set precision to 9. Everything will fit here. So let's try that. And you can see what's happening with precision 9. I get 1, 2, 3, 4, 5, 6, 7. Instead of 89, I'm getting 90 because it's rounding that. This guy's displaying all of it because it can display all of it, right? 1234.5678. And the 1, 2, 3, 4 still displays the same way because we're not adding any zeros. Okay? So now you understand precision. Now let's talk about fixed and how it changes precision. So what we're doing here is we're setting precision to 3. You can see that happening right here on line 40. And we're fixing the decimal point. So now the precision happens after the decimal point. Okay, so let's run this and take a look at the output. Okay, so take a look at the output here. Again, I'll scroll up so we can see these numbers up top. So now we're displaying 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We're displaying all of that. And the precision now applies after the decimal. So notice that all 3 of these guys are displaying 3 digits after the decimal because that's the precision. And we're fixing that size. So it's going to round. In this case, 9876 becomes 988, and 5678 becomes 568. And in this case here, you can see that it's displaying all the zeros on the end, okay, because we set the fixed formatter. All right, so hopefully that makes sense. Let me stop that, and we'll run a couple more. Let's take a look at this example. What we're doing here is we're setting the precision to 3, and we want to do scientific notation. So this should be very similar to what happened before with the precision 2 when stuff wouldn't fit. So again, precision is 3 and scientific notation. So what we get is right down here, 1.235. Notice the precision is 3, right? But what happened? Because it's fixed, I set fixed up here, and fixed is persistent, so it carries down. Even though I didn't say fixed right here, it's fixed because I've set it up here. So in this case, I get the 3 decimals after the decimal point, the 3 digits, I should say, after the decimal point, and it's all in scientific notation. And then a couple more examples. You notice that that E in the exponential notation, in scientific notation, was a lowercase e. I can make it a capital E by simply using stood uppercase here. And let's just run that to be sure that we get it. And there you go, right down here at the bottom, you can see 1.23, and you can see the E is capitalized here, whereas it was lowercase here in the previous example. In this case, I'm using the show positive. And what I'm doing is I'm just setting it to precision 3, fixed, and show positive. So this will show a positive plus sign in front of positive numbers. Let's run that. And then you can see down here at the bottom again, I'll move this up just a little so you can see it a little better. You can see the plus symbol being displayed in front of all these positive floating point numbers. If they were negative, obviously the negative sign would show. Now, we can set these guys back to the defaults, either by doing an unset F, calling that method, and we can pass in scientific and fixed, setting them back to the defaults. And what we're doing here is just a binary or we could use the reset iOS flags manipulator here and pass in show position, and that'll unset that. All right, so let me clean this up here. Now notice what I'm doing here. I'm setting precision to 10, and I'm telling it to show point. Okay, what this is going to do is going to add these trailing zeros up to 10 spaces, all right, or up to 10 precision. So let's run that, and we can see num1, num2, and num3. There you go. You can see right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. It's rounding here. And then 1, 2, 3, 4, 0.5, 6, 7, 8. We've got a couple of zeros on the end, but you notice all of them now are in precision 10, right? And in this case, we have 1, 2, 3, 4 point and then 6 zeros at the end. We'll set these guys back to the defaults, and I'll show you how to do that right here. And then we'll run one more time, and we should get that same behavior we got at the very beginning. So what I'm doing here is I'm setting this back to the general notation here. I'm setting the precision to 6, which was the default. And I'm setting show positive and show point back to their defaults. And then I'm just displaying num1, num2, num3 at the end. And what we should get back is what we got at the beginning. So down at the bottom, here you go. We get the scientific notation for this guy. We've got the 6 precision digits here, and we've got the 1, 2, 3, 4 right here. Okay, so that's it. That's a good example of these floating point formatters. They're pretty powerful. They're pretty easy to use. In the next video, what we'll do is we'll learn about setting field widths and justifying things left to right. And you can use those along with these to really format tables and get your format looking really nicely for output. In this video, we'll see some of the stream formatting options that are available that work with any type of data. These are very powerful and easy to use. They give you the ability to define a field width and then display the next data item either left justified or right justified within that field. We can also specify the fill character that will be used to fill up any unused space. By default, there is no field width defined, and all output occurs right after the previous output, as we've seen already in this course. If you do set a field width, then the next data item displayed will default to right justified within that field width. It's important to understand that if you set the field width and justification, they are only applied to the next data item placed on the output stream. When we set the fill character, that will persist until you change it. Again, this all might sound really complicated, but it's pretty easy, and a few examples will show you exactly how it works. But first, let's look at the defaults. Here's an example that uses absolutely no stream manipulators or methods. This is the default behavior when you put data on a stream. As you can see, we're displaying the floating point number 1234.5678 and then the string hello. The number will display with 6 digits of precision, and it will round. And then hello is displayed immediately following the number. If we modify this program slightly so that it prints the number and the string each on a new line, then we get the number displayed as before on the left side with no padding up front, followed by the string on the next line. So far, this is what we've seen, and it should be pretty clear. So now let's set the field width of the next data item placed on the stream using setW. In this case, we're using setW with a 10 as a parameter. This will create a field width of 10 for the next data item only. In this case, that data item is num. Notice that num will be displayed right justified by default in a field width of 10. I'm displaying a ruler of numbers just above the actual display so that you can see the alignment. This ruler isn't displayed by the code. It's only there so you can better follow the examples. Notice that the last digit in number, the 7 in this case, is displayed in position 10. That's the rightmost side of the field width we set earlier. But now look what happens when we display hello. It displays right next to the number starting in column 11. That's because the field width and the justification only apply to the next data item placed on the stream. In this case, that data item was num. So hello has no field width associated with it, and it uses just the defaults. In this example, we set the field width of each of the 3 data items to 10. And remember, when we have a field width, the default justification is right. So in this case, num is displayed right justified in a width of 10, The first hello is displayed right justified also in a field of 10, and the last hello is also displayed right justified in a width of 10. And you can see from the display in the ruler exactly what's happening. This example shows how the field width only applies to the next data item put on the stream. In this case, we set a field width of 10, and we want left justification for the next data item, which is num. And we get what we expect. Num is displayed in a field width of 10, and it's left justified. Now we want to display hello. Notice that hello has no field width associated with it, so it will display starting in column 11. In this example, we'll set the field widths for all three items displayed. Num will have a field width of 10, and it will be right justified by default. The first hello will have a field width of 10, and we're explicitly setting right justification. We don't have to do this since it's the default, but we can do it to be very explicit. And the second hello will have a field width of 15, and it will also be right justified. You can see the output is exactly as we expect. Num is right justified in a field width of 10. The first hello is right justified in a field width of 10, and the final hello is right justified in a field width of 15. Now let's take a look at the setFill formatter. This only works when a data item has a field width associated with it. We supply the character that we want to fill any empty space in the given field width. Here's a simple example. We're setting the fill character to a dash with the setFill manipulator, and we're setting the field width to 10. This will apply only to num, which is the next data item on the stream. So we expect num to be right justified in a field width of 10, and the remaining space in that field to be filled in with dashes. That's exactly what we see. But what about the hello that we display next? We said that setFill was persistent, but we don't see any dashes with that hello. That's because that hello doesn't have a field width associated with it. So setFill only applies when we've set the field width. So let's look at one final example. In this case, we're setting the fill character to an asterisk, and then setting the field width of num to 10. We expect num to be displayed right justified in a field width of 10 and asterisk to fill in the remaining space. And you can see by the output that that's exactly what we get. Now we set the fill character to a dash and the field width to 10 for the first hello. We expect hello to display right justified in a field width of 10 and the blank space filled in with dashes. Again, that's exactly what we get. Then finally, we set the field width of the last hello to 15. We expect hello to display right justified in a field width of 15. And since setFill is persistent and the last hello does have a field width, we expect that those blank spaces will be filled in with dashes, and as you can see, that's what we get. So you see, it's really not that complicated, and the rules are very consistent. Using the formatting manipulators that we've seen in the last few videos, we can have a good amount of control over how our output looks. Now let's head over to the IDE and we'll see these stream formatters in live code. Okay, so I'm back in the IDE. I'm in the section 19 workspace, and I'm in the manip_fields project. And what we'll do here is we'll play around with the field width, the justification, and the setFill. You'll notice on line 7 here that I've got a function called ruler, and all that function does is just display a line of numbers, and that way we can line up our columns easier when we see them. Okay, you don't have to do this, but it just makes it easier to learn exactly what's going on. And then I've got these 3 data items here that I'm using. I'm using num1, which is an integer, and it's 1, 2, 3, 4. I've got num2, which is a double, 1, 2, 3, 4, 0.5678, and just a simple string hello. First thing we'll do is, just like we did in the slides, let's just do the defaults. So all we're doing is we're putting num1, num2, and hello onto cout, and when we run that, you'll see everything just runs up together. So let me build and run, and then we see 1, 2, 3, 4, that's the integer, and then 1, 2, 3, 4.57, rounded 6 significant figures here, that's our precision, and then the hello. Everything jumbled up together, right? One right after the other, that's exactly what we expect. Okay, we can obviously, let me comment this code out, we can obviously display 1 on each line, and sure, that'll help us read it a little nicer, because now we'll see each 1 on each line. But remember, the defaults are being applied. So we're getting 1, 2, 3, 4 as the integer, 1, 2, 3, 4.57, which is rounding to the 6th precision for the digit, and hello again. Now let's play around with the field widths. And here's a simple example. What we're doing is, again, we're displaying the ruler, and then we're setting the field width to 10 for the next data item that's being put on the stream, which happens to be num in this case right here. So num will be displayed in a width of 10. And if you recall, num is that integer 1, 2, 3, 4. So that will be displayed in a width of 10, and the default is right justified. But then when num2 and hello are displayed, there is no field width associated with them. That field width only associates with the next item. So these two should print right next to each other and right next to num1. So let's take a look. And there you go. You can see 1, 2, 3, 4 right here. And let me grab my pencil and I'll draw in white. I think it'll be easier to see. You can see right here the 1, 2, 3, 4 right there. That's our integer. And that's the 10th, right? The 10th column. So it's being right justified in the 10th column. But then after that, we're seeing our double and our string all printed, run right next to the other, no formatting applied. Now let's do one more example. Actually, let's do a few more examples. Let's do this one here. And the source code's available to you. I encourage you to go in there and play around and change things around. That's really the best way to learn it. Okay, so now look what we're doing. We're setting the width to 10 for num1 and for num2. So now we expect num1 to be right justified in a width of 10, num2 to be right justified in a width of 10, and then hello with no formatting, just put right on the end of it, num2. So let's run this. And here down at the bottom, you can see that that's exactly what happens here. There's my field width of 10, and there's 1, 2, 3, 4 right justified in there. Here's the other width of 10 right here, the next field, and you see 1, 2, 3, 4, 0.57 right justified in there as well. And there's my hello. I'm going to put a couple of new lines at the end just so that it'll separate that time elapsed message a little bit. So it'll be a little bit easier to see what's going on. And there they are. I just had them commented out. So I'll uncomment them. Okay, so let's take a look at this example now. I will uncomment this code. And notice what's happening here. I'm setting the field width to 10 for each one of those items. By default, we're going to right justify everything. So num1, num2, and hello will each display right justified in a field width of 10. And let's give that a run. And there you go. You can see 1, 2, 3, 4, the integer in the field width of 10. 1, 2, 3, 4, 0.57 in its own field width of 10. And hello, you can see the 0 right there, right? That would be the 30th column, the third field width of 10, and it's right justified. Comment this out and see what this is doing. Now this is doing exactly the same thing, except we're left justifying each one of these. Now remember, we want to left justify them, we have to say it explicitly. Right justified is the default. I always like to put in left and right. That way, whoever's reading my code afterward understands exactly what's going on. Even though we know it's the default, somebody might have forgotten. So it's nice to see that there. So here, width of 10, left justified, num1, width of 10, left justified, num2, and width of 10, left justified, hello. So let's give that a run. And you'll see the difference between this guy right here where they were right justified and now down here where they're left justified. So you can see that 1, 2, 3, 4 is displaying in column 1, 1, 2, 3, 4.57 in column 11, and hello in column 21, just like we expect. Okay, so now let's do a couple with the set fill, and I'll comment this out and we'll walk through this in a minute. So notice what I'm doing here. I'm setting the fill character to the dash. Now this is a persistent setting. This will persist until I change it. And what I'm doing here is I'm setting the width to 10, left justified num1. Now num1 was only 4 digits, right? So the rest of the space in that field of 10 is going to be padded or filled with that dash character. And the same thing will happen to these guys. Remember, if we don't have a width set, then the set fill doesn't apply. It only applies when we're setting the field width. So in this case, we expect to see all 3 of these guys left justified in a field width of 10, and all the spaces that are left over, all the blank spaces in that field of 10, filled with dashes. So let's take a look. And there you can see right down here, you can see 1, 2, 3, 4, and then dashes all the way to the 10th position. And then 1, 2, 3, 4.57, dashes all the way to the 20th position. And then hello, and dashes all the way to the 30th position. Okay, had we right justified them, the dashes would have been on the left. It would have filled any empty space in that field width. And The last example is we're using different set fill characters. So we're setting the field width to 10 for each one of them again, and we're left justifying. And in this first example for num, I'm using the asterisk as the fill character. For num2, I'm using the hash mark or the pound symbol. And for hello, I'm using the dash. We should see 3 different fill characters filling up all that space. Remember, once this statement is done, this is the fill character that's set. So that's going to persist until I change it otherwise. All right, so let's run this. And there you can see that I'm using the asterisks for the first field, the pound signs or the hash symbols for the second field, and the dashes for the final field. Okay, so that's it for this video. In the next video, we've got a challenge where we're going to put some of this stuff together to display a table. Now you get a chance to play with them and put them together and understand how you can use your precision, your left, your right, your fixed, and so forth all together to create a table of tour prices for trips to South America. So that's the challenge coming up in the next video. Welcome to the first challenge for section 19. This challenge is all about using what you learned about formatting output to format a table of tours to different cities in South America, including prices and so forth. And we'll get to that in a second. But I'm in the section 19 workspace, and there are 2 projects. Challenge_1 is the source code that I'm providing for you, and challenge_1_solution is my solution to the challenge. So let's take a look at what the challenge is all about. Then I'll give you a sample run, and then you can try it out on your own. So as I said, it's about formatting output, and we're going to do everything to cout. We're going to display everything to the console. Later on, we can change that and display to files, and that's what we're going to learn next in this section. So let's start. I'm giving you the starter source code for the challenge, and I'll go through that in just a second. But the challenge is for you to display the provided data in a nicely formatted table. Your table doesn't have to match mine. You can do however you like. The point is for you to become comfortable with these manipulators. Play around with them. Don't just try to mimic my table exactly. Be creative. Do your own thing. So I'm going to give you 3 structures. We haven't really done these sorts of structures before, but they're really, really straightforward. They're not classes. We're going to use structures because we don't really need to model operations. We just want to model data. And when we're modeling data, it's really common to just use structures. Again, I'll show you what they look like in just a second. So the first thing is these structures work together to create a tours structure. And that's going to contain information about tours to South America. And the tours include the countries that you can visit, the cities within those countries, and those cities have population and cost data associated with the tour. I know population, I was thinking the same thing. I just wanted a really big number so that you could format it. Watch the challenge video, which you're obviously watching right now. But if you're looking at the code, I'm hoping that you come back to this video and watch it so that you can see what the expected output looks like. I tried to copy the output to this document here, but everybody's got different fonts, and some of the fonts aren't monospaced, and the document would look really weird. So I'll just run it for you so that you can see exactly what it's supposed to look like. In the code, I'm going to give you some starter code that displays all the data from these structures and vectors using tabs to kind of align things, and it looks pretty ugly. But your job is to clean it up, make it look pretty. Okay, so as I always say, have fun, create functions, constants, do whatever you think makes sense, explore, play around, do it, and then do it again a different way. That's how you really, really learn. Okay, so let's go to the source code. So again, I'm in the challenge_1 project, and I'm looking at the main code right here. And let's go over these data structures. First of all, what we've got is we're including our normal group here. We've got IOStream, we've got IOmanip, since we're going to use the manipulators. We've got a vector, and we've got a string. And we've got these 3 structures right here. Here's the first one. It's city, country, and tours. And let me start with city. Think of a struct. We talked about a struct a little bit earlier in the object-oriented classes and methods section. It's like a class, except everything's public. You can have constructors. You can have all kinds of stuff. But typically, we use structs like this to just model data. Sometimes you just want pure data, and you don't want to deal with constructors and methods, and you really don't need any of that. So this is just a good way to collect data together. So what we've got here is we've got a city. And each city has a name. So let's say the name for one of the cities is Bogota in Colombia. a population, which is a long, and I don't know how many millions there are. I made some of those numbers up. Let's just say 18 million or something like that. And the cost of taking a tour to Bogota from Miami. So that's $569. And again, I don't know what that number is. It's in the data you'll see in a minute. So that's a city. We're going to have many of these cities, right? We'll have Rio de Janeiro. We'll have Santiago, Chile. We'll have a whole bunch of places that we can visit in South America. Each one will be modeled by a city. Perfect. Now, let's look at the country. The country has a name. In this case, it would be Colombia. Right? And it has a stood vector of cities. Okay? So I might have 3 or 4 cities associated with Colombia. I might have 2 or 3 cities associated with Brazil and so forth. So this is how we structure our data using these structures, building one within the other. Finally, we've got our main object here, which is the tours, and it has a title. And that title, I don't remember exactly what it is, but I'll show it to you in a minute when I show you the data. It's something like tours to South America or something. It's some big title that'll be the header on our report. And the tours has a vector of countries. Okay, makes sense? So we could have the title, which is this guy. And then we could have, let's say, Colombia. And we could have Brazil as our countries. And we could have Argentina. And then the countries have cities within them. You can see them right here. So you may have Bogota here, and the population is 18 million, and the cost is $567 or something like that. Then you would display the next city and the next city. Then you'd go to Brazil and you'd display Rio and so forth. So this is what our report is going to look like. And the reason we structure this data is because it makes it so much easier to process that way. We don't have to just play around with hundreds of arrays and strings and so forth. So we're using what we should be using. We're using stood strings and we're using stood vectors. I mean, that's what modern C++ is all about. It's not using character pointers and we're not using anything else, just real solid data structures. Okay, so how do we initialize these guys? Let me scroll down just a little bit. And here you see some of the initialization. And this is done for you. I've already written this for you. You could just use it. Notice that this piece right here, and this is using our uniform initialization, right? This is the kind of stuff we've been using all along, except we're doing it all in one shot here. So here is a city. Here's another city. Here's another city. Here's another city. These 4 cities are a vector, and that vector is the vector of cities in that country, Colombia, right? And that country, Colombia, is one of these guys. And here's the title at the top of the tours. So all we're doing is we're building this using uniform initialization, which makes it really, really nice to visually see what's going on here. So you could see that I've got, let me scroll up just a little bit here. So hopefully we can see them all. Yep, I think we can see them all. Great. So in this case, there's my title. Okay. Here is a country, another country, another country, another country. Okay, I don't know what happened to my mouse. It all of a sudden got really big. Let me fix that real quick. And within those countries, I've got cities and cities and cities. And here's a single city. You can always assume that there must be, if you've got a country, you must have a city. So you can assume that you're never going to have a country without a city. That'll just make your processing a little bit easier. That's it. So that's our data. And let me show you how you would work with this data. So let me scroll up and clear this a little bit. Here's the code I'm giving you. And you may not see it right off the bat, but it should be pretty intuitive once you start walking to it and thinking about it a little bit. You can see what we're starting out here. We're displaying the title. The title is part of that tours object, right? Tours.title. And then for each country that's in the countries in that tour object, so we're going to loop through all the different countries, right? Colombia, Brazil, Argentina, and so forth. For each one, I'm displaying the name. And then I'm looking through that city's vector that's inside of it. And for each city in that city's vector, I'm displaying the city. That's really it. It's really, really straightforward. Again, take a minute, understand the concept, walk through this. Before you start trying to format this data, make sure you understand how we're getting the data. It's real important. Once we do that, we can display this information. It's not going to look very pretty because you can see we're using tab characters to kind of align these columns, and it's not going to do a real good job, but at least you'll be able to see what's going on. If I run this now, it'll be the output that you should be getting as well. So let me run that project right now. That's what you should get. Tour ticket prices from Miami. You can see Colombia and the cities, Brazil and cities, Chile and Argentina. But you can see this isn't lined up nicely because we're not doing any real formatting. We're just using the tab character. Okay, so let me stop that and then let me show you the solution output. Looks something like this, which is much nicer. And I'm displaying this ruler up here. I'm doing this in a width of 70 total. You don't have to do that. That's just what I chose because it's easy to see. You can see here I'm displaying tour ticket prices from Miami centered. There's no way to center something. Remember, when we use the set width and the justification, we can only do left or right. So centering it, you're going to have to do maybe a little bit of math and figure out what's the center. Now I've got a header here where I'm displaying the country, the city, the population, the price, a line of dashes, and then I'm just lining up the data. So I've got all the countries, Colombia, Brazil, Chile, Argentina, the cities within the countries, the population of those cities, it's right justified here in this field, as well as the price, which is right justified, and I've got the 2 decimal digits displaying. Okay, so that's it. Good luck with this one. Again, this project, this little challenge is more than just formatting. I really want you to understand the structures and how you access those structures using the vectors within the structures. It's really simple once you get it, and it's really powerful to be able to use those structures that have those vectors of structures within them. Very powerful, very easy to use. You saw how easy it was to declare the data. Okay, so that's it. Good luck with the challenge. I'll see you on the other side in the solution. Don't rush through this. Take your time. Once this challenge is over, we'll start working with files. Hello, everyone. Welcome back to the Section 19 Challenge 1 solution. I'm in the Section 19 workspace, and I'm in the challenge_1_solution project. I hope you found this challenge challenging. There was probably a couple of pieces that were kind of tricky. One of them had to do with displaying the country right next to that city the first time around, and I'll talk about that in a second. The other one might have been trying to center that title. So we'll go over both of those. Here are the structures again. Here's my city, my country, and my tours. I've got this simple function called ruler, which I'm just going to use one time at the very beginning, just so we can look at our alignment. And then I've got my structure, which has been initialized here exactly like I gave it to you. So the first thing I want to do is I want to look at my data, and I want to kind of look at the sizes of the data, make sure that there's nothing like a city that's got 30 or 40 characters in it. That way I can gauge what kind of field widths I want. So that's what I did. And what I've done here is I've decided to go with a total width of 70. And the reason I did that was just purely console based, because some terminal windows and some DOS windows and some shell windows, which is where we're running these programs, are 80 max. So I didn't really want them going over the 80 and then wrapping over and really making it ugly. So what I decided to do was keep the total width of the entire report to 70 characters. Okay. So 70 is our goal here. And then we've got 4 fields, right? We've got the name of the country, the name of the city, the population, and the cost. And obviously we have a title up here centered somewhere. And I'll talk about the title in just a second. So the way I decided to do this was to create 4 field widths, and I'm going to make constants from all of these guys. That way I don't have to use my numbers everywhere. I can just use these names. And if I ever need to tweak anything, I can just come here and tweak them, and it should be good to go. So 70 is the total width. My first field is a width of 20. So let's say that this is my first one here. Let's say that this is another 20 here. And then my last 2 are 15, which are a little bit smaller. This isn't to scale, but you get the idea. So this would be the country's name, right? So this would say, let's say Colombia would display here. And then the city would be over here. The population, and both of these guys, I'll just draw arrows here, will be left justified in that field width. Then I've got the population, which is a number, which will be right justified here. And I've got the cost, which would be some number with 2 decimal points on the end, and that's going to be right justified here as well. Okay, I've got a header over here, which is going to say country, city, population will be right justified over here. So it lines up. And over here, cost will be right justified. So that's sort of the structure that I've got in my mind. And I can tweak this as I go. Okay, so that's really pretty much it. Here are my field widths that I've defined. So again, 20, 20, 15, 15. We add them up to 70. So I know that I'm in the ballpark. Let's deal with that title. So I'm going to erase this real quick. And I'll scroll down just a bit. And what we want to do is we want to display the title. Now you'll notice on line 71 down here, I'm displaying the ruler. That's just going to display that series of numbers so that we can line things up. But let's talk about the title and what kind of algorithm we want. Again, we've got 70 for our total width of our report. And suppose I wanted to display something. Well, obviously the center here is 35, right? That's pretty clear. And suppose I wanted to display something that was 10 characters wide, a string that's 10 characters wide. The idea would be that I'd want to display 5 of those characters on this side and 5 on this side, right? That would center that string. If the string was 20 characters wide, I'd want to display 10 over here, and I'd want to display 10 over here. That way we know that that string is always centered. So we've got to do the math that lets us do that. And it's pretty straightforward. If you think about this, notice here, if the string is 20 large, right? We want 10 on this side, 10 on that side. And if 35 was the center, that means we really want to start printing that guy at 25, at column 25. And if the string was 10 characters big, we want to print it at 35 minus the 5, which is 30 right here. Okay, so that's really what my algorithm is going to be. Let me clear this because it's a little messy. And I'll do it one more time with an actual example. So here's the 70. We know we're at 35. And I want to display a string that's 40 characters wide. Okay, so what do? How do I figure this out? Well, I want to display 20 of them and 20 of them, and I want to line those up, right? So 35 minus 20 gives me 15, and that's where I want to start displaying that string. So how do we do this? You take the total length, which is 70. You subtract from it the length of the string that you want, which is 40. That gives you a 30. And then you divide that by 2. And that gives you the 15. That gives you exactly where you need to start displaying the string so it's centered. Okay, let's do another example. Suppose the string is 20 big. I need 70 minus 20 divided by 2 gives me 25. Does that make sense? Well, let's see. If it's 20, I want to do 10 on this side and 10 on this side. 35 minus the 10 is 25. Exactly right. So my algorithm makes sense, and it's really easy to implement. Let me show you how to do it. I'm going to scroll down just a little bit and we'll do the header right here. So what I'm doing here on line 72 is I'm determining what is the length of that title string. Well, where's the title string? It's in tours.title. I just want the length of it. Whatever that length is, I'm going to subtract it from the total width, divide it by 2. That's where I want to start displaying tours.title. But how do I do that? Well, it's really easy. I can set a width to that amount and just display an empty string. Remember that the set width applies to the next item that's being put on the stream. There it is. I'm not putting anything. It's just an empty string, but it's still going on the stream. Okay, so that should take care of centering that. And then the rest is pretty easy in this context, because what we're doing here is I'm setting my field width for the country to field 1, which is 20. Right? I'm justifying left, and I'm displaying country. So field width 1, which is 20, is going to be left justified, and right there is what I'm putting on the stream. So country, that string, is going to be left justified. Then field 2 is 20 again. Then I've got 15, 15. I'm doing the 2 left and the 2 right, just like I did before. And then I've got a new line. So that should display the title centered and my headers, those 4 names, right where I want them. The next thing I need to do is I need to do a line of dashes, right, to separate my my header from the content. And I want 70 of those dashes. I could just say, see out a big string of 70 dashes, right? But if I ever change my total width, then I've got to change that as well. So what I can do here is I can simply say, set the field width to the total width, that'll be 70. Set the fill character to the dash. And that's what I want to display, which is just an empty string, but it doesn't really matter because it's going to fill up everything with the dashes and then give me a new line at the end. That's it. let's run this and we'll see where we're at. And there we go. You can see tour ticket prices from Miami, that's centered. I've got my country left justified in 20, my city left justified in 20, my population and my price both right justified here in 15. And if you count them, you can actually see that it's all lining up just right. And there's my dash line of 70. Okay, in this case, 70. If I change total width to 80, it'll do 80. If I change it to 40, it'll do 40. That's the nice part about using those constants. Okay, so that's it. Now we need to get into the body of the report. Before we do that, let's do a couple of things here. This is important right here. Let me go back to where I was. Here we go. I want to uncomment these two lines out. Let's talk about these for a second. Okay. I want to set my fill back to blank, right? Remember, I changed the fill right here, and that's persistent. So I don't want to keep it that way. Otherwise, I'm going to get dashes all over the place. So I want to set it back to a blank character. And I want to set the precision to 2 and fixed. And that's basically for this guy right here, for the price. I want to be able to make sure that I've got 2 digits to the right side of the decimal. Okay. I only need to do that one time, and then we're good to go. And now comes the logic for actually displaying the data. And this is it. This is all there really is to it. There's a couple of tricky parts here, and I'll talk about that in a minute, but let's just talk about the outer loop first. Here's the outer loop. My collection is tours.countries, right? So each time I go through there, I'm going to grab a country structure. And each one of those country structures has city structures within it, right? So that's the idea, a vector of cities. So in this case, for each country in tours country, I want to execute this inner loop. And now this inner loop, we could have done this a lot more complicated, a couple of different ways to do this. I chose to do it a simple way with just one standard out statement right here, one cout statement that kind of does everything. But the only thing that's different here is, and let me make a little room down here so I can show you what I'm talking about. In the report, we could have done something like this. We could have said Colombia, and then the cities down here, Bogota, the population, the amount, and Cali, and the population and the amount. I didn't want to do it that way. I wanted to do it where this guy is down here, right there, right next to the first city. So it looks more like a report. Here it kind of just leaves all this empty space here, which I didn't like. But in order to achieve this, you've got to do a little bit of extra logic to do it. So let me show you what I did. For each one of those cities, remember, outer loop is the country, inner loop is we're looping through the cities vector in the country. So each time we loop in here, we're going to get a city. So what we're going to do is the only time that we want to display, let me write that again. The only time that we want to display the city and the country is that first time, right? That very first city is going to be different. The second city, I just want to display it like this. I don't want to display Colombia again, or I don't want to display Argentina again. Make sense? Okay, so what we're doing here is we're looping through the cities vector, and I've got my width set exactly like we did before, left, left, right, right. None of that changes. The only difference here is this one line of code right here. This is using the conditional operator. Now, if you remember the conditional operator, it's an if-else statement built right into an expression, which is kind of cool. So here, I've decided to use a for loop, not a range-based for loop, but a regular for loop, because I need to know when I'm at the first one. The first one will be when I is 0. So notice what's happening here. When I is equal to 0, I am displaying the country's name. That's what I want. When I is not equal to 0, that means that I've already displayed the country's name. I'm displaying cities now. Then I just don't want to display anything on that line. Make sense? So the first time through, I'm displaying the country, and then the city, the population, and the cost. The city, population, cost. The next time around, I will not be equal to 0, right? So I'm just displaying a blank. So I'm not displaying anything here, but I am displaying these 3. Okay, so it's just a nice little way to do this. That way you don't have to write multiple cout statements depending on all kinds of conditions. Okay, so that's that first one. The rest are really simple, right? Grab the city at I, or the name of the city at I, the population and the cost. We're just looping through that vector, grabbing the fields that we want. And simple as that. Now, there are different ways to do this, and we'll learn how to do this when we talk about the standard template library using iterators, which is much nicer than using these loops. But when we get there, we get there. That's it. Let me run this, and we'll verify that it works. And there you go. And you can see right here, this is exactly what we wanted. You can see Columbia's here. Then I'm printing out that city right next to it. And then on the second city, I'm not displaying Columbia again. Okay. If you did it this way, great. If you didn't do it this way, you just wrote a blank line here and then you started with the cities underneath, that's fine too. I just think that this report looks nicer this way. All right, so that's it. You've got a whole bunch of stuff to look at here. Hopefully your solution was close. If your solution was better or quicker or more efficient, or you used a different kind of looping construct, post it in the forums. You don't have to post the whole program. Just post this piece here, this loop right here, because that's really the interesting part. The rest of the data is all same for everybody. Okay, so in the next video, we'll start talking about files. In this video, we'll talk about the steps needed to read input from text files using C++ streams. In the following slides, I'll talk about the main classes and methods that we can use to read from files. And then I'll go over a bunch of examples in live code so that you can see alternative ways to read text data from files, depending on the type of data we want to read. First, we'll talk about input files and reading from them. And then in another video, we'll discuss output files and writing to them. The two classes that I'll discuss for text file input are fstream and ifstream. There are a few steps that we must always perform when we read from files. The first is to include the fstream header file. Then we declare a stream object of either fstream or ifstream type. We then connect the stream object that we just created to the file that we want to read from on our file system. File systems are very different, so we have to be sure that we get the file name and the path correct. I'll talk more about that later. Once the file's connected and open, then we can read from it. There are many, many different ways to read from a file. We can read in binary mode, we can read in text mode, we can read one line at a time, one character at a time. We can use methods like getLine. And we can use the extraction operator like we've been doing with cin. Then when we're done processing the file, we have to close the file. This should sound pretty easy, and for the most part it is. In the next few slides, we'll discuss the details of opening a file, checking to make sure that the file was opened correctly, reading from the file in various ways, and then closing the file. So let's get started creating the stream object. In this example, we're creating an object named inFile. And we're using the fstream class as its type. Notice that I'm initializing the object as well. The initializer takes two arguments. The first is the name of the file. This can sometimes be very operating system specific and also very IDE specific. In the CodeLite IDE, we always open our files one directory up from where the executable lives. That's why we're using .. before the file name. I'll talk more about file names in the live code session. And I'll also include a video at the end of this section that talks about the file paths used for some other IDEs. But for now, let's assume that the file is where it's supposed to be. The second parameter specifies the mode and any other properties of the file that's being opened. In the first example, we're using std.ios_in. This means to open the file in input mode, so we're able to read from it but not write to it. By default, files are opened in text mode. In the second example, we're opening the file in input mode and in binary mode. This is necessary when reading non-text files that contain binary data. We won't be doing that in this course. We'll work strictly with text files. Notice the vertical bar or the pipe operator between std.ios_in and std.ios_binary. This is the bitwise OR operator. When used with bit fields such as these, it sets both the input and the binary modes to true. At this point, the file will be opened if it was found. In this slide, we used the fstream class. The fstream class can actually open up a file for reading and writing at the same time. We won't be doing that, but if you have a file that you'll use only for input, it's more common to use the ifstream class. Let's see that in the next slide. In this slide, we're using the ifstream class as the type for infile. ifstream is used for input files only. We can create an ifstream object the same way we created an fstream object. However, in the case of an ifstream object, the std_ios_in is optional since it's already the default. So the first two declarations of infile have the same effect. The last declaration opens infile in binary mode. There's another way to open a file that's commonly seen in code, so let's take a look at that next. In this example, notice that we're creating infile as an ifstream, but we haven't provided any file name to associate with it yet. This is a common use case since many times we don't know the file name and we have to get it from the user or from some other source at runtime. Once we have the file name, we can then use it and use the open method on the stream object to open the file. So we can say infile.open and provide the file name, or infile.open, file name, and then any flags we need to set. Now that we attempted to create the stream and connect it to a file, we have to be sure that this was successful before we start reading from the file. So let's do that next. So we have to be sure that the file was opened successfully. Maybe it wasn't found or there was some sort of hardware or permission issue. There are a few ways that we can check to see if the file was opened successfully. We can call the isOpen method of the file stream object that we created. This will return a Boolean indicating whether the file is open for processing or not. If we get back true, we're good to go. If we get back false, something happened and we can't read from the file. In the case of this error, what do? Well, it depends on the application. We might just display an error message and terminate the program. We might see if we can somehow recreate that file from a backup. It's totally application dependent. In our examples, we'll simply display an error message and terminate the program. If there was no such error, then we can go ahead and read from the file. Now let's see another way that we can test to see if the file was opened successfully. In this case, we can simply test the stream object itself. If we couldn't open the file, then this will return false, and then we can decide what to do. Otherwise, it's good and we can proceed reading from the file. But let's talk about the last step first. That is, closing the file. Once we finish reading from the file, we must close it. This is a simple method call to the close method. With input files, it's not so critical. But when we talk about output files, closing them is very important. Okay, so now that we know how to open a file, check to make sure that it's open, and close it, let's do the part that's the most fun, reading from it. There are many ways to read from a file. In these examples, we'll be using text files. We can read formatted data from the text file using the stream extraction operator. Remember that one. We've used it all along with cin to get input from the keyboard. Well, now we can use it again to get input from the file stream. In this example, let's suppose that we have an integer, a double, and a string in a text file, and we want to read these into our programs. You can see the text file's contents in the little box here on the slides. We can assume that infile was created successfully. Notice that we create three variables. Num is an int, total is a double, and name is a string. Now we can read from infile using the extraction operator. The first statement will read 100 and store it in num. The second statement will read in 255.67 and store it in total, and then read Larry and store it in name. That's it, simple as pie. We can have these three separate read statements on a single line. We can chain them all together, just like we did when we worked with cin. Sometimes we want to read files an entire line at a time, and we know that the extraction operators will stop when they see any white space. So in this case, we can use the getLine method. Remember that method? We used it when we read lines from the keyboard using cin. In this case, suppose our file contains the string, "this is a line." We create a string object called line, and then we use getLine with the name of the stream we're reading from and the string we're reading into. That's it. An entire line of text up to the new line will be read from the file and stored in the string named line. Reading a single line from a file isn't too useful unless the file only has one line, but usually files have many lines of text. So let's see how we can wrap this up in a loop to read all the lines in a text file. Here's the sample code. We can assume this code is in main and all the necessary header files have been included. First, we declare inFile as an IF stream and we connect it to myfile.txt. We also declare line to be a string object. That's where we'll store each line that we read from the text file. Okay, so first, let's make sure the file was opened successfully. You can see in the if statement that we're checking to see if not in file. Not in file will be true if the file was not opened successfully. And if so, we display an error message and we return something other than 0 and our program terminates. Otherwise, we have an open file and we can start processing it. We'll read the lines from the file in a while loop. And while we're in the while loop, you'll see the condition while not in file.eof. EOF is a method that returns true when we reach the end of the file. So we're looping while we have not seen the end of file. At each loop iteration, we use getLine to read from inFile and store an entire line of text into line. Then we display line to the console and we iterate again. At some point, we'll reach the end of the file and the loop terminates. Then we close the file and we're done. So as you can see, this program will read a text file from some file on disk and display its contents to the console. Pretty easy. Now let's see a variation of this program that does the while loop condition a bit differently. In this case, the loop is while getLine inFile line. At first you might think, what's going on there? Well, we can embed many of the string input statements right into the while condition. We can also embed statements that have the extraction operator in there. Since these statements return a reference to the stream object, they'll only return a true value when the read was successful. So when we reach the end of file or some other error condition is encountered, they will not return true and the loop will terminate. You can write code either way. Okay, so one more example and then we'll see some examples in live code in the next video. In this example, we're again using inFile as an IF stream object, but this time we're reading the file in an unformatted manner. In other words, one character at a time. Sometimes this is very useful since the extraction operator, getLine, and other methods depend on white space or new lines to be able to work correctly. Unformatted input reads one character at a time regardless of what that character is. The code in this example is exactly the same, except that in the while loop condition, we're reading a single character into the variable C with the get method. Then we simply output the character. So as you can see, this example also reads a file from disk and displays it to the console, but it does it in an unformatted manner, one character at a time. Okay, so in the next video, we'll head over to the IDE and we'll read some files, and I'll talk some more about those file names. In this video, we'll go over some examples of reading text files. So I'm in the section 19 workspace and I'm in the read file _1 project. And right now I've got nothing in here. The only thing I've done is I've included IOStream and I've included FStream. We obviously need to include FStream to work with files. That's all I've got. Here is my project. You can see it's open and the file that I'm going to read is not there yet. I wanted to show you how to create it. First thing we want to do is let's write the code to open the file. Then it will obviously fail because the file is not there. And then we'll put the file in there and we'll read it. Okay, so first thing we need to do is we need to create an input file stream and we'll just call it inFile just like we've done in the slides. And I'll initialize it on the next line. I'll open it on the next line. That way you can see that kind of syntax. So we'll say inFile.open. And here we give it a file name. Now this is the part that's pretty operating system specific. It's IDE specific. If you're in Windows, you might be tempted to do this kind of thing. C:/ and then some directory and then some other directory, maybe followed by some test.txt or something like that, right? That's the way that Windows file names look. The problem with this is, you remember that character literal that starts with a slash, that won't work because that right there becomes a character. So what we want to do, if you do it this way, you want to use 2 slashes. Don't forget, that's really, really important. You would want to use 2 slashes everywhere if you're on Windows. Now, if you're on Mac or Unix or some other operating system, then you really don't do that. You kind of just, / / directory names to the file. Now, the good thing about this is even if you're on Windows, you can still use this slash, and behind the scenes, it'll be mapped to the proper one. So that's what I would recommend you do. I would not recommend that you do anything like C: or D:, because that really ties your code to your computer. So for example, if you're trying to open a file in C:/frank/test, and then someone else tries to run this program, unless they've got a frank directory, it's not going to work. That file won't be there. So the best thing to do is just to do something like that. That way it'll look in the current directory, no matter what computer system you're on. Now, this is where the IDE issues come in, and I'll talk about that a little bit. For now, let me just leave that just like that. I want to open a file called test.txt. It doesn't exist yet here, as you can see, but we'll worry about that in a little bit. So we're trying to open that here. The next thing we need to do is we need to see if it was open. So let's say if not in file. And remember here we could have said if not in file dot is open, like that. Either one will work. This is the style I like, and that's the one I've been using a long time, and I'll keep using it. So if not in file, that means we could not open this, okay? So in this case, we're just gonna say std c error. We're gonna display an error message that says opening file, let's say. Just something real simple like that. What do we do here? I want to get out of here. I've got nothing else to do. I need this file to run my program. So I've got a couple of options. I can say return anything other than 0. 0 means the program completed successfully. I could return a 1. I could return a -1. It really depends on what number you're looking for. That means I couldn't find a file. So I'm just going to say return 1. Sometimes you'll see code that looks like this. It says exit 1, or more properly std exit. And in this case, that calls a function named exit that closes up certain things and destroys static variables and things. But right now, I'm just going to simply return 1 if I'm having some sort of problem opening the file. Now, if I get beyond this piece right here, I've got the file. It's good to go. So I'm just going to say std cout. File is good to go. I'm ready to read from it. That's it. That's the program. This will fail when I run it. So let's try it. I'm going to build and run. And it says problem opening file. How come? Because the file's not there. Okay, so let's create the file. What I'll do is I'll come in here into my project and I'm going to click on the source directory. This is what I would recommend that you do. Whatever files you create them in the same directory where your .cpp files are. Okay, so in this case, I'm going to put it right where my main CPP file is. I'm going to right click on that source folder and I'm going to select add new file. You could also do it from up here, add new file. And then I'm going to select any file and just give it a name. And I'm going to give it this name right here, test.txt. So I'm going to say test.txt. I'm going to press enter. And now you can see that test.txt file right here. And I can type some data into there, and I will in a moment. So now I've got the file. So now let's run it. Still a problem opening file. How come? Well, this is where the IDEs are all different. If I open this file up, this project up right here, I'm going to right click on it and I'm going to say open the containing folder just so I can open it up in Explorer here and look at it. Let me move it over from my other monitor. You can see that here's my C++ source file right here, my CPP file right there. And here is that test.txt file I just created, right? But the executable is not here. The .exe file is not here. It's in debug. It's right here. That's my exe file, the application. So when it runs, it's looking for that txt file in here, and it's not finding it. That's why with CodeLite, we have to do something like this, .. /. So in other words, I'm in debug. I need to go one level above, one directory above me. Now, if I try to run this, file is good to go. It found it. Usually, this is what you want to do. Most IDEs will work this way. CodeLite does not. I believe Code Blocks and Visual Studio will all work if you just type in the file name just like that. And then what you do is when you create your file, you create it where your CPP file is, and it'll find it. Depending on what IDE you're using, you're just going to have to play around with it until you get it and it opens it, and then you're good to go. Okay. Xcode, if you're using Xcode, we'll talk about that in the video at the end, because Xcode is a little bit different. CLion, it'll just a regular test.txt will also work. Okay, so that's it. So now we've got a file, we're able to open it. So that's perfect. That's the first step, right? If we can't open it, we can't read it. So I'm going to get rid of this file is good to go statement. I really don't want to say that again because I've got it. Now what I want to do is I just want to read some information from that file. So let's put something in there. I'm going to go into test.txt, and it's just a text file. So I'm going to say hello. That's it. I just saved it just now, and I'm going to go back to main CPP, and I'll create these variables up here just so they're all in one place. So let's create a string, and let's just call it line. Okay, just any variable name will do. And down here, what I want to do is, remember when we had cin, we would say cin into line. Well, it's the same thing, except we're not reading from cin, we're reading from in file. So what that'll do is it'll read one string. Right? It's going to remember the way the extraction operator works. It'll stop at a space or at end of file. It'll stop as soon as it sees some white space. Now we should have that string in line, and we could just simply display it right to the console. Okay, so let me go through this again before I run it. I'm opening the file. I'm testing to be sure that it's open. If it's not open, I'm displaying problem opening file, and I'm out of here. Otherwise, I'm reading from the file into line. Line is a string. And then I'm displaying whatever I just read. Remember, the file contains hello, so that's what I should see. Right? So let's give it a run. There's hello. So that came from that text file. Okay, so now what we'll do is, let's read a couple of other things in here. So I'm going to have an int. We'll call it num. And we'll have a double. And let's just call it total, just like we did in the slides. So now what we'll do is we'll modify that file here so that it's got a string, an int, and a double. It's already got a string. So we'll give it an int. And let's give it a double. 200.345. So that's my file. It's got a string, an int, and a double. Okay, so now we'll come down here. And what we'll do is we can read the string, and we could do this in separate lines. We could just do it all in one. I'm just going to do it all in one to save a little time. So I'm going to read the string, then I'm going to read the integer, and then I'm going to read the total. And what I'm going to do here is I'm going to display the line. I'll just display them in 3 lines. I'll copy that one. So here we're displaying the line, here we're displaying the num, and then finally we'll be displaying the total down here. Okay, so all we've done now is, rather than just read hello, we're reading hello, the integer, and the double. And when I run this, I should get 3 pieces of information displaying. There they are. Hello, 100, and 200.345. Pretty cool. And if we modify this file to look like this, this will still work, right? Because we're using that extraction operator, and it's going to stop right here when it sees a white space, and it's going to stop right here when it sees a white space. So we're pretty flexible as far as the format of this file. So if I run this again, you can see I still got those numbers right there. Okay, so that takes care of that example. And what I'll do next is we'll go to read file 2, and we'll do exactly the same thing, except we'll create more data here, and we'll read these inside a loop. Okay, so I'll be right back to do that. And actually, before we go to the next example, I forgot to close the file. So I wanted to be sure that you know that we need to close this file. So I'm just going to do infile.close. Okay, that's very, very important. I got carried away with showing you how to read. I forgot the simple things to close the file. So make sure you close the file at the end. Okay, so I've switched over to section 19, workspace read file _2 project. Okay, so what we want to do now is, rather than just read those 3 data items, we want to continuously read 3 data items. And let me show you what I did to the test file. Now we've got Frank, 100, and a double, Larry, an integer and a double, Mo, an integer and a double, and so forth. So what I want to do is, rather than just read the 1 line, I want to read as many lines as they're there. So we'll need to do this in some sort of loop, right? So we're going to use a while loop. And let me go back to my main, and I'll show you what's happening here. Everything else is exactly the same. I have included IO manip here just because I want to display those guys out at the end in a little bit of a formatted column. That way you can see it a little better. So I'm just displaying line, num, and total a little bit formatted. So here I've opened the file and I've checked that it's open. I'm assuming it's open right here. Otherwise, I can't get here because the return 1 would kick me out. So what do I want to do? Well, I want to have some sort of while loop here. I want to loop while not in file dot end of file, EOF, and that's a function that will return true if it's end of file or no, not true if it's not the end of file. And what I want to do in there is basically display this, but first I want to read the input, right? So again, I'm reading from in file, and first I'm reading the line. Actually, it should be name, right? But we'll just keep the name line, the num, which is the int, and the total. And that should do it. So again, while we're not at the end of the file, we're reading 3 items, displaying them, looping back up, reading another 3 items, displaying them, and so forth. And then when we're done, this time I remembered to close the file. Okay, so let's run this. And when it runs, that's the information you get. You get Frank, Larry, Mo, Curly, and you get the integers and the doubles here nicely formatted because I'm using the setW manipulator. So we can do that with end of file, but we can also do that by putting that this statement right here, right inside the while. So what we can do is we can refactor this a little bit. And what we'll do is we'll put this statement right in there. I'll just move it up here, just like that. All right, so now this is a little different. You have to wrap your head around this a little bit. So there's my in file, and I'm reading those 3 items. If I hit end of file, if anything fails, if I've got illegal data, anything, this will fail, and the while loop will fail, and I'm out of here. If I'm able to read all those 3 items, remember this is using formatted input because I'm using those extraction operators. So that's it. It'll read them, and then I'll display them. So if I run this, I should get exactly the same output as before. And there it is. Okay, cool. So now in the next video, this one's getting a little bit long, so I'll cut it off here. In the next video, what we'll do is we'll read one of Shakespeare's poems line by line and display it out to the console. Okay, in this video, what I want to do is read a poem from a text file and just display it out to the console. And we're going to use getLine to do that. So I'm in the section 19 workspace in the read file _3 project. And what I've done here is I've got a poem already, and I created a file called poem.txt, just like we did before. And this is Shakespeare's Sonnet 18 poem, and you can see it's 14 lines. And what I want to do is read each line and display it out to the console. Now, if we tried to do this with the extraction operator, reading one of these words at a time, it's much trickier because, when do we hit the end of line? We really don't want to deal with any of that. The simplest way to do it is just to read one line at a time and then display that line right out. So let me show you where the main is. This is about as simple as it gets. I've got IOStream, FStream included. You can see here I've created my in file, and I'm opening poem.txt in my parents directory, which is exactly where I want it to be in CodeLite. If the file is not able to be opened, I'm displaying an error again, and I'm out of here. And I'm closing the file at the end. So what I need to do here is simply process that file. So how do we do this? It's really just 2 lines of code. It's really, really straightforward. So what I'm going to do here is just say while. I'm going to use std_getLine. And there's 2 versions of getLine, by the way. There's a getLine that works with character pointers or C-style strings, and there's a version that works with C++ strings. We're using C++ strings from now on in the course, so that's what we're going to be using. So we're using std_getLine, give it the name of the input stream, which in this case is in file. And where do I want this read into? I want this read into line. We haven't defined line yet, so let's define line. And I'll do that right here. I'll say std string line. That's it. That's where the input's going into. So what do we do? Well, while we're getting a line and it's successful, this will be true. So what do we want to do with that line? We just want to display it right to the console. So can't get much easier than this. See out, line, and I need a new line. That's it. That's really that simple. So if I run this, there's the poem, right? One line at a time till I hit the end of the line. I'm reading that in and I'm just displaying it right back out. Okay, Pretty easy, right? Now you can see how easy it would be to write a file copy utility. We haven't learned about writing files yet, thinking you know where we're going, right? We can, just like we write to std_cout, we can write to a file. So we can easily write a utility that will copy a file. And we're actually going to do that. We're going to, when we get to the output file section, we'll read this file and maybe this one or Romeo and Juliet or something, a bigger one, and we'll write it out with line numbers and so forth. That way we can modify it a little bit. So that's it. This is using getLine, reading one line at a time. Now what I want to do next is I want to go into readFile_for project. And what we'll do is we'll do the same thing, but we'll use unformatted input. So we'll do it one character at a time. So I'll set that up and I'll be right back. Okay, so I'm back in the readFile_for project for the section 19 workspace. And what we're going to do here is we're going to read Sonnet 18 again, except we're going to use unformatted input. In this case, we're just going to use the get method. And what that'll do is it'll return one character at a time. And we'll just display that one character out. So the advantages of using unformatted input are you don't have to worry about new lines. You don't have to worry about end of files. You don't have to worry about fancy characters and different things that could maybe break the way that you're reading because it's formatted. And it's just going to process characters unformatted. It's pretty cool. It gives you a lot of flexibility. And that's what we'll do now. So this is where we're at again. We've got IOStream and FStream exactly like we were before. We've created our infile object and opened the file, and we've tested to be sure we've got an open file. We're closing it down here. So right in here is where we're going to do our processing of the file. How do we do this? Well, pretty simple again. While infile.get some character, C. Okay, we need to define C as a character, so we'll do that right here. We'll say char C. That's it. It's really pretty simple. So while this is true, what do I do? std_cout the character. And then that's it. I mean, down here, I guess we could print a new line here just so we get a little bit of space at the end so we can see a little better. But that's it. So while we're reading a character and it's true, right? We haven't hit end of file. We haven't hit some bad bits. We haven't had any hardware issues. While all this is good, we've got that C. We're just going to display it. So if we run this, there's the poem exactly like it was before. That's it. Now you're ready for the challenge. And the challenge is going to be a fun one. There's a couple of challenges actually. So I'll see you in the next video and I'll explain the challenge to you. Hello everyone, welcome to the Section 19 Challenge 2 project. In this project, what I'd like you to do is write an automated grader. Let me explain what that is. We want to write a program that reads a file, and this file is called responses.txt, which I'm providing for you. That file contains the answer key for a quiz that some students have taken, as well as the responses from the students for that quiz. The structure of the file is really simple. The first item in the file is the answer key, and it's just a simple string with a bunch of letters in it. Then you've got student pairs as far as student response, and so forth. So here's a sample file. You'll see right here on line 17 is the very first line of the file. That's the answer key. So in other words, the correct answers to this quiz are A, B, C, and D. Now we've got student response pairs here. As you can see, there are 5 students here. Frank's answers are A, B, C, D, and E, so Frank got a 5 out of 5. Larry got A, B, C, A, and C, so we only got the A, B, C part right, so Larry got a 3 out of 5. Mo got the B, C, D, E, so he's got a 4 out of 5. Curly's got the B and the E, so he's got a 2 out of 5. And Michael's got all but the first one, so he's got a 4 out of 5. That's it. So what you have to do is basically read this file, process the data, and then display the output. The output display is pretty straightforward. You can format it so it looks nice, but it'll look something like this. So it'll say student and score. It'll display the student. It'll display the score that they got out of 5. And then at the very end, you'll have a little footer that shows the average score. In this case, 3.6. You can assume that the data file is properly formatted. You're always going to have pairs. You're not going to have missing data. And you'll always have at least one student in there. Okay, so let me give a sample run so you can see what it looks like. So there's a sample run given this data right here. And as you can see here, I've got the student, the score, Frank, Larry, Mo, Curly, and Michael, and there's a score out of 5, and the average in this case is a 3.6. So here you'll get a chance to read a file, to do some processing, and you'll get a chance to use your manipulators to line this up so it looks nice. Let me show you the file itself. It's called responses.txt, and there it is. You can add data to this and test it all you like. There is no test case right now with a 0, so you might want to add that as well. And that's about it. You can find it in the section 19 workspace in the challenge_2 project. There's also a challenge_2_solution project, which is the one we're going to talk about in the next video, where I'll show you my solution. So have fun. Add fields to it if you like. Change the length of the answers. Right now, the quiz is only 5 questions. You can change that around if you like. Like I said, do the base challenge and then just have fun and learn from it. All right, so I'll see you in the next video, and I'll show you a solution. Welcome back to the Section 19 Challenge 2 solution. I hope you had fun doing that challenge. It was pretty nice, and it's got a lot of different ways that you can tweak it and extend it to make it your own. So I'm in the Section 19 workspace in the challenge_2_solution project. And I wrote some functions to solve this, but first I just want to go through the logic in the main so you can see that it's really dead simple, and the functions that I wrote make it even simpler. So let's just start here at the top and we'll walk through this. I've got an input file stream called infile. That's what I'm going to use to read the responses file. I've got a string for the answer key, and I've got a string for the student name and the student responses, and I'm going to read each iteration of the file read. Okay. Then I've got a running sum and a total number of students that we're going to use to calculate the average score. Okay, pretty simple. So let me scroll up just a little bit here. And here's my program pretty much. I'm opening the input file right here, responses.txt. Notice again that the .. is because I'm in CodeLite. If you're in another IDE, you'll probably have to do the same thing, or just use responses.txt. It's totally up to the IDE. If we can't open that file, we display problem opening file, and we're out of here just like before. And then the very first thing I'm going to do right here, I'm reading that first line in the file, right? Or the first string in the file, which is the answer key. That's it. I'm reading it from in file, storing it in an answer key. So that will be that A, B, C, D, E string. Then I'm going to print the header, which just displays student and score with a bunch of dashes underneath it. So that's a function that I'm using to print the header. And then I've got the logic of my loop right here. So I'm saying while read from in file the name and the response pair. If anything, and those two are strings that I declared up top, I just showed them to you a minute ago. If anything at all goes wrong here, if we hit under file, if we have a bad read, if we've got bad data, this will fail and I'm out of here. Okay. But if we don't, now we've got name and response contain the strings for example, Frank and Frank's response. We increment the total number of students because we need to do that to calculate the average. And then I'm going to call a function called process response. I'm going to pass into it the response and the answer key, and it's going to return an integer with the score. So it'll return 0, 1, 2, 3, 4, 5 in this case, because you can get them all wrong or you can get them all right, or everything in between. That's it. I add the score to my running sum of scores, and then I call print student. I'm going to call that each time. So I'm going to print the student's name. So right here, it'll say Frank, and Frank got a 5. Then I loop and I do it again. Okay, so I'm going to clear this screen real quick. Then at the very end, I just calculate the average. I'm going to be sure that I don't do a division by 0 error. So if the total number of students is not equal to 0, I'm going to do the division. And I'm doing the static cast that you guys have seen before here. So I need to make one of these a double. And at the end, I print the footer. And in order to print the footer, it doesn't know what the average score is, so I'm sending it to it. I close the file and I'm done. Okay, so you can see the logic is really straightforward, right? You can see here I'm opening the file, I'm making sure it's open, I'm closing the file down here, I'm reading from the file right here, and the rest, and here as well. And the rest is just the processing that I need to solve this specific problem. Okay, so now let's take a look at these methods. I'll scroll up a little bit. And let's start with the print header method. Pretty straightforward, right? Just a bunch of print statements to see out. And what I'm doing here is I'm displaying the student, I'm displaying the score, and I'm using the setW manipulator here on the left to just line them up nicely. I could have used constants for 15 and 5 and 20, but I chose not to. It was such a simple little program. And then I'm using setFill to display the little dashed line. That's it. I set fill back to space just in case somebody else needs it. I don't want to have them display dashes. The footer is passed in the average score, and it just displays the footer. Really, really straightforward again. Okay. Now, I probably should have used the set precision and set fixed 1 here, but I'm using it here. So it's persistent, but good practice is to put it in here as well, right about here. That way, if someone changed it and then this function got called, you'll set it the way you want it. And then the last one is the print student, where I pass in the student's name and the student's score, and I just display them, just like we've done before. So these are just these handy little functions. And the reason we're using these functions is so we don't clutter up our main. And this is just a lot of code, a lot of noise, really, because it's just all about, I mean, all I'm doing here is displaying student, displaying score. But you've got all this other stuff around it with the manipulators. I need to set widths, and I need to do left, and I need to do right, and precisions. And it just really clutters up the logic in the main. So you really want to extract that out and modularize it out into a function, get it out of the way, and out of sight, out of mind. It's abstraction. I just call footer whenever I need it and pass in an average. I just call print header, and that's it. Real simple. And then the last thing is that function that actually calculates the number right. So that's process response right here. So we're passing in the student's response, which was a string that could be like ABCXX or whatever it is, and the answer key, which in this case was ABCDE. And we're setting the score to 0. We're assuming they haven't gotten anything right. And all we're doing is we're looping 1 character at a time through that answer key. And we're comparing the answer key at I to the response of the student at I. If they're the same, we're bumping up the score. We're doing that throughout, so we're going to check this guy with this guy, and then this guy with this guy, and so forth. When we're done, we return the score. So that's it. That's the solution, or that's one solution. You may have your own solution. If you think it's cool, post it on the forum. And if we run this, that's what we get. Just what we expect. Students, Frank, Larry, Mo, Curly, and Michael, their scores, and then the average score, 3.6. And the nice thing about this solution, I think, is this right here. I mean, I'm looking at the code right here, which is really doing most of the work. Well, this first one as well, which is reading the key. So this piece of code right here, this is really what's doing it all. And when you read it, it's really, really easy to read. I'm reading the answer key. I'm printing the header. While I'm grabbing those pairs, I'm processing the response. I'm printing each student, and then I'm calculating the average and printing it in the footer. So looking at this, it's really easy to understand it, to debug it. And that's it. That's the challenge. I hope you had fun with it. I hope you extended it. And there's another challenge coming up right after this one. Welcome to the third challenge of the Section 19 part of the course. I'm in the Section 19 workspace in the challenge_3 project. And this is the project that I'm supplying to you. The challenge_3_solution project will have my solution, which I'll go over in the next video. This challenge is all about finding words in files. So the idea here is for you to ask the user to enter a word. And then you're going to search the text of the Romeo and Juliet play by Shakespeare to see how many times that word is found in the text. Okay. And I'm supplying the Romeo and Juliet text. You can see it right here. You can get this from shakespeare.mit.edu. And there's the entire play. It's a very long play, but you can see that there's all kinds of words in here. And what we want to do is we want to ask the user to enter a word. So for use an example, suppose we ask the user to enter the word and the user enters love. So in this case, I want to match any word that has love in it as a substring. So love will match, lovely will match, beloved will match, and so forth. Now you decide whether you want to be case sensitive or not. My solution is case sensitive. If you were going to do a case insensitive solution, you'd have to write a little extra code. But here's a few sample runs. Enter the substring to search for, the user enters love, and the results are 25,919 words were searched, and the substring love was found 171 times. Now you'll get a different result if the user typed in love with a capital L, of course, because my results are case sensitive. If the user enters Romeo with a capital R, we'll find it 132 times. Obviously, we're searching the same number of words every time. If they typed in Juliet with a capital J, it's going to find it 49 times. And unfortunately, my name's not in this place. So if you type in Frank with a capital F, it's found 0 times. Okay, so that's it. Now I'll give you a sample run of this. So what's the substring I want to search for? Well, let's search for Romeo lowercase. That shouldn't be in there. And you can see we found it 0 times. You can also see how quick this is. Let's run it one more time. And let's say I want to search for Romeo uppercase. In this case, it will be there because it's on a couple of the captions. Actually, a lot of times. We found it 208 times. So that's it. It's a pretty straightforward challenge. I'm giving you no hints here. You decide how to read this file, whether you want to read it a line at a time, a word at a time, a character at a time. It's up to you. And also how you're going to figure out that substring. Remember, at this point, we should be using modern C++. We shouldn't be using character arrays or character pointers. We should be using stood string objects, right? C++ string objects. So make sure you use those. That's it. Have fun. Post your solution if you like. It's actually pretty straightforward. The only tricky piece is finding that substring in the string. All right, so I'll see you on the other side with the solution. Hello, welcome back to the Challenge 3 solution for Section 19. I'm in the Section 19 workspace in the challenge_3_solution project. And this is the project where we try to find the word matches in the Romeo and Juliet play. So let me go over my solution, and I wrote a simple function to help me with the solution. And we'll talk about the function in just a second, but let's just go through the solution at the beginning here. Here's my main. I've got my input file stream right here called infile. Here's the word that I want to find. That's what the user is going to give us. Here's the word that I've read. So each time I loop through that file, I'm going to read a word. And then I've got the word count and match count, which are just counters that we're going to increase when we see a word and when we see a matching word. Okay, so that's it. That's the preamble there. And here's the good old recipe that we always adhere to, right? I want to open the file, Romeo and Juliet. If it's not open, I display an error and I leave. So let's get to the part of the program that's doing all the work here. So right here on line 29, I'm asking the user to enter the substring to search for. Suppose they enter love. I'm reading that in from standard input, and then I'm in my loop here. So while I want to read a word from infile, okay, so I'm going to stop at any white space. I'm using the extraction operator here. So I'm going to read a word into word read, and if it didn't fail and if it didn't give me an end of file, I've got a word. So I'm going to increment the word count because I've seen a word. And then I'm going to call a function, which I'm going to show you in a minute that I wrote called find_substring. And the idea here is I send into this function the word that I want to find and the word that was read from the file. And if this word happens to be a substring in that word, it's going to return true. When it returns true, I increment the match count. If it doesn't return true, I don't increment the match count and I just simply go back up and loop again. That's it. Pretty straightforward. When I'm done with the loop, I've hit the end of file. I simply display how many words were searched and how many times my matching word was found. Okay, that's it. So let's talk about that find substring function now, which I wrote up here. And here it is. This function, as I said, expects 2 parameters, 2 strings, and they're both const refs. In this case, what's the word to find? Okay, the word to find is what the user gave us, love, which is being passed into this. And what's the target? The target is the word that we just read from the file. So maybe we read the word lovely, or we read the word Romeo, or whatever word we read. Okay. So what we're going to do is we're going to use the find method in the string class, which says, hey, target, which is this guy, find that substring word to find within you and give me back the index of where you found it. I really don't care about the index. I just want to know if it was there or not. So if it returns stood string no position, that means that it was not in the word and I return false. Otherwise I return true. Like I said, I really don't care what position it's in. I just want to know whether the substring exists in that target or not. That's it. Really, really simple. Let's run this. And let's search for, again, let's search for Romeo. Actually, let's search for Juliet this time. Juliet. 49 times we found the word Juliet. All right, that's it. Now, suppose we're trying to debug this along the way. We really want to see what word was actually read from the file. So what we could do here, or even better, let's just see the words that match. We know the words that match right in this if statement right here, right? That's why we're incrementing match count. So what we could do is right in here, we could say stood C out, and we could display the word that we just matched, right? Which is the word that we read. So we could display word read, followed by a space, and no new lines. That way it'll just display them one after the other. So let's try running this again now. And let's look for the word love. There we go. Those are all the matches that we found. Lovers, love, love with a question mark, punctuation, love performing. You can see here, love song, dear loved. There you go. So it gives us a pretty good gauge as to the correctness of our program. Obviously, we would have to do some real testing and absolutely know ahead of time how many times this word exists. Let's try it again with a capital L with love. 4 times. Okay. So there you go. And let's see, how about Romeo? You can see Romeo was found 132 times, and it was found with a period at the end, a period at the end again, at the end of the sentence with question marks, Romeos with an apostrophe S. So that's it. That's the solution. If you came up with another solution, if you figured out a way to do it by reading a whole line at a time and then splitting up the words out of the line, that's a lot more work. But if you did that and you think it's cool, post it out there so we can all learn from one another. All right, so I hope you enjoyed this challenge. In the next video, we'll learn about output streams and writing to files. In this video, we'll talk about the steps needed to write output to text files using C++ streams. In the following slides, I'll talk about the main classes and methods that we can use to write to files, and then I'll go over a few examples in live code. The 2 classes I'll discuss for text file output are fstream and ofstream. We must always include fstream. Then we declare a stream object of either fstream or ofstream type. We then connect the stream object we just created to the file we want to write to in our file system. Once the file is connected and open, we can write to it. By default, C++ will create the file if it does not exist. And if it does exist, the contents of the file will be truncated or removed unless we state otherwise. We can write to files in binary or text mode, and we can use any of the stream manipulators that we've already learned about. Then when we're done processing the file, we must close the file. This is very important for output files since it flushes any buffers that may not have been written out to the file yet. It's pretty easy. In the next few slides, we'll discuss the details of opening a file for output, checking to make sure the file was opened correctly, writing to the file in different ways, and then closing the file. It's important to remember that by default, output files will be created if they don't exist. But we have to make sure that if we provide a path along with the file name, when we open the file, that path must exist. Otherwise, we'll get an error when creating the file. If the file already exists, then it will be overwritten or truncated unless we specify that we want to append to the contents of the existing file. Finally, we can write in text mode or in binary mode. In this section, we're only concentrating on text mode. So in this example, we're creating an object named outFile, and we're using the fstream class as its type. Notice that I'm also initializing the object as well. The initializer takes 2 arguments. The first is the name of the file. As we've already seen with input files, this can be very operating system and IDE dependent. So in CodeLite, we're going to use .. so it puts the file in our parent directory. The second parameter specifies the mode and properties of the file that's being opened. In the first example, we're using std.ios_out. This means to open the file in output mode. So we're able to write to it but not read from it. By default, files are opened in text mode. In the second example, we're opening the file in output mode and in binary mode. This is necessary when we're writing non-text files that contain binary data. Notice the vertical bar or pipe character between std.ios_out and std.ios_binary. This is the bitwise OR operator, and when we use it in the context like this, it sets both output and binary modes to true. At this point, the file will be opened if it was found and truncated, or it will be created. In this slide, we use the fstream class. The fstream class can actually open a file for reading and writing at the same time. We won't be doing that, but if you have a file that you need to read from and write to, we can use the fstream class to do that. In this slide, we'll be using the ofstream class as the type of out file. ofstream is used commonly for output files only. We can create an ofstream object the same way we created an fstream object. However, in the case of an ofstream object, std.ios out is optional since it's already the default. So the first two declarations of out file have the same effect. There's another way to open the file that's commonly seen in code. We saw it with input files, so let's see those next. When we open a file for output, we have a few choices as to how we want to open the file. By default, the file is opened for truncation, and we can explicitly specify that as in the first example. If we want the output file open, but we want all further output to append to the end of the file, then we can use the std.ios app flag when we open the file. Finally, we can use the std.ios ate flag when we want to open a file that exists and we want to set the initial position of the next write to the end of the existing file. But we're free to move around using random access. We aren't going to use random access files in this course. We'll focus solely on text-based sequential files. Now, just as we saw with input files, we can first create the stream object and then open it. So let's see that. In this example, notice that we're creating out file as an ofstream object, but we haven't provided any file name to associate with it. This is a common use case since many times we don't know the file name and we have to get it from the user or from some other resource at runtime. Once we have the file name, we can then use the open method on the stream object to open the file. So we can say outfile.open and give it the file name, or outfile.open file name and any flags we need. Now that we attempted to create the output stream and connect it to a file, we have to be sure this was successful before we start writing to the file, and we'll do that next. The process here is exactly as it was with input file streams. We have to be sure that the file was opened successfully, so we can call the isOpen method on the file stream object we created. This returns a Boolean indicating whether the file is open for processing. If we get back true, we're good to go. If we get back false, some error occurred. If no error occurred, then we can go ahead and write to the file. Let's see another way that we can test to see if the file was opened successfully. In this case, we can simply test the stream object itself. If the stream object was not instantiated, then this will return false, and we can decide what to do next. Otherwise, it's good to go and we can proceed writing to the file. Once we finish writing to the file, we have to close it. This is a simple method called to the close method. With output files, this is very important since it flushes out any buffers that may not have been written out to file yet. Okay, so now we know how to open a file, check to make sure that it's open and close it. Now let's write to it. There are many ways to write to a file. In these examples, we're going to use text files. The most common way is to use formatted output using the stream insertion operator. So in this example, we have an integer, a double, and a string and 3 variables, and we want to write them out to our output file. We can assume that out file was created successfully. All we have to do is use the insertion operator as we've been using all along with cout, except that we insert the values into out file. That's it. Very simple, very powerful. Remember, the stream manipulators we learned about in the beginning of this section, we can use them all as well to format our output however we want. Also notice that endline flushes out any unwritten buffers. So let's write a program that copies one text file to another. We'll assume the existing file is myfile.txt, and we want to copy it to another file named copy.txt. First, we create an ifstream object in file and initialize it to our input file. Then we create an ofstream object out file and initialize it to our output file. In this case, if the output file does not exist, it will be created. If it does exist, it will be truncated. We need to be sure that both files were opened successfully, so we check using 2 if statements, and if there's any error, we terminate. In the next slide, we'll complete the program and actually do the copying. So at this point, our input file and output files are open and ready for processing. We can use a while loop with a get line to read the input file one line at a time into the string variable line. If the read was successful, the while loop condition will be true and we write the line to out file. Then we close both files. That's it. Really, really easy to copy one file to another. Okay, so let's see one more example. This time we'll use unformatted read and write, and then we'll see some examples in live code. In this example, again, we're using infile as an ifstream object and outfile as an ofstream object. We go through the same steps necessary to open the files, check to be sure they're open, and so forth. And then in the next slide, we'll do the actual copying, but this time in an unformatted manner, one character at a time. So here in the while loop, we read a character from infile using the get method. And if it's successful, we write that character to outfile using the put method. When we reach the end of file, the loop terminates and we close the files. That's it. So there you go. 2 different ways to copy text files. One that's doing it one line at a time, and another one that's doing it one character at a time using unformatted read and write. Great. So now let's head over to the IDE and we'll see some examples of creating and writing to text files. In this video, we'll write some code that will allow us to create some files, and we'll create some files a couple of different ways. First, we'll create a real simple file and just write a string to it. And then what we'll do is we'll write a couple of copy file utilities, just like we did in the slides. Okay, so I'm in the section 19 workspace in the write file project. And I've got nothing going on here except these includes. I'm including iostream, fstream, and string. Let's get started. First thing we need to do is let's create an ofstream object. So we'll call it std_ofstream, and we'll call it out file, since it's going to be an output file. And we'll initialize it to .. Again, I'm in CodeLite, that's why I'm doing this. And I'll name the file output.txt. Okay, now we'll check to see that it was opened correctly. So if not out file, then what we're going to say is just get out of here, right? Some error. So we'll provide an error saying error creating file, because it is an output file. And we'll return something other than 0. Let me get rid of that extra quote right here, and we'll return 1. That's it. So if we get now to this line 13, we know our file has been created in this case. Remember, if the file does not exist, it's going to be created. Right now it does not exist, so it will be created. If it does exist, it'll be truncated. Okay, so we'll lose whatever was in there before. So let's create a string variable. We'll just call it line. And we'll ask the user, we can call that variable name anything we want. We'll ask the user to enter something to write to the file. And we'll simply read it from, we'll use getLine to read it because we want to read more than just one word. So we'll say getLine from cin into line. Remember, again, we're using string objects here. We're not using C-style strings. That's it. So what do we do now? We say outfile, and we insert that line into that file, and we'll give it a new line as well. Remember, end line will flush out the buffer, and then we're done here. We'll just close the file. That's it. Pretty easy. Now, if we run this, let's do that. Enter something to write to the file. I'm going to say hello there file. I'll press enter. Program's done. I'll exit this. Now, there is nothing that shows up here by default. Some of the IDEs will show that file when it's created. CodeLite doesn't. So what you can do is you can select the project, right-click, and say Open Containing Folder. That'll open it up in Explorer or in Finder if you're on a Mac. And I'll just drag that over here. And you can see that it's right here. We just created the file name. Remember, let me drag this down just a little bit. The file name was output.txt. There's output.txt right here. And you can see the contents of it right over here. Hello there file. Okay, now let me move this out of the way and let's run this again. And if we run it again, I'll just say my name is Frank and press enter. And now if we look at the file again, I'll drag this back over. You can see that what was there before was erased because we're opening the file in truncation mode, so it gets rid of whatever was there. That's the default. Now, if we want to add something to the file, we can simply open it in append mode. So we can put another flag here, just say, we'll say std ios append mode or app. And if we run this again now, we say this should be another line. Okay, so we'll take a look at the file now, and you can see my name is Frank, and now I wrote this should be another line. Okay, so you can see that it's actually appending to the existing file. So that's it. That's pretty straightforward, and really that's the basics of output to text files. We have the power of all those stream manipulators, which really gives us a lot of power into how we format the output files. Okay, so what I want to do now is I want to switch to another project. It's going to be the copyfile_1 project. So I'll switch to that and I'll be right back. Okay, so I'm in the section 19 workspace and I've opened up now the copyfile_1 project. And in this project, what we've got is this poem. We've got Shakespeare's sonnet again. And what we want to do is we just want to copy it to another file. So what we can do is, I've already written the code and it's really, really straightforward. It's just like it was in the slides. What we can do is we can start here, and you can see we've got our includes that we need, and we've got an input file stream called infile, which is my poem. And then I've got an output file stream called outfile, which is my poem_out.txt. That's the file we want to create. That's going to be a copy of the poem.txt file. So again, we're basically following the recipe. We're instantiating those objects. We're making sure that our file streams are open and ready to read and write. And then we've got our logic, and our logic is really only just a couple of lines of code. We've got a line that we want to read the file input into, and there's my loop. I'm using getLine to read a line from infile. And when I get that line, all I'm going to do is write it to outfile. That's it. At the end, we're going to display a little message that says file copied, and we're going to close both files. So if we run this, it'll say file copied. That's it. You can see how quickly this runs. And we'll open up that project, the containing folder, and we should see a poem_out. There it is right here. That was just created, 1K big. And if I select it, you can see that the poem is over here. This is the original poem, and this is the copied poem. So it's exactly the same. So it's really easy to copy one file to another. In this case, we used formatted input and output because we're using getLine, and we're using the insertion operator with line to write it to the file. That's it. Now, if we go over to copyfile_2 project, let me open that up. It's exactly the same thing. The only difference here is that we're using get and put. So we're using unformatted input output. And you can see that the code is exactly the same except the while loop and the variable declaration right there. That's the only difference, is we're doing it one character at a time. So while we get a character from infile, we output that character to outfile. That's it. So let's run this. I'll select that, make sure that that project is selected. I'll run this. It's done. And I'll open up that project in the containing folder. And right here, you'll see poem.out. And it's right over here. You can see it right there. So that's it for this video. Here you can see a few examples of creating files, appending to files, and copying files using unformatted and formatted I/O. Next is the challenge. And in the challenge, what we're going to do is we're going to take Shakespeare's Romeo and Juliet and add line numbers to it and create a new file. I'll see you there. Welcome to the fourth and final challenge of section 19. I'm in the section 19 workspace in the challenge_4 project. We also have a challenge_4_solution project, which contains a solution. This challenge is pretty easy, but it's kind of fun. The idea is that we have the Romeo and Juliet play that we've used before. And what we want to do is we want to read that in, add line numbers to it, and then write it out to a new file. So we're not going to modify the original file. We're going to create a copy of the original file that has line numbers on it. Okay, so it's real nice, really easy to do, and it'll get you a little bit of experience writing more files. Let me run this for you. I'm going to run the solution and it shows no output. It just says copy complete because there's not much to show. But let's open up the enclosing folder here so we can see what's created. Now here you can see the original Romeo and Juliet. There's no line numbers here on the left. And this is the file that's created right here, Romeo and Juliet _out. You can name that anything you like. And you can see that that has line numbers now, nice and formatted. And you can see them all lining up right around the side. There are a lot of line numbers in this file, about 5,000 something, I believe. Now, there's one thing I don't like about this solution is, let me scroll, there you go. See, this solution gives line numbers to all these empty lines. I guess that's okay. It all depends on what you want a line number. So I'm doing it two ways. I'm doing it like this, and then I'll show you another way in a second, which gives only line numbers to lines that actually have text, okay? So let me run that solution in a second, and I'll show that one to you. Okay, so I'm gonna run this other version, and its copy is complete, and then we'll take a look at what it looks like. And right here, Romeo and Juliet _out, and you can see it looks exactly like the previous one, except that blank lines aren't numbered. So you can see that we're skipping those blank lines. We're still displaying them like they were in the original file, but we're not numbering them. And I think it looks a little easier to read this way. I mean, I don't know whether line numbers are put into scripts like this or not, but different option. It gives you two different solutions and you can experiment with that. I'll show you both solutions when we do the solution project in a little bit. So that's it. Have fun. Okay, so that's it for this video. I'll see you in the solution. Hello, welcome to the Section 19 Challenge 4 Solution video. I'm in the Section 19 workspace in the Challenge _4 Solution project. And here's the solution to this project. It's pretty straightforward. We're going to do it a couple different ways. Like I said, one, we'll put line numbers on every line, and then we'll modify it a little bit so that we're only putting line numbers on lines that actually have text. So we've got our includes. We're including IOStream, FStream, IOManip, and string. And we're creating our input stream right here, our input file, which is Romeo and Juliet.txt. And of course, it's in my parent directory because, again, I'm in CodeLite. I'm creating an output file stream where we're going to create a copy of this file with line numbers. And I just called it Romeo and Juliet _out.txt. I'm opening both files and I'm double checking that they're both open for reading and writing. If they're not, I provide an error just like we've seen before. Here I've got a line, which is a string. And I've got a counter for the line numbers, and I've initialized it to 0. Pretty simple. That's it. Now I'm going to start processing the file. I'm going to use getLine because I want to read a whole line at a time. I'm using getLine, and I'm reading a line from InFile. What I'm doing is, no matter what, if it's successful, I'm incrementing line number here, and I'm simply displaying line number left justified in a width of 7. That gives me a nice formatted area on the left side of the file that's got all the line numbers in there, and then line, which would also be left justified against that 8th position, basically. That's it. Then I display copy complete, close both files, and we're done. So if we run this, copy complete, we can go to our project and open up the folder. And we should have a Romeo and Juliet _out, which we do right here. I'll double click on that. And there you go. You can see everything's lined up nicely with line numbers on the left-hand side. Okay. Now, what I said earlier was this kind of bugs me. All these line numbers on these blank lines. So I don't want that. Let's just do another version of this program that gets rid of those. So that's what we'll do next. What we'll do is we need the logic right in here. Basically what we want to do is we want to do this only if the line is not empty, right? So let's put an if statement in here. We'll say if the line we just read is empty, then what do we want to do? Then we just want to write to the file. We still need to write the blank line to the file. So we'll just say in file, sorry, not in file, out file, and we'll write an end line. That's it. Then we'll have an else statement here, and we'll wrap all of this up inside that else, and we'll just indent it over. Okay, that's it. So now we're only displaying a new line. We're not displaying text because there is no text, right? We're not displaying a line number because we don't want to display a line number on an empty line. And if it is not an empty line, then we're going to treat it as normal. We're going to increment the line number and display it. So let's run that. And let's take a look at the output again. And that's pretty much what I wanted, right? All the blank lines are still displayed, but they are not numbered. And that's it. I hope your challenge was fun, and I hope you basically got the same kind of solution. There's a lot of different ways that you can modify this program. If you had any and want to share, please post on the forums. So that's it for this video. There are a couple videos left in this section. The next one is going to be about using string streams, which allows us to use our own in-memory strings as streams, which is pretty cool. And we will address input validation, which is a question that's come up a bunch of times in the forums. In this video, we'll talk about string streams. String streams allow us to use in-memory string objects as streams. That means that we can read and write data to strings in the same way that we can read and write data to any stream. This is a very powerful concept, and it's very useful for data validation. It's also very easy to use since we already know how to use streams. There are three classes that we can use when using string streams. The string stream class allows us to read and write from string streams. The iString stream class allows us to read from string streams, and the oStream class allows us to write to string streams. For all of these, we must include the sstream header file. The rest is very much like using any other stream. First, we declare a string stream object of one of the three types that I mentioned, then we connect it to a string. That's it. Now we can read or write to that string stream using formatted I/O and stream manipulators if we wish. Let's see an example of how we could read from a string stream. Suppose we have three variables declared, an integer named num, a double named total, and a string called name. Now suppose that we have string info with the string mo100 1234.5 as its contents. Remember we did this example in this section and that same data was in a file. Well, now it's in memory in a string. We can create an iString stream object, we'll call it ISS, and connect it to the info string. So now we can read from the string stream. Now we can use the stream extraction operator to extract those data from the string. That's pretty cool. I'm sure you can see lots of applications for this, especially in data validation. So now let's see how we can write data to a string stream. In this case, we've initialized our variables num, total, and name to 100, 1234.5, and mo respectively. We can create an oString stream object named OSS, and we can write to this stream object. In this case, I'm inserting the three values onto the string stream. Remember, we can use any stream manipulators to format that data that we're putting on the stream. So now how do we display the string that we just formatted? Notice that in this case, we didn't connect the oString stream to any string object. We could have, just like we did with the iString stream example in the previous slide. The string stream has a string buffer that it uses internally, and we can use that. So if we want to display that string, all we have to do is call the string streams.str method. In this last example, we'll do some basic data validation. The idea is that I want to ask the user to enter an integer. And I want to be sure that they do enter an integer and not some invalid data like a name. So we have a string named input, and we read the user's input into that string. We don't read it into an integer. Again, we read it into a string. Then what we want to do is to try to convert that string to an integer if possible. There are many ways to accomplish this in C++. Some are better than others. Let's do it with a string stream. It's pretty easy. What we can do is we can create a string stream object. We'll call it SS. And we can connect it to the input string that the user just entered. Then we can try to extract an integer from SS and store it in value. We can do that using the stream extraction operator. If the extraction was successful, that means that we have a valid integer stored in value. If the extraction was not successful, we know that the user didn't enter an integer, and we can ask them to enter the number again, or we can do whatever else makes sense in our program. So now let's head over to the IDE, and we'll see these examples, and we'll do a more complete data validation example as well. Okay, so I'm in the IDE. I'm in the section 19 workspace in the string stream project. And what we'll do here is we'll do a few examples using string streams. We'll read from them, we'll write from them, and then I'll show you a little bit better data validation example than the one in the slide, a little more complete. So what we're doing here is we've got some includes, and we're including limits, and I'll show you what that's about later. But right now we have IOStream, IOmanip, our SStream for our string streams, and the string class. Okay, so here's what we've got. We've got these three variables, just like we saw in the slides. Num is an int, total is a double, and name is a string. And we've created this string right here called info that just has those three pieces of data in there. It's all a string right now. But what we want to do is we want to be able to read that or extract that information from the string as a string, an integer, and a double, and store them into these variables right up here. Yeah. It's really easy to do. All we have to do is create an iString stream. We'll call it ISS, and we're going to hook it up to that string info, this guy right here. Okay. And now what we can do is we can extract information from ISS, which is a stream, the same way that we extracted information from CIN, the same way we extracted information from a file. Same idea. Remember, we're using the stream abstraction, and we really don't care what the stream is connected to. In this case, it's connected to an in-memory string. And that's what we're doing here. We're reading name, num, and total. The compiler knows the types for these guys because they're defined right up here. So it's going to try to read a string from the string ISS, which is connected to this guy right here, and it's going to grab mo and store it in name. Then it's going to get 100, store it in num, and it's going to get 123.4.5 and store it in total. We'll display this information out to the console right here with cout, and we'll get a nice formatted output. So let's see what it looks like. And there you go, mo 100 and 123.45. That's the data that was in this string. So you can see how easily what we were doing is actually parsing that string and parsing information out of there typed, which is kind of cool. And it was so easy to do. We really had to do very little. All we had to do is this one line, 17 right here, once we hooked up the string stream. Okay, so that's an example of input. Let me show you an example of output. I'll comment this piece of code out, or uncomment that, I should say. Notice what we're doing here. We're going to use an output string stream here, and we'll call it OSS. And we're not going to hook it up to anything. Behind the scenes, the string stream class has its own string buffer, and that's what we're going to use. So in this case, what we're doing is we're instantiating OSS right here, and then we're just going to write to the stream, and the stream is going to store that information in that string buffer that it has. So what we're going to do is we're going to display name, we're going to display num, and we're going to display total. We still have those from this piece of code up here. And we're going to display them using these stream manipulators. And then when we're done, we want to display the string, right? But all we have is that stream, OSS. I know string and stream sound alike. It's hard for me to say them because I confuse them myself. So all we have is a stream, OSS. It's connected to a string. So what we want to do is display the string. And the way we get to that string is we use the str method for the stream. And that will return that internal string buffer that it's got, and it'll display it. So what we're doing here is we're outputting all of this information to that stream, which is connected to its own string. And then we're displaying the string. So when we display the string, you should see this display in a formatted manner. So let's try that. There it is, mo 100, 123.45. It's the same formatting that we used right up here. Make sense? So what we're doing is we're displaying this. Remember, before it went to cout, now it's not going to cout. Now it's going to that string stream. They're both streams, right? Cout is an output stream, and OSS is an output stream. It just happens to go to a string. And now let's do an example for data validation. You guys had a lot of questions about data validations on the forums, so I decided to do an example using the string stream. All right, so let's go through this one really slowly here. This is the value. At the end of this, I want the user to enter an integer, and I want that integer to be in that value variable right here, okay? But I can't, you've seen how we can't just ask the user for an integer and then do something like cin. So we could read the console input into that value variable. That doesn't work real well, right? When they type strings and when they type silly stuff on the keyboard, it's going to fail. So we've got to have a better way to do that. We have to be able to validate the type that they're entering. So that's what we're going to do here. Rather than read directly into an integer, we're going to read into a string right here, entry. Okay, and we're going to do this in a loop, and we're going to keep doing it until they enter something that's valid. So let's talk about the loop. What we'll do first is we're going to create a Boolean flag right here called done. And we're going to set done to false because we're not done. We're done when we're done, right? And we're starting out. Obviously, we're not done when we first start. So we've got a do loop, a do while loop here. And what we're going to do first is we're going to say, hey, user, please enter an integer. And we're going to read the integer into entry. Remember, entry is that string. So now we're allowing them to enter anything they want, right? We're going to grab a string so they can type in numbers, letters, decimals, whatever they want. And what we'll do is we'll try to validate that to make sure that what they typed in is an integer. This is where the string stream comes in. And we're going to use an iString stream here. We could have just used a regular string stream. It doesn't really matter because it goes both ways. But this is an input string stream. And we're going to call it validator. Could have called it anything you want. Typically, you see these things called SS out there in real code. I don't know why, but it's very, very common to see string streams named SS. So I'll call it validator, and I'm hooking it up to entry. So now remember, entry is, suppose a user entered 1 instead of the number 1. They entered the string 1. What we're doing is we're hooking up this string, right? Entry right here to that validator string stream. And then this is the key right here. I'm going to try to extract value. What's value? An integer. I'm going to try to extract value from the stream. There's no way, right? We've got a string here that's O-N-E. That's not an integer. This will fail. If this fails, we're going to say, sorry, that's not an integer. Done is still false. And we're going to loop again. And I'll talk about this statement here in a second. But now, suppose that they do enter a valid integer. Suppose they enter 123. Remember, it's a string. They're entering strings, but that's a valid integer in that string. When we get to here and we try to extract that integer from that entry that they put in through the stream, we're going to get back 123, and that's going to be stored right in value. So that's going to be perfect. This will pass. We'll set done to true, and we're looping while we're not done, so we're done, right? Our loop will finish, and then I believe there's a statement down here at the bottom that says you entered the integer value. And I'll run this for you in a minute. Now let's talk about this statement right here. Okay. This is something I hadn't talked about yet, and these are the more advanced edge cases and nuances of C++. Suppose that the user entered something like 12.38. Okay. Well, this right here will extract the 12, and 12 will be put into value. But then we have all this stuff left over on the stream. So the next stream read doesn't really know that that's there. So what we're doing here is we're saying stood cn, and we're using cn here because that's where we're reading data from. We're going to ignore everything in that stream up to the new line. And that's what we're doing here. And that's where that limits header file comes in. So we're using stood numeric limits up to whatever the stood stream size is. And that's dependent on your platform. So however big that stream is, the maximum number, I'm getting rid of all of this stuff. I'm just ignoring all that. I'm clearing out that stream so that the next time I read from the stream, it's clean and there's nothing left over. Okay? Because remember, the user could have typed in 12, hello, there, right? And that space right there grabs that 12, and that 12 goes into value. This passes. This is true. So we've got an integer. They did type in an integer. They typed in a bunch of other stuff as well. But what we can do is we can grab the 12 and just delete that rest of that stuff so that the next time we read, we're clean. All right, so let's run this example. And please enter an integer, 12. You entered integer 12. Good, that was an integer. That's what we expected. So let's run this again. Please enter an integer. Let's say I typed in Frank. Sorry, that's not an integer. How about 0.01? Sorry, that's not an integer. But notice now that when I loop around, whatever was left in that input stream is gone because I ignored it. I got rid of it all. So that really helps us with future input. So now if I did something like 10 Frank is a good teacher. Something like that. You entered 10. Notice it grabbed the integer, but then it just discarded everything else. Right, so we're ready to read again, and our stream will be in a known state and not some unknown state. All right, so that's it. I hope you enjoyed this this section on string streams. They're very, very powerful. They're not used that often out there, but sometimes you'll see them used, and they're used a lot in GUI work sometimes when you want to display strings to GUI, graphical user interface elements. We tend to format them in memory and then display them out. That's it. So let me know if you have any questions about this. In this video, I'll go over some of the popular IDEs and where you should place the input files that you're going to read from. CodeLite I won't do because we've been using it throughout the course, but we've got Windows Visual Studio, CodeBlocks, CLion, and Xcode, and I'll do a really short video on all of them. It's the same little program that all it tries to do is open a file called test.txt, and what I found was that in CodeLite, we need to do a /test.text. In Windows Visual Studio, it's just a file name, and CodeBlocks is also just a file name. In CLion, just like in CodeLite, we need to go up a directory and then provide the name of the file. And Xcode is a little different, so please watch the video if you're using Xcode, and I'll show you how to set it up so that you can use input files. Okay, so first, let's start with Visual Studio. So in this example, I've got Visual Studio. And you can see when I run this sample, it says error opening file because the file doesn't exist. So what we want to do is create the file. So we can click the resource area and click add new item and then select text file and give it the name test.txt. It's lowercase, and press add. And at this point, that file has been added. We can go back to our C++ file and execute it at this point. And notice we're just using test.txt as the file name, and we should get good to go. There we go, good to go. So it's all set. So that's the way you would create an input file in Visual Studio. So now let's see how we can get this to work using the CodeBlocks IDE. For this example, I'm in the CodeBlocks IDE, and you can see I've got the same file here where I'm trying to open an input file stream named test.txt. It's not here right now, so if I try to run, it says problem opening file, just as we expect. So what we'll do is we'll come up here. So what we can do is we can come up here to, we can select our project and say file new, empty file. Do you want to add this new file to the active project? I'll save the project first. And all we're doing here is we're just creating that file, test.txt. And make sure that it's in the file test directory or whatever the project directory is. And we're basically where you see your CPP source file right here. I'll save. Then it's going to ask me to select the targets. That's important. Make sure those are checked. Select it. And at that point, you can see it creates this folder called Others with the test.txt in it. And now if we run this, we're good to go. Okay, so that's how you would create a file for input in CodeBlocks. Next up is CLion. Let's see how we can get the input files to read using CLion. I'm in the CLion IDE on Windows, and you can see I've got a real simple program that's going to test opening a file. The file name is test.txt. If I run this, I can just click that little green arrow right here, or I can click the green arrow up here. I'll just do it right here. You'll see that what we'll have is we'll have an error. It says problem opening file, just as we expect because the file doesn't exist. So I'm going to come up here to the project, right click and say new file. The file name would be test.txt. I'll save that and we'll try to run it again. And I'll click the CPP file again. Again, we're seeing a problem opening file. And if we look at the directory structure, you'll see the problem is that the exe file is being created in here. You can see it right here, file test exe. So it's a level up. So what you need to do is the same thing we did in CodeLite. We just basically say .. We'll save it. We'll run it again. And we're good to go. So that's how you would do this in CLion. And we'll finish up this section with Xcode. Xcode is a little bit different, so watch the video if you're using Xcode and you need to have input files. Okay, so I'm on a Mac running Xcode, and I've got that simple program here. I'm trying to open a file named text.txt. If I try to run this, I'll get an error down here saying problem opening file. So the file's not there, so let's add the file. So let's right click here, we'll say new file, and I'll select Mac OS and I'll scroll all the way down to the bottom till it says empty. And we'll create test.txt. That's it, so the file's there now. So if we run again, it still won't find it. We'll have a problem opening file. The way that Xcode works and Mac works is that exe file, that app, is stored in some derived data directory really far removed from the project. So the best way to do this on a Mac is to come up to Product, then select Scheme and Edit Scheme, and then look for this working directory right here. It's under Options on Run Debug. You select Working Directory, and you say Use a Custom Working Directory. And what we want to choose is we want to search and what you want to do is select the working directory where those files are, your main CPP and your test.txt, and you select it. We close this up now, and now if we run, we should be good to go. And we are, and it'll find the file just fine. Most of the other IDEs will also allow you to change the working directory, but it's much easier just to change the file path on those. But on a Mac, this is the best way to do it. Welcome to the Standard Template Library section of the course. In this section of the course, we'll learn about the C++ Standard Template Library, or STL for short. The STL provides a rich set of containers, iterators, and algorithms that we can use with just about any type of data we wish. We've already worked with one of the STL workhorses, the vector. First, we'll see what the STL is all about, and then we'll learn a little bit about generic or metaprogramming, which is what the STL uses to allow us to use its components on just about any type of data. We'll see how C++ can use preprocessor macros, function templates, and class templates to achieve generic programming. We'll also learn what generic programming is and why it's so powerful. Then we'll look at the types of containers, iterators, and algorithms provided by the STL. And we'll look at each of the main containers, such as array, vector, dec, list, set, map, stacks, queues, and priority queues. Finally, we'll learn about some of the commonly used algorithms in the STL. The cool thing about the STL is that once you learn how to use one container, one iterator, and one algorithm, then the rest follows the same pattern, so they become easy to learn. There will also be several challenges in this section that will allow you to solve more problems using the STL containers, iterators, and algorithms. Most beginning C++ courses don't cover the STL, but I think it's important to cover it since it's used very often in C++ programming. Great, so let's see what the STL is all about. In this video, I'd like to do an overview of the basic elements of the C++ Standard Template Library and see what it's all about. The STL is a library of powerful, reusable, adaptable, generic classes and functions. Okay, so what do all those words mean? Well, the STL is powerful. We've already seen a bit of that power when we used the vector class. The STL is reusable. Remember when we created vectors of integers and doubles and accounts and so forth? We didn't have to do anything except tell the vector what we wanted it to hold. The STL is adaptable. It provides containers, iterators, and algorithms that we can adapt to make them do whatever we need them to do with our programs. Finally, the STL is implemented using template functions and classes. We'll learn about C++ templates in the next few videos. They're one of the features that make C++ so powerful. The STL is a huge class library. We'll only be scratching the surface in this section, but once you understand how to use the STL, the principles we'll learn will apply across the entire STL. The STL was developed around 1994 by Alexander Stepanov, and even today it's considered one of the best designed generic class libraries ever created. So what is the STL? Well, at its core, the STL is an assortment of commonly used containers. We'll see some of these containers in the next slide. The algorithms provided by the STL have published and well understood time and size complexity information. That means that when you use the containers and algorithms in the STL, there are no surprises. You know exactly how the algorithms behave as the size of the collection increases. Complexity theory is beyond the scope of this course, but it's an important part of software development. The STL has been around a long time. It's been tried and tested across many millions of lines of code. The STL is consistent, fast, type-safe, as well as extensible. The STL has three main components: containers, algorithms, and iterators. Containers are collections of objects or primitive types. These include array, vector, dec, stack, set, map, and more. Algorithms are functions for processing sequence of elements from containers. The STL has about 60 algorithms that can be used and extended to work with any type of data. These algorithms allow us to find a specific element in a container, find the max or min element in a container, count the number of elements in a container, accumulate or sum up the values of container elements, sort containers, and that's just a few examples. We can do much, much more. Finally, iterators generate the sequences of elements from the containers that the algorithms use. There are several types of iterators that allow us to generate sequences of elements in various ways. Note that one of the beautiful aspects of the design of the STL is that the containers, algorithms, and iterators are designed totally independently from one another, yet they work together seamlessly. Also note that I said the STL has three main components. It also has a few other components such as functors and allocators, but we won't be covering those in this section. Before we get into the details of the STL, let's see a simple example of how we could use some of its functionality. We'll use a vector of integers for these examples since we're already familiar with vectors. In this example, I'm including the vector and algorithm header files. Vector allows me to work with vectors, and algorithm allows me to use the STL algorithms. So let's create a simple vector of integers. We'll call it v and initialize it to three integers, 1, 5, and 3. Now, suppose we want to sort that vector. We can use the STL sort algorithm to do that, but the sort algorithm needs a sequence of objects to sort. That's where the iterator comes in. We provide the sequence using v.begin and v.end. This provides the sort algorithm with the integers in the vector v from the beginning element to the ending element. In other words, the entire vector. That's it. Now we can display the vector using a range-based for loop, and we can see the elements in the vector are now sorted. Pretty easy, right? The iterator we used produced a sequence of all the integers in the vector, but we could have easily provided only a subset if that's what we needed. So suppose we had a need to only sort the first half of a vector. We could modify the iterator to produce just the first half of the elements. Also, we aren't restricted to using a vector. We can sort just about any STL container exactly the same way. Also, we can extend the sort algorithm to tell it exactly how to compare the elements when sorting. For example, maybe we have a vector of account objects and we want to sort them by balance. Suppose that now we want to reverse the order of the integers in this vector. We can use the STL reverse algorithm to do that. The code is exactly the same, but we use the reverse function instead of sort. And when we display the vector's elements, we get 5, 3, 1 as we expect. Also, I should mention that behind the scenes, the range-based for loop is itself an iterator. We'll talk more about that later. Now let's see a different type of algorithm function, the accumulate function. In this case, I want to add up all the integers in the vector and store the result in a variable called sum. To do this, I can use the accumulate function. Notice that the function has parameters. The first two are iterators. Where do I start? Where do I end? This produces the sequence of elements that the accumulate function will process. The third parameter, 0 in this case, is what the running sum will start at. Typically 0, but we can use any number we want. The type of this third parameter is very important. So if you want to sum integers, use 0. If you want to sum doubles, use 0.0. The total is stored in sum, and in this case we display 9, which is 1 plus 3 plus 5, the sum of the elements in the vector. From these simple examples, you can see how powerful using containers, iterators, and algorithms can be. Now let's talk about the various types of containers provided by the STL. We have three basic categories of containers: sequence, associative, and container adapters. Sequence containers are containers that maintain the ordering of inserted elements. These containers include array, vector, list, forward list, and dec. We'll discuss each of these containers in this section of the course. Associative containers insert elements in a predefined order or no order at all. For example, a set is a collection of elements where there are no duplicates, but there may be an order associated with it or not. We've got the option to choose whatever one we want. A map is like a dictionary where we associate a word with its definition. There are many variants of this category. So we can have ordered sets, unordered sets, sets that allow duplicates, maps that allow duplicates, and so forth. These are very powerful data structures that are often underused. We'll talk about them in this section, and I'll show you how to use them. The last category, container adapters, are variations of the other containers. This category does not support iterators, so they can't be used with STL algorithms, but they're so commonly used in programming that the STL provides support for them. These include the stack, the queue, and the priority queue. In this slide, you can see that the STL has several types of iterators. Input iterators make container elements available to your program. Output iterators can iterate over a sequence and write an element to a container. Forward iterators can iterate forward over a sequence and can read or write any element. Bidirectional iterators are like forward iterators, but they can iterate over a sequence in both directions. And finally, random access iterators can use the subscript operator to directly access elements. We saw that with the vector class. Finally, we have the STL algorithms. As I mentioned previously, there are about 60 algorithms in the STL. And the algorithms are classified into two major groups: non-modifying and modifying algorithms, depending on whether the algorithm modifies the sequence it acts upon. As you can see, there's a lot to the STL, and we can't possibly cover it all in detail in a single section. In fact, entire books have been written about the STL. But by the time you get to the end of this section, you'll understand the fundamentals of the STL and be able to use STL containers, iterators, and algorithms to solve real problems. But before we get to the STL, let's talk a little bit about generic programming and templates so that we can understand the design behind the STL. According to Bjarne Stroustrup, the inventor of C++, generic programming is, quote, writing code that works with a variety of types as arguments, as long as those argument types meet the specific syntax and semantic requirements, end quote. So why is generic programming such a big deal? Well, it's because if I have code that's written to be generic, then I should be able to use any types with that code as long as it makes sense and it should work. We'll see this specific example later, but what if I wanted to have a function that took some number as a parameter and returned the square of that number? With generic programming, I should be able to pass in any numeric type into that function, and it will return the correct result. So it should work with ints, short ints, longs, long longs, floats, doubles, and so forth. You get the idea. But we have a bit of a problem. The C++ compiler is statically typed, so it needs to know the type being passed into that function, so it can type check it. So if I write the function to expect an integer, then I won't be able to call it correctly with a double. So how can we get this to work in C++? There's a couple of ways. In this video, we'll look at macros. And in the next several videos, we'll learn about function and class templates. Notice the note on the macros bullet. Be very careful when you use macros in practice, especially macros that use arguments. So why am I showing it to you then? Well, sometimes the best way to teach how to do something correctly is to first teach how to do it in a way that's inferior. Second, you'll likely see this out there in production code. There's a ton of legacy C++ code out there, and macros are used in much of that code. Macros are used more extensively in C code though, and we sometimes see C code used with C++ code. Now we've actually already used a macro. Remember when we created the include guards around our .h header files, we used #define? Well, that's a macro. In the context of header guards and conditional compilation, it's okay to use macros, but don't use macros in your code as I'll show you here. Okay, so let's see how these macros work. First, the macros begin with a pound sign, and we know that all directives that begin with a pound sign are preprocessor directives. And what else do we know? Well, we know that the preprocessor doesn't know C++. So there is no type information associated with macros. The preprocessor is just doing simple substitution. Notice the first pound define defines the name max size to be 100. Notice that the 100 has no type associated with it. It's just 100. The second pound define defines the name pi to be 3.14159. Now, if we use these names in our program, the preprocessor will replace the names with what we defined them to represent. Notice that there's no semicolon at the end of the macros. If there was, then the semicolon would also be copied, and that's not usually what we want. In this slide, we can see max size being used in the expression in the if statement, and pi is being used in a calculation. The preprocessor will first remove the pound defined statements from our code. Then it goes through the program and replaces any defined names with what we defined them to be. You can see the values being replaced here in the if statement and in the calculation. Now the processed file is sent to the compiler. It looks simple, and it is, but there's a better way to do this, and we learned it a long time ago. We used constants. Constants are typed, and they're known to the compiler. I know what you're thinking. What does this have to do with generic programming? I'll show you in the next slide. Suppose we want to write a function that expects 2 integers and returns the maximum of those 2 integers. We could easily write that max function as you can see in this slide. Note that we're using the conditional operator. So it evaluates A greater than B, and if it's true, then A is returned, otherwise B is returned. Simple if-else logic. Now we can define 2 ints, x and y, call the max function with x and y as parameters, and it works perfectly. Okay, so what? Where's the generic programming? Now, suppose we need a max function for doubles and another one for characters. And we could have another one for floats and longs. You get the idea. We could end up writing many of these max functions. The code is the same for all of them. It's that code with the conditional operator. The only thing that changes is the types of the parameters. Remember the idea behind generic programming. I should be able to use max with any types as long as they make sense. But how can I do that without writing many versions of this function like we did here? Well, one way is to use macros with parameters. In this slide, we're defining a macro named max that expects 2 arguments, A and B. And we can define it to be the conditional expression we saw earlier. So when the preprocessor sees max with 2 arguments, it will replace it with what we defined it in the macro. And it will also replace the arguments A and B. So now we have no functions defined, just a single macro called max. We can now use max in our code with arguments as you see in the examples. It works fine. That's an example of generic programming. Remember, the preprocessor is simply substituting. It doesn't know C++, so problems can occur once the compiler tries to compile the processed code. We have to be very careful with macros. Here's an example. Suppose we want a simple macro that's defined as pound defined square with a single argument A, and it's defined as A times A. Looks simple, and it is, but there's a few problems here. Now we can use that macro in result equals square with a 5. Square 5 will be replaced with 5 times 5, and all is good. But look at the next example. Result equals 100 divided by square 5. What we expect is 100 divided by 25, which is 4. But that's not what we get. We get 100 divided by 5 times 5. Again, blind substitution. So how can we make this better? When we use macros, we can wrap up all the arguments in parentheses. This is the best practice. Now we give ourselves a better chance that the result will be correct. In this case, we now get what we expect. Okay, so why don't we want to do this? Because the compiler isn't doing it. The preprocessor is doing it, and it doesn't know the syntax or semantics of C++. Don't use macros with arguments in your code. If you have legacy code, understand how it works so that you can better test the code. So what's a better way to write these max and square functions so that we can use generic programming and let the compiler do the work? We can use templates. In this case, function templates, and we'll learn about them in the next video. We've seen how we can attempt to write generic functions using preprocessor macros. In this video, we'll see how we can use C++ templates to accomplish writing generic functions. So what is a C++ template? A template is a generic blueprint that the compiler uses to generate specialized functions and classes. As I just said, C++ supports function and class templates. In this video, we'll learn about function templates, and we'll see class templates in the next video. The idea with templates is that we define a template with a placeholder type, and then we plug in the actual type we want when we need it. Then the compiler generates the specific function or class that we need. Remember, all of this happens at compile time. If you're coming from other programming languages, you might be used to this happening at runtime. C++ does it at compile time, so we get the benefit of the compiler performing type checking for us before the program executes. C++ template supports the concept of generic programming or metaprogramming, since we're providing a generic representation of a function or class, and then the compiler writes the actual function or class for us. That's very, very powerful. However, with power comes complexity. C++ templates can be very, very complex, and while the concept is easy to understand, seeing them in practice can sometimes be very intimidating, even for experienced programmers. Also, the error messages provided by the compiler can be very difficult to understand. So let's see how we can use function templates with the max function that we used in the previous video. Let's quickly review. We want to write a max function that returns the maximum of 2 integers passed into it. We can use a simple conditional expression which, if you recall, is equivalent to an if-else statement. Now we can simply use the max function and pass in integers and get back the max of those integers. Now suppose we need a max function for doubles and another for characters. And we could have another one for floats and longs, you get the idea. We could end up writing many of these max functions. Just as we saw in the previous lecture, the code is the same for all of them. It's the code with the conditional operator. The only thing that changes are the types of the parameters. So now let's see how we can use templates to allow us to write just one blueprint for this function. Why don't we simply replace the type with an identifier that represents any type? In this case, we'll use the uppercase T, but we can use any valid identifier we wish. So that's it. That was easy. That's what we want, right? Yes, indeed. But the compiler won't know what to do with this, and it's going to give us a compiler error. We need to explicitly tell the compiler that this is a template function. So let's do that in the next slide. Notice that now we provide the compiler with the line template and type name T in angle brackets. That's the template parameter type. This tells the compiler that T is the type name that will be replaced with whatever the user needs. Now this will compile, but it will not generate any code. Let me say that again. This will not generate any code. It's simply a template or a blueprint. Code is not generated by the compiler until the user uses a specialized version of the template. I'll show you how to do that in a second. But first, I want you to know that we can use the reserved word type name or class in templates. They are essentially equivalent. I will use type name in this course, but you'll see both type name and class in production code, so please be aware of that. Okay, so now how do we use this template function? Notice the code in this slide. We declare 2 integers a and b and initialize them. Then we call max with a and b as parameters. But also notice the template parameter we're using. That's the int in angle brackets. This gives the compiler all the information it needs to actually generate a specialized function from the template we created, using int in place of t. The syntax should look familiar. We used it previously when we created vectors and smart pointers. You guessed it, vectors, unique pointers, shared pointers, and so forth are implemented as template classes. Now suppose we need a max function for doubles. Easy, we simply use max and pass in 2 doubles, say C and D. and use the template parameter double in the angle brackets. The compiler now knows that it needs to generate the double version of the max function. Often, the compiler can deduce the type of the template parameter, and we don't even need to provide it as in the second statement. How cool is that? That makes it even easier. And we don't have to stop with doubles. If we need to compare two characters and return the max character, we can simply use the template function max with chars, and the compiler will generate the character version of the max function. We can use almost any type we need. Notice I said almost. What do I mean by almost any type? Well, let's take a closer look at the function again, and you'll see what I mean. Notice that the code in the template function is using the greater than operator to compare A and B. This means that whatever type we use for T must support this operator. For primitive types like ints and chars and doubles, it's not a problem. But for our own class types, we have to be sure that our class overloads the greater than operator, or this won't compile. In this example, we're assuming we have a player class, and we're using max with player objects. So the compiler will generate the max function that expects and compares player objects. Unless the player class overloads the greater than operator, this code won't compile. There is no limit to the number of template parameters you can have, and of course they can be of different types. In this example, we're creating a function template for a function named func. It expects two parameters. The first is of type T1, and the second is of type T2. Notice that we specified two template parameters in this case. So there's the function declaration. Now let's see how we would use it. We can call func and explicitly provide an integer and a double in this example. Or in the case of the call to func with no template parameters, the compiler will deduce the types from the function arguments. That's it. Now, of course, we can pass by value, by reference, by pointer, with const modifiers, and so forth. And all of the function parameters don't have to be generic. You can see all the possibilities and combinations. Now, let's head over to the IDE and we'll write a few template functions. Okay, so I'm in the section 20 workspace in the function templates project. And what I'd like to do here is go over those two templates that we created in the slides, and I'll show you how they work with integers, with doubles, with characters, basically with primitive types where there are no issues with overloading operators. Then what we'll do is we'll create our own type. We'll call it person or something like that. And then you'll see some of the issues that we have to address to get that person class, or structure in this case, to work with these templates. And then what we'll do is we'll create a swap template function at the end. All right, so let's go over what we've got here. Now, if you recall, we've got a function called min, and it's a template function, right? So there's my template parameter t. And basically, if you write this with ints instead of t's, it's really, really easy. And all you need to do is just replace it with the generic type t. The compiler will take care of the rest. So it's going to be an A of type t, a B of type t is what it expects, and it's going to return a type t. And all we're doing is comparing using less than. Now, here's where the issue is. If we're using integers here, then assuming A and B are integers, then the less than works great, right? We know how to compare integers and doubles and characters and so forth. But when we use our own types, that's where the issue comes in. And I'll talk about that in a second. But first, let's just look at a real simple example of using it, and then we'll look at this template function right here next. Remember, at this point, the compiler's done nothing for us. It hasn't, all it's done is made sure that this is valid, but it has not created an integer version of this or a double version of this. Nothing gets created. It's just a blueprint right now. So what we've got here is, right here on line 18, you can see that I'm calling min, and I'm using the template parameter int, and then I'm passing in two integers. At this point, the compiler now sees this blueprint and generates the integer version of it. So t would be int now, right? So this whole template stuff gets taken away, and we just get a function that, just like we wrote in the slides, with just plain integers. So in this case, I expect that result to be a 2 because that's the minimum. Now, you'll also notice right here on line 19 that I'm not providing this template parameter right here. You can see it's just min 2, 3. The compiler is smart enough to deduce that these are integers, so it's going to create the integer version of it. A lot of times the compiler will figure it out. Other times the compiler won't figure it out, depending on how complex the template function is. So in this case, it can figure it out. So all I need to do is just call min pass in a 2 and a 3, and I'll get a 2, just like before. Now here you can see I'm calling min with 2 characters, A and B. In this case, they're literals. It doesn't really matter. They're all literals in these examples, but it doesn't really matter if they're literals or variables. It'll all work the same. The compiler will now see, 2 characters here, so it will deduce that this template parameter right here is a character, and it will generate the character version of that template function. And we'll get an A right here when we display it. Same thing with one with the doubles here, 12.5, 9.2. A double version of the function will get created by the compiler. And in the very end here, we've got integers, but this is a real difference between the template functions and macros. We don't have to worry about precedence or anything here. We just do what we need to do. We want 5 plus 4. We don't have to worry about C-style macros like we did before with the pound define in the previous video. This is going to work correctly because the compiler knows C++. So that's it. If we run this, we should get what we expect. So let me build and run. And here are my results right here. Let me just scroll a little bit up right here. And that's just what we expected, a 2, an A, a 9.2, and a 9. What we'll do now is we'll create our own structure. Now, this can be it could be a class, but I'm just going to create a structure so I don't have to worry about private and public, but it'll work exactly the same way with a class. So right here, I'm going to create a structure, and I'm going to call it person. And I'm just going to say that every person has a name, which is a string, a C++ string, and an age. That's it. There's my person. Let me spell struct correctly. It's a structure, so now I can create person objects, right? So let's do that. I'm going to do it up here, right about here. And I'm going to say person P1. And remember, I've got a string right here, name, and I've got an age. So my first person will be Curly. And let's say that Curly's 50 years old. And my second person is Mo, and Mo is 30 years old. And it keeps giving me that Curly. I'll get rid of that. Okay, so now I've got 2 person objects. So what I want now is I want the minimum of those 2, right? I want to be able to use my min function that I wrote to be generic, so it should expect any type that makes sense. Well, here, it doesn't quite make sense yet, but it will in a minute, because what I want to do is I want to compare their ages. So let's just say person P3 is the minimum of P1 and P2. In other words, the one with the least age. Now, if we try to compile this, we're going to get an error. And the error, if you can see down here, it says error no match for operator less than for the operand types person. So you can see that the compiler has generated that specialized function for the persons, but now it can't compile it because it doesn't know how to compare 2 persons using that less than. Okay, so what do? Well, we tell the compiler how to do that. So what we'll do is we'll simply write a real simple overloaded operator. Remember, they return Boolean. The operator is operator less than. That's the one that's causing the problem. And what does it expect? Well, remember, this is a member. So we're going to say const person ref right-hand side. Hopefully you guys remember this part of the course. And it's const because I really don't want to modify anything here. And all I'm doing here is I'm just saying I want to return this person's age. Is it less than the other person's age? That's it. So if I run this now, now we've got a clean run, right? We just need to display the result, which we haven't done yet. So I want to do that right here. And I'll just say something like std cout. And I'll just say p3.name is younger. That's it. So if we run this at this point, we should see Mo, right? We should say Mo is younger. So let's run that. There we go. Mo is younger. So let's change this around now. Let's say that Curly's 15 and Mo is 30. Now we should say Curly is younger. And that's exactly what's going on. Okay, so that's pretty cool. I'm able to use persons and integers and doubles and all kinds of stuff, right? And in this case, I'm really explicitly saying that I'm interested in comparing ages here. Okay, so now let's look at this second example right here. And this is the one where we're using 2 template parameters. We're here on line 11. Our function is called func. It expects 2 parameters, an A and a B. A is of type T1, B is of type T2. They can be the same or they can be different. And all we're doing is just displaying A and B. That's it. Real simple. So let's take a look at our main example down here. There's a bunch of test cases here, but you can see in this case, I'm explicitly providing the template parameters in that first example right here. And you can see that I've got 2 ints and I'm supplying those 2 ints. So we just expect this, all this function does is display what's passed into it. So it'll display 10 and 20. Then we can do the same thing, but in this case, the compiler is deducing the types. Notice I'm not providing them explicitly. Here I'm providing a character and a double explicitly. Here I'm just letting the compiler deduce it. And again, here's an integer, here's a C string, here's an integer, here's a C++ string. So I'm passing all kinds of stuff into this function, and the compiler is going to generate the correct one for me, which is really cool. So if I run this, you can see down here, we're getting a 10 and a 20 and a 10 and a 20 again, and the A and the 12.4, twice I'm getting that. And then I'm seeing 1,000 in testing and 2,000 in frank. Exactly what we expected. Okay, so now let me scroll up here just before line 31 right here. And what I'd like to do here is let's call func with a person or 2 persons. It doesn't really matter. Remember, it's expecting 2 different types or 2 types that are the same. So let's do that. Let's call func with P1 and P2. Now, when we try to compile here, we're going to have a problem. It says error no match for the insertion operator that expects a stream. And if I come over here just a little bit, and a person. What's the problem? Well, the problem is that in this case, A is a person and there is no overloaded insertion operator for a person. So that won't work. So what we want to do is we want to add the overloaded insertion operator. And we could do that really easily. We could do it right here. We don't need a friend function here because this is all, it's a structure, so everything's public. So what we can do is we could just say std ostream, remember this? And we're returning an ostream reference. And what we're going to do here is it's operator. And we're doing the insertion operator. The left-hand side is the stream. And we don't want to do that const because we want to change it. Now the right-hand side is the person. So in this case, it's a const person reference. And we just call it P. So what do we want to put on the stream? Well, we could just say OS and let's say P's name. That makes it really easy. And we want to return the stream. That's it. We run this now. Now we get curly and mo. Notice they're both printing out right here. That's exactly what we wanted. So this is one of the things that'll get you when you're first starting out with template functions is, yeah, I can supply any kind of type to it, sure. But a lot of times when you're using operators, you've got to really be careful with those operators to make sure that they work correctly. Overload them if you have to. Okay, so now the last thing I want to do is let's create our another template function, and we'll write it right down here, right before the main. And what we'll do is we'll just call it my swap. And I just want to swap 2 elements, right? So how would we do this with an int? I would say something like int, oh, sorry, I would do something like void, and we'll call it my swap. It expects 2 integers. Now we want to change them, so we really want them by reference. And here's the second one. And then in here, all we're doing is assigning a temporary, right? So we have an int temp equals A, then A equals B, and then B equals temp, right? Simple swap. Simple logic. That'll work. That'll swap 2 integers. But we don't just want to swap integers. We want to swap anything. So what we can do here is we can come to this int, we can replace it with a T, replace this guy with a T, and replace that guy with a T. And remember, that could be any letter. I'm just using T. So now we'll tell the compiler that this is a template function and its type name is T. That's it. Now we've got a template function called mySwap. That's pretty cool. Now I'll do it up here, so we'll see that as the first output. And what we can do here is we could just say int x is 100, int y is 200, and we can swap them, right? So that's x and y. If we displayed x and y, we'd obviously get 100 and 200. But now we can call mySwap, and we can pass in x and y. And at this point, what I want to do is just display x and y. So I'll copy that in here real quick. That's it. So it's going to display X and Y. What I expect now is 200, 100, right? Actually, you know what? Let me put this before and after the swap. That way it'll be really, really obvious what's going on. That's it right here. So if I run this now, you can see 100, 200 at the top, and then 200, 100, which swapped them. Now, the cool thing about that, I can write this with strings, characters, all kinds of good stuff, right? And I'll leave that to you guys to play because this video is getting a little bit long. Try replacing some of these with your own types and playing around with it. You'll see it's not so bad. Once you understand the basics of template functions, you'll see how powerful they are. But remember, there's those little gotchas. If you get those errors, they're typically about operators that the compiler can't resolve. So it's your job to resolve them. Okay, so that's it for template functions. In the next video, we'll start talking about template classes. We've seen how we can write generic functions using C++ templates. In this video, we'll take it a step further, and we'll learn how we can use C++ templates to create generic classes. So what is a C++ class template? A class template is similar to a function template, but instead of creating a generic function, we'll be creating a generic class. So this implies generic attributes, constructors, destructors, methods, and so forth. Just like we can plug in any type to a function template, we can do the same with a class template. We've already used class templates in several places in this course. The most obvious is when we created vector objects. We didn't just say, I want a vector. We said, I want a vector of a specific type. And that's where the class templates come in. So the class template is a generic blueprint that the compiler uses to create specialized classes. That's what metaprogramming is all about. As I mentioned in the previous slides, templates can be very complex. Class templates in particular can be very complex. Imagine combining inheritance, dynamic polymorphism, operator overloading, templates, and other advanced C++ features together. Super powerful, but also complex. So let's see how we can use class templates. Let's say we want a class that will hold an integer and a string, and we want that class to be called item. We can write a simple class as follows. Note that we have two private attributes, name and value, a constructor that initializes those attributes to those provided by the user, and we have a getName and getValue getter methods. Of course, we could add other methods, but we won't in this example, since the purpose is to focus on how we can make this class generic. So let's suppose that now we need a class that's similar to the item class, except instead of an int and a string, we want to model a double and a string. What can we do? Sure, we can create a new class just like we did for item that has a double and a string. But we'd have to name it something other than item since we can't overload class names in the same namespace. And we don't want to create a complex hierarchy with dynamic polymorphism. So let's see how we can use class templates to allow us to just write the blueprint for the class. First, we can replace the type of the value attribute from int to t in this case. But remember, this can be any name. Then we go through the class, and wherever we used value or return values type, we replace it with a t. That's pretty much it. Now, of course, this won't compile. We need to tell the compiler that this is a template class. And we can do this by adding the template declaration before the class declaration and provide the template parameter. This is a pretty simple example, but it sure makes the item class much more generic and much more useful. Now, if we want to create instances of items, we can simply provide the type of the value in the template parameter, and the compiler will take care of generating the correct class from the template. In the first example, we're creating item 1 as an item with a value of type int and a name of type string. Name will always be of type string, so we don't have to provide it as the template parameter. In the second example, value will be of type double. In the third example, value will be a stood string. And in the final example, we're creating a vector that holds items, and those items will have value as an integer. That's it. Just as with function templates, there's no limit to the number of template parameters you can have, and of course, they may be of different types. In this example, we're creating a class template called myPair that models a pair of data items. The types of these data items can be different if we wish, or they can be the same. Note that in this case, we use a struct, since all we want to do is associate first with second. We're just modeling data, so we won't bother with constructors, methods, and so forth. Now, if we wanted to create myPair objects, it's really easy. In the first example, we create P1 as a myPair of std string and integer, and we initialize it to frank and 100. In the second example, we create P2 as a myPair of integer and double, and we initialize it to 124 and 13.6. And in the last example, we create a vector that holds myPair objects, and those objects are int double pairs. This myPair class can be a very handy class, since it can associate any two pieces of data of any type. In fact, it's so useful that it's already defined for us in std_pair. We need to include the utility header file, and then we can use the std_pair class, which is implemented very much like the way we implemented myPair. In addition to the pair template class, C++ also has a template class named tuple. It allows you to have a fixed number of elements of any type. It's not just limited to 2 items like the pair class. Okay, so let's head over to the IDE and we'll see these class templates, and we'll also implement our own template-based array class. Okay, so I'm in the IDE, I'm in the section 20 workspace, and I'm in the class templates project. In this project, what I'd like to do is go over those 2 templates that we talked about in the slides, and then we'll switch to this other project up here, class template array, and we'll implement an array class based on a template. Okay, so first things first, I put a little note here that's important. Template classes are typically completely contained in header files. So we would have the template class in item.h, and I'm talking about this template class that I'm going to talk about right here. And there would be no item.cpp file associated with it. Now that makes sense because what we have is a blueprint. The compiler is not compiling this blueprint. It's basically using it to create a specialized version of it that will be compiled. So it's important. If you start putting stuff in CPP files, you're going to run into all kinds of issues. There are ways to get it to work, but they're beyond the scope of this course. So for this course, put all your template classes in their own .h file. Let's talk about this template class. This is the one that we did in the slides, and we'll do this one first, and then we'll do this smaller one down here second. So what have I got here? I've got a template class. I know it's a class right here. It's not a function. It's called item. And here's my template parameter right here, t. So what do I know about this? Well, I know I've got a class called item, and it's got 2 private attributes. One is a string called name, and one is a value of type t. That's what's going to be replaced or plugged in. I've got a constructor here that just constructs it based on my name and my value that are being passed in. I've got a get name and I've got a get value. And notice the get value returns a t. So that's pretty straightforward, I think. And now let's look at this second template down here. This is the pair template that we created. And we're going to use a struct here instead of a class. But that's, again, it's perfectly fine. We're only modeling data in this case. So we've got this template parameter list right here, where we've got a T1 and a T2, and they could be the same or they could be different. So all we're doing is we're saying the first item here, in other words, this is just a name, an attribute name. First is the T1, second is a T2. So all we're really doing is associating 2 data types and calling it myPair. Okay, just like we did in the slides. So let me go down to the main and I'll show you some examples of this, and I'll walk through these one at a time. So first thing, on line 30 right here, I'm creating an item1 object, and it's of type item. That's my class. Value is going to be an integer. So remember, I have a string and I have a value. In this case, I always have a string first, and then this guy right here, that's going to be the t. That can be replaced with any type I want. So in this case, item1 will look something like this. Item1 is an object. It has a name attribute, and it's got a value attribute. The name is always going to be a string, and in this case, it's going to be Frank. And the value, that's our template parameter. That can be any type I pass into this, right? That's what I'm doing right here. So in this case, it's going to be an integer, and it's going to be 100. So that's kind of what's going on. So when I display item1 get name, I'm getting this guy right here, and that's going to display Frank. And then when I say item1 get value, it's going to get the 100. here. Okay, so that's that example. Let's take a look at this one here on line 33. And we'll run these in just a bit. So here I'm creating, again, an item 2. That's my object name. And it's an item, but look at my template parameter here. I'm saying the second one is a string. So what that will look like is, now I've got item 2. It has a name. It also has a value. In this case, they're both going to be strings. The first one will be Frank. That's my name. And value will be professor. Now, in the output statement, item 2 get name will get Frank right here. And item 2 get value will get professor, and that's what will be displayed, Frank professor. Now, this one here is a little more complicated, and I did this one on purpose just so you can see how you can build these things up, because sometimes you'll see these defined this way. Now, let's walk through this one really slowly. Item 3 is my object. So let me write that down right here. This is item 3. And we know that item 3 is an item. Okay, so it's going to have a name, and it's going to have a value. But what are we saying that the value is? Well, in this case, the value is another item. But that other item has a string as the value. Makes sense? So this value here, well, let's see, name is Frank. Let's get rid of that one first. Let's do that one really easily here. And I'm using my initializer right here to do it. And now my value is going to be an item. And that item has a name and a value. Okay, so you can see that I'm just building them up. I'm nesting one within the other. So in this case, the name will be C++, and the value will be professor in this case. All right, so now when I say item 3, get name, I'm getting this guy right here. That's item 3's name. In order to get to these guys in here, I've got to go through the value. So in this case, I'm saying item 3, get the value. Now I've got this item. And then I'm saying get the name. So now I've got C++. And over here, I'm just saying item 3, get value. That takes me to the value. That is an item. Remember that I'm going to get the value from the value, which is going to be professor in this case. So when I print this out, I should get Frank 100, Frank professor, Frank C++ professor. All right, so let me clear the screen and we'll give it a run. And what we've got here is we've got Frank 100, Frank professor, Frank C++ professor. Just what we expected. Okay, so let me make a little bit more room here. And now what I'm going to do is I'm simply going to take some items and create a vector of those items. So in this case, I'm creating a vector, and that vector is going to hold item objects. And in this case, the values will all be doubles. Remember, the names are always strings, but in this case, the values will be doubles. And I'm just going to push back 3 of them. So I'm going to say Larry 100.0, Mo 200.0, and Curly 300.0. I'm creating items here, and I'm pushing those items on the vector. And then all I'm doing is looping through the vector with a range-based for loop right here. So for each item in that vector, get its name, get its value. That's it. Now that's pretty cool because I'm doing all of this using a template class. So if we run this, we should see Larry 100, Mo 200, and Curly 300. So let's give that a run. And there you go. Larry is 100, Mo is 200, and Curly is 300. Just what we expected. Okay, so now let's look at the pair. That's this last piece right here. So I'll uncomment that out, and we will run this now, and you can see what's happening here. I'm creating my pair, and my pair is going to associate a pair of types, right? In this case, a string and an integer. There's the string, there's the integer. Here I'm associating an integer and a double. There's the integer, there's the double. This guy is called P1, this guy is called P2. And if I want to display those values, all I have to say is P1.first. To display the second, I would just say P1.second. And that will display Frank 100. Then for P2, we could do the same. P2 first, P2 second will display 124 and the 13.6. So let's give this one a run. And you can see down here, we've got Frank 100, 124, 13.6. So this gives you an idea of using 2 pretty simple template classes that we've created. Now I'm going to pause this for a second and I'll be right back, and I'm going to jump right into this class template array project. And what we'll do there is we'll create another class template for an array. In this video, I'd like to implement a class template for an array class. Now this is going to be a little bit more complicated than anything we've done before, but I'm sure you'll be able to follow along if you've been following along with the course. I'm in the section 20 workspace, and I'm in the class template array project. Now I've started this a little bit already, and the idea here is we'd like to create an array class. Okay, not an array, a raw array, and not a dynamic array, just a class array. And eventually, we want it to be of any size and of any type. That'd be pretty cool. And we want this to be a fixed size array. And basically, it would be a replacement for using a raw array. C++ already has this for us. In C++11, we have an array class in the standard template library. And I'll talk about that in a couple of videos. But let's see how we could implement the beginnings of that so we can really learn from it. So we want to have an array of something, right? Well, in this case, let's just stick to integers. And then later on, what we'll do is we'll make this generic. The array is a fixed size, and that fixed size is n. And I've got this n right here. None of this will compile yet, but I just want to get this the point across here. The question is, how do we get this n? Well, the user knows how big the array needs to be. Let's say it's 10 integers or 20 integers or 100 integers. They could pass that in through a constructor argument, right? The problem with that is that the compiler needs to know what the value of n is right here in order to create this array. Now, we're not doing something like using a pointer and creating a new array of integers like we did before. We're not doing that. That's not what I want to do. I want to create it on the stack. So the compiler needs to know the value of that n. And it can't know that if we pass it in through a constructor argument, because it could be a variable, it could be any value. So one of the first things we want to do is figure out how to do this. So I want to be able to create an array class. And let me show you the way I want to do it. I want to do something like this. I want to be able to say, give me an array. Let's say it's ARR. Right now it's an array of integers by default. You can see right here. And I'll just do that. Now that's not good enough because there's no size information. But if I can do something like that, that's pretty cool. So I can pass in the size of the array as a template parameter. Well, how do we do that? Everything we've seen so far has been type parameters, right? Well, it's possible to have non-type template parameters. And let me show you how that works. And basically, what we're doing here is we just have a regular array class. It's got a constructor, a default constructor. It's got a constructor with an initial value. So what we're doing here is just setting all the values of the array to that value. I've got a method called fill, which will just change all those array elements to whatever value is passed in here. Then I've got a couple of more methods that I'll talk about in a little bit. So first thing first, let's make this array class a template class. So what we can do is we can come up here and we could say template. And now we've got our template parameters here, right? Now, what do we do here? We're not passing in a type. We'll do that later when we make this a generic type. But what we want here is the size of the array. So we can supply n right here. Now, when I use the syntax that I used earlier, I've got my n. Now, that's pretty cool. So that's how we get the n. The user provides the n at compile time. Now the compiler can actually create that array. Now we've got a friend function here that's just used to display the array. And in this case here, it needs to know what that n is. So I'm just going to put an n right in here. So it needs that template parameter. Now, as I come down here, none of this code really needs to be changed. There might be a couple of new things that you haven't seen before. This one here, I don't know if we ever overloaded the subscript operator, but we're doing it right here. And it's the subscript operator, right? The two square brackets, so that we can use it as array indexing. And all we're doing is returning a reference so that we're able to change it as well. So now let's go down to the main and see how we can actually use this. And here's a couple of examples. Now we'll write the rest of this in a little bit, but take a look at how useful this array is. Here I'm creating an array of 5 integers. These are all integers right now, right? I haven't made it generic yet. But here I have an array of 5 integers, and I can display what's the array size. It should display 5. And then it'll display the integers because I've overloaded the insertion operator. I can fill the array to zeros. I can fill it to tens and display it again. And this is where the overloaded subscript operator comes in. So I can specifically set, and remember what's going to happen here is it's going to call nums dot operator subscript operator, and it's going to pass in 0 in this case. So that's what's being called. And I'm just setting those values in this case. If this is on the left side, we're using the L value. If it's on the right side, we'll be using the R value. That's it. And here in this case here, we're actually using an initializer. We're initializing 100 integers. All right, so let me run this so you can see the output. And this is all we did, and it's so powerful. All we really did was pass in that integer n as a non-type template parameter. So you can see what's happening. Here I've got 5 integers, and that array is called nums. And notice when I display it, I get 5 pieces of garbage right here. Right? That's exactly what we'd expect. Now here I'm filling it to 0, and then I'm displaying it again, and I'm getting this output right here, all the bunch of zeros. Then I'm filling it to tens, and you can see them display right here. And then in this case, I'm setting num sub 0 to 1,000 and num sub 3 to 2,000. And you can see right in this line when I display it, you can see that num sub 0 is here and num sub 3 is right here. Okay, so let me scroll just a little bit down. And this last example, we're creating 100 integers. Remember, they're all integers. So we're creating 100 integers. This right here is that template parameter n. This right up there, when we created the top one, was the template parameter n. So in this case, we're creating an array of 100 integers. It's a fixed size array. We're not doing any memory allocation. It's happening on the stack, which is pretty cool. The compiler's handling the sizing, and we're initializing all of those elements to 1. We're displaying them all right here. There's 100 of them. Okay, so that's it. Now we've got a pretty powerful little array class here that allows us to create an array of any size, but only of integers. So let's take this to the next step and make it totally generic, which is really where we want to go. So let me close this window down up here. And a couple of things. I'll scroll all the way to the top so I can give you these little notes here. Since C++11, the STL has been around before C++11, but in C++11, we have stood array. And this is an array with a lowercase a here. And I'll explain what that array is in a couple of videos from now when we go over some of these container classes. This is a template-based array class. The idea here is in modern C++, we really shouldn't be using arrays, raw arrays. We should be using stood arrays and stood vectors. Now, the vector is great, right? But the vector can shrink and it can grow and it varies in size depending on what you need. That's one of the great things about the vector. You don't have to worry about that. But sometimes you know exactly what you have. You know that you have 10 integers, or you have 20 integers, or 5 strings. And the vector might be overkill and it could be a little less efficient. In a case like that, you really want to use stood array. It's much more efficient. It's not going to shrink. It's not going to grow. It's exactly that fixed size. And sometimes that's exactly what we need. If we've got 12 months in the year, that's not going to grow, right? So it's a good example of using a stood array. Now, let's make this template class generic. So what do we have to do? It's really all about this guy right here. It's not about size. Size is always going to be an integer. Probably be even better if we made that a size t type, since it's going to be an unsigned, but we'll just leave it an int for now. Values is the one that's going to change. It's not just going to be integers. It could be anything. So that's where we want to replace our placeholder, right? Our type name t. So we'll do that right now. So let's start right here in the template parameter right here, and we'll say type name, and we can use t again. We can use anything we want. Now that's going to be what's going to be replaced by whatever type the user wants, right? So let's walk through this and make sure we get them all. This is fine. This guy is going to be a t because now we've got values is an array that's n size of t types, okay? Here, we've got 2 template parameters, so we need to supply t comma n. And this is just my friend operator that allows me to display these things on an output stream real easily. So that should take care of that. Now let's take a look down here. We've got the initial value that we want to set the array elements to. That can no longer be an int because it could be anything. So we want that to be a t. Here, the same idea. We want to fill the array with whatever t's are provided to us. Remember, the t is just a pluggable type. Could be an int, a double, a character, or something more complicated. Get size is okay. It's going to return an integer. But this guy right here, our overloaded subscript operator, is not going to return an integer reference. It's going to return a reference to a t. Okay? Now, this won't compile any longer. Let me compile it just so you can see what's going on. We're going to get errors right here. Why? Because look at our template definition right here. It's expecting two items. It's expecting a type and it's expecting an integer. But right now we're only providing the integer here. So we need to provide the type. So we could say int, comma, and then the 5. And now we've got exactly what we did before, right? So let's try that again. Same here. We've got 100, but let's try integers. And we'll modify this to a different type in just a second. That's it. Now, if I run this, I've got a clean run. It looks like I didn't do much, but there's a lot going on here because in this case, the compiler is providing two template classes for me, right? One is using integers with 5 and one is using integers with 100. So now what we can do is we can modify this. Let's say we want to modify it so that we can hold stood strings and not just integers. So we're going to create an array, provide the type, which is going to be stood string. And how many do we want? Let's say we want 10 of them. That's it. You can really see the power of templates here. So now what do we do? Let's call this guy strings and let's give it an initial value. We'll call that constructor with the initial value. And what we'll do is we'll just say stood string and we'll construct a string. Let's just call it Frank. Makes it easy. That's it. And then I'm going to just copy and paste this right here and rename a few variables so that we know now that the size of strings now, not nums, that's my array right here that I just named, is strings.getSize. And what we want to do is display it. That's it. Let's run this. There it is. The size of strings is 10. And now I've got 10 stood strings in there. Pretty cool, right? I mean, I didn't really do much. All I did was make this class generic. That's awesome. Now, suppose I want to change that first string, right? The 0th index. So I could simply say strings sub 0 equals, and we'll create a stood string. I can't use a character pointer literal right here because the typing would be wrong. So I'm going to create a stood string for, let's say, Larry. And that is going to be put in for the 0th item. And then I'll just display them again. And we should be able to see that first item in that strings array should now be Larry. So let me run that real quick. And there it is. You can see it right there as Larry. That's pretty cool, right? All right, last thing is let's fill this array with some X's, let's say. So we'll say strings.fill. And again, I want to fill this with a stood string. And let's just say X. And we'll display it one more time. Now we should see all X's when it displays. And there they are right down here. So that really finishes this video up in this little mini section about templates, including function templates and class templates. You can see the power here, right? It's so powerful. Now, obviously, let me scroll up real here. Obviously, you would never do this right here. I mean, we're just doing this to learn. If you need an array, use stood array. It's part of the STL. Everything's baked into it. It supports algorithms and iterators and all kinds of good stuff that we'll talk about soon. So again, if you need a fixed size array in modern C++, use stood array. So the next video, we'll start talking about containers, iterators, algorithms, and then we'll look at each one of the containers. In other words, array, vector, lists, sets, and maps and everything. And we'll go through some examples for those. In this video, I'd like to go over some of the basics of the standard template library containers. We won't go over the details of specific containers in this video. We'll get to that soon enough. Instead, it's important to understand what the containers have to offer as far as functionality is concerned, and understand what types of elements we can store in them. First, we know that the STL containers are data structures that can store almost any type of object, and they're implemented as template-based classes. Each container has a set of member functions that we can use. Some of these member functions are specific to a particular container, but there are quite a few member functions that all containers implement. We'll go over a table with some of these methods in the next few slides. Finally, each container has an associated header file that must be included in order to use the container. We've already seen this with vector and string. I'll tell you what the specific header files are for each container class we go over. Okay, so let's take a look at some of the common methods provided by the STL containers. This table and the table in the next slide show some of the functionality provided by the STL containers. Let's start with the default constructor. All containers provide default constructors, and it results in an empty container. They also provide many versions of overloaded constructors that allow you to initialize the containers in many ways. You have to refer to the specific container you want to use to see the various overloaded constructors. Containers also provide copy and move constructors, so we can create a new container based on an existing container. We can choose to copy it or move it. Of course, containers provide destructors. The container destructors clean up the container and delete all the objects in it. Containers also provide copy and move assignment. This, of course, will allow you to copy or move an existing container into another existing container. Remember, this is not initialization. And containers provide the last three methods in the table, which are used very often. Size returns the number of elements in the container. Empty returns true or false depending on whether the container is empty or not. And the insert method allows us to insert an element into a container. In this table, we can see that we also have the ability to compare two containers. We can test to see if the elements of one container are less than the elements of a second container. And we can also test for less than or equal to, greater than, and greater than or equal to. We can also check to see if the contents of two containers are the same or not using the equality operators. We have the swap function, which swaps two containers. And we can remove one or all elements from a container using erase and clear. And finally, we can get iterators to elements in containers. Not all containers support all these iterators, but I listed them anyway so you could see them here. We'll talk about iterators in more detail in the next video, so don't worry, you'll learn about them in a few minutes. This last slide is super important. Now that we know a little bit more about the functionality provided by containers, let's talk about what types of objects we can store in containers. First, we can store all of the primitive types in containers: int, float, double, all of them. But what about our objects? It's important to remember that when we store an element in a container, the container makes a copy of that element. So we must be sure that our objects are copyable and assignable. This means they must have default copy constructors or our own copy constructors, as well as copy assignment. We can also provide move semantics for efficiency. Finally, the ordered associative containers must be able to compare objects. They do this using the less than and the equality operators. So your objects must support these operators via operator overloading. Okay, I hope you can see that everything we've learned and done in this course comes together right here. We now know exactly what we have to do to make our own objects work with the STL. And you know what? It's not that complicated. In most cases, we can use all of the compiler-provided functionality, unless we have raw pointers. And we already learned how to handle classes with raw pointers. Well, that completes this video. In the next video, we'll learn about iterators, which give us something to do with these containers. I'll see you there. In this video, I'd like to go over the basics of iterators in the standard template library. Iterators allow us to think of a container as a sequence of elements. It doesn't matter what the container is. For example, we might have a vector or a set or a map. They're all very different containers, but iterators allow us to process sequence of elements from these containers without worrying or even needing to know about how the container is implemented behind the scenes. That gives us so much power. Iterators are implemented as template classes, so we create iterator objects and use them to iterate through our containers. The syntax we use with iterators will remind you of pointers. We can use the dereference operator, the increment and decrement operators, and so forth. This was done intentionally. C++ programmers are comfortable with the pointer syntax, and it's very easy to learn how to use iterators without having to learn some other arbitrary syntax. Most of the STL containers can be traversed with iterators. There are a few exceptions, such as a stack and a queue, and we'll see them later. So what do iterators look like and how do we use them? An iterator must be declared based on the type of container type that it will iterate over. So if I have a vector of integers, then my iterator must know that when I create it. The syntax is very straightforward. We provide the container type, the scope resolution operator, the iterator type, and then the name of our iterator object. That sounds complicated, I know, but it's not. Let's see some examples and you'll see. In the following declarations, I'm declaring 4 iterator objects. The first, it1, is an iterator that will iterate over a vector of integers. It can only be used on vectors of integers. The second, it2, can iterate over a list of strings. A list is a container in the STL, which we'll see later in this section. The third, it3, can iterate over a map of string-string pairs. Maps are like dictionaries. We'll also see them in this section. Finally, it4 is an iterator that can iterate over sets of characters. As you can see, we must be very specific when declaring iterators. Now let's look at an example using a vector so we can see how to initialize iterators. In this example, we've created a vector of integers named vec and initialized it to 1, 2, and 3. Remember, a vector is a container in the STL that stores elements in contiguous memory and can resize itself to accommodate elements dynamically. How this is implemented in the STL doesn't really matter to us. What we do need to know is that a container has a beginning and an end. The STL defines the beginning as the first element in the container, in this case the 1. And the STL defines the end as 1 after the last element in the container. This is very important and it's consistent throughout the STL. The end is not the last element, it's 1 after the last element. Almost all of the STL containers have begin and end methods. When we call these methods, they return an iterator object that's pointing to either the first element in the container or 1 past the last element in the container. In this case, vec.begin will return an iterator that's pointing to the element 1, and vec.end will return an iterator pointing 1 past the element 3 in this case. When we write code, we use vec.end as the sentinel so that we know when we're at the end of the list. Now, suppose we have a set. A set may or may not be implemented in contiguous memory. It doesn't matter, and that's the point. We don't need to know. If we want to iterate over a set of characters named suits in this case, we know that suits.begin will return an iterator to the first element in the set, and suits.end will return an iterator 1 past the last element in the set. We can use this information to initialize our iterators. For example, we can declare an iterator named it that will iterate over a vector of integers and then initialize it to point to the first element in that vector. We do that by calling vec.begin. In this case, it will point to the element 1 in the vector. If the vector had been empty, then it would point to vec.end. Now, the syntax can get long when we do this, so we can use auto to let the compiler deduce the type of the iterator. This is really handy and it's used very often. So the compiler deduces the type of it as an iterator to a vector of integers based on the result returned by vec.begin. This is much more readable and much more writable and easier to debug. There are a bunch of operations that we can use on iterators. Most will feel very similar to using pointers. In this table, we have a few of the most commonly used operations for iterators. The first column is the operation, the second column explains what it does, and the third column shows what type of iterator supports the operation. In this table, we'll assume that it is an iterator and I is an integer. Notice the first 2 iterator operations, pre-increment and post-increment. When we increment an iterator, we're asking it to point to the next element in the container. How's that determined? It's up to the container we're using. The third operation is assigning one iterator to another. Of course, the types of the iterators must be the same. These 3 operations are supported by all iterators. The fourth operator is the dereference operator. Just like when we dereference a pointer, when we dereference an iterator, we get the element in the container that it's pointing to. And we can also use the arrow operator when we're pointing to objects and we want to access their attributes and methods. Both input and output iterators support this, and we're able to read and write elements to containers. For the rest of the operators, you can pause the video and look at them on your own. Notice that we have ways to compare iterators, and we can also decrement operators. Some containers support bidirectional iterators, which means that we can move forward and backwards through the container. Others support random access iterators, like arrays and vectors. So how can we use these operators to work with iterators? Here's a really simple but common example. First, we declare vec as a vector of integers and we'll initialize it to 1, 2, and 3. What we want to do is use an iterator to iterate over the vector and display the contents of the vector. So we declare our iterator it as an iterator over a vector of integers, and we initialize it to the first element of vec by calling vec.begin. Now we simply iterate through the vector while it is not equal to vec.end. And at each iteration, we display the element the iterator is pointing to by dereferencing the iterator. Then we move to the next element by incrementing the iterator. That's it. Simple as pie. I know what you're thinking. Why not just use a range-based for loop or a counter-controlled for loop? We absolutely could, and we often do. We'll see in a bit that a range-based for loop is converted to an iterator-based loop behind the scenes by the compiler. But the real answer is that in the case of a vector, we could do it a lot of different ways. But other containers don't allow us to randomly access elements like a vector does. So for those containers, iterators are necessary. We can achieve the same result with a for loop instead of a while loop. Here we declare it using auto. This makes the code much more readable. We start at vec.begin, we loop while it is not equal to vec.end, and we display the element by dereferencing the iterator. Then we increment the iterator and do it all over again. This is exactly how range-based for loops work. In fact, sometimes we might mess up the code in a range-based for loop that iterates over a container, and the compiler gives us an error message saying that something is wrong with the iterator. This error is really confusing to beginning students, but no more. If you ever get an error like that, you'll know exactly what's going on. Now let's iterate over a set of characters using an iterator. Here we define suits to be a set of characters, and we initialize it to the character chsd. We can also declare our iterator it as auto and let the compiler deduce its type based on the result of suits.begin. Then we loop while it is not equal to suits.end and display the character. Increment the iterator and loop again. The pattern should look familiar. Finally, let's wrap up these slides by looking at a reverse iterator. A reverse iterator is exactly what you would expect. It works in reverse. So the last element is the first and the first is the last. And when we increment the iterator, we move backwards through the container in reverse. When we decrement the iterator, we move forward. Here's the same example with vec as a vector of the three integers 1, 2, and 3. We then declare it as a reverse iterator and initialize it to vec.begin. Since it's a reverse iterator, it will be pointing to the last element in the list, not the first. Now we can write code as we did before, and this will display the vector elements in reverse, 3, 2, 1 in this case. In addition to the reverse iterator, there's a few variants that are const iterators that are read-only iterators. Let's take a look at those really quickly. So in this slide, we'll wrap up the iterators by learning about the const iterators. These are methods in the appropriate container class that return specific types of iterators. You can see that we used begin and end for regular iterators. We can also use cbegin and cend for const iterators. rbegin and rend for reverse iterators, as we saw in the previous slide, and crbegin and crend for const reverse iterators. Okay, so that's a basic introduction to the STL iterators. There's much more to learn, but this foundation will let you use iterators with containers and algorithms and solve a bunch of problems. So let's head over to the IDE and I'll go over some of these simple iterators in live code. In this video, I'd like to go over some live examples of how to use iterators. There'll be a bunch of examples here, and I'll go through them one at a time so that you can really understand what's going on. I'm in the Section 20 workspace in the Iterators project. And first things first, you'll notice that I'm including a bunch of header files here. Vector, set, map, and list. These are all containers in the STL. We haven't really talked about set, map, and list too much, but that's the whole point. We really don't need to know that much about them to be able to iterate through them. We'll talk about them in detail in future videos. So the first thing we'll do is we'll have a couple of functions, and here's a function that we're going to use, and we're not going to use it too much, but if we ever need to display a vector of integers, we're going to call this function. It's just going to display it in a nice little format. Okay, so I'm going to close that up. And that way you know what it is. So here's my first function. And what I did was I broke this up into, I think, 5 different functions. That way it's all more self-contained rather than having one just huge main with all the examples in it. So in this case, let's walk through this. We're creating a vector right here of integers called nums1. And we're putting 1, 2, 3, 4, and 5 into that vector. So this is where we're at right now. 1, 2, 3, 4, and 5. And remember, the end of the vector is after the last element. So we want to create an iterator now. And that's what I'm doing right here. I'm using IT. And notice I'm using auto. I'm letting the compiler deduce the type of the iterator. Obviously, it's going to be an iterator that iterates over vectors of integers, right? That's the idea here. So I'm going to call nums1.begin. That's going to give me the iterator to that first element and assign it to IT. So IT is here. And it's going to be pointing there. Now remember, this is not a real pointer. This is an object, okay? But the syntax and the way it feels is very pointer-like, and that's by design. So that's pointing to the 1. In order to get to the 1, I need to dereference that iterator right there. And what that's going to do is it's going to give me the 1, the object in the container. And in this case, I'm going to display it. Okay, so it's as simple as that. Now what I want to do is move this iterator. So I'm incrementing the iterator right here, and I'm incrementing it by 1. So what's going to happen? The iterator now will be pointing to 2. What do? We're displaying it again. So I'm going to display a 2. Now you'll notice what's happening in the next line. I'm saying iterator plus equals 2. So I'm incrementing the iterator by 2. It was at 2, so I'm going to go 1, 2. Now it's going to be pointing to the element number 4. What do? Display it. Now I'm going to move it right back down by 2. So I'm going to move it back to the 2. And display that. And then the last thing I'll do is I'll set the iterator to point to the element that's not at the end. Remember, there is no element at the end. The end just means you're at the end of the list. But I want to go 1 back from it. So I really want to point to the end of the list, the 5 in this case. So what we're doing is, in this case, we're going over here, and then we're backing up 1. So that. So if I run this test function right here, that should be the output, 1, 2, 4, 2, 5. And what's interesting here is you can see how these iterators feel just like pointers, right? And that's real handy. I'm using the auto here. It saves a lot of, makes it a lot easier to read. I'll use it in some places. I won't use it in others. That way you can actually see both styles. So that's it. If I run this program now, let me go down to my main and make sure that I'm calling test1. I am right there. So if I run this now, what I've got is, I should get 1, 2, 4, 2, 5, exactly like we thought. So that's test 1. So let me collapse this guy and we'll move on to test 2. And I'll go down to my main and I'll just make sure that I comment out test 1 and uncomment out test 2. Perfect. So now let's take a look at test 2 and see what's going on in there. So here's test 2. We're doing the same thing. We're creating a vector of integers and initializing it from 1 to 5. So we've got 1, 2, 3, 4, 5. And here is the end right here. I'm creating another iterator. I'm calling it IT again. This time I'm doing it long style. I'm not using auto. And you can see it's really pretty straightforward. It's just a lot of extra typing. So we're creating a std vector of integers, and that's the iterator, and we're calling it IT. And we're initializing it nums1.begin, which is the first element in this vector, which is that 1 right there. So that's where we're at now. And now you can see what's happening here. I've got a while loop. It's really simple. I'm saying while the iterator is not pointing to this guy over here, the end, In other words, while the iterator is in the real list, in the container, in this case, a vector, what I want to do is display what it's pointing to and then increment. So you can see what this is doing. It's just going here and then here and then here and then here, and then it's going to stop. So this will print out 1, 2, 3, 4, and 5. Right? Just like that. So let's take a look at this loop right here. What we're doing here, it's really the same thing. Now remember, this iterator now, IT, is over here. It's pointing to the end. So if I want to go back to the beginning, I could just simply say IT equals nums1.begin, right? So I'm resetting that iterator to point to the beginning of this container, of this vector. So what I'm doing is the same loop. While I'm not at the end of the list, this time I'm doing this right here. Now that's an interesting statement. Remember, it's dereference the iterator equals 0. Just like we did with pointers. What are we doing? We're storing 0 where the iterator is pointing, and we're looping through. So what we're doing is we're doing this. We're changing all of those values in that vector to 0. And then I'm just calling display nums, which should display a bunch of zeros. All right, so let me erase this and give this a run and see what we get. There's our output. 1, 2, 3, 4, 5, just like we expected, and then a bunch of zeros when we call the display function. Hopefully you all are with me. These iterators are pretty straightforward, but it's important to understand them because we really need to use them with the algorithms. So we have to be able to make sure that what we're getting is what we want. So let's take a look at test 3. Let me take care of main real quick, and I'll uncomment this one out so we can run test 3. And here's test 3. Now what we're going to do here is we're going to use a constant iterator. All a constant iterator is an iterator, but I can't change what it's pointing to. It's constant. So we can do this a couple of different ways. We're doing the same declaration here of num1s. That's my vector of integers. Again, 1, 2, 3, 4, 5. Now what I'm doing here is I'm saying IT1 is a const iterator. Notice const underscore iterator. What that's doing is it's creating a constant iterator, not just an iterator, again, a constant iterator. And it's starting at the 1 again, num1.begin. And I'm not going to write that again because you guys kind of know what's going on. Now, if I wanted to not use this long style and just use the auto, I can't just say auto IT1 equals nums1.begin because that'll give me a regular iterator. I have to say cbegin. That's going to give me the constant iterator. So these two lines would be equivalent. Okay, we could do it either way. Now what we're doing here is we're just looping through and printing them all out again, 1 through 5. But let's see if we can change things, right? Remember here, we're trying to change each one of those elements to 0, just like we did in test 2 a little while ago. I can't do that, right? I'm not allowed to do that because it's a const iterator right here. So if I try to do that, let me uncomment that line out right here. If I try to do that, I should get a compiler error. And it's exactly right. Now, this is one of the things that you'll notice about compiler errors for the standard template library. They're not exactly readable compiler errors. Some of them are really, really nasty and hard to understand. But this one's not too bad. It says error assignment of read-only location. That gives you a clue, right? I mean, we've got a constant iterator here, and you're trying to write through it. So that's the rest of the error message, which is kind of nasty to read. So I'll comment this back out. And if I run it now, I should just get the 1 through the 5. Just like we did before. Perfect. Now let's take a look at test 4, which adds a few more little things to the mix. We'll use some containers that we haven't used yet. So let me uncomment test 4, and let's take a look at test 4. There's a lot going on here. First thing is we're going to use a reverse iterator first. So what we're doing here, we've got a vector 1, 2, 3, 4. I probably should have put the 5 in there. I forgot. So, but it doesn't matter. We've got a vector 1, 2, 3, 4, and it's vec. It's a vector of integers. Now I'm creating IT1 as my iterator. And notice that I'm using auto and I'm using rbegin right there. That's a reverse iterator. That's what the R stands for. And then what I'm doing is while IT1 is not equal to vec.rend. So now we're just going the other way around, right? So we're going 4, 3, 2, 1, and the end is actually over here now. And we're simply displaying, and notice I'm incrementing, right? You may want to decrement since you're going the other way, but we're using a reverse iterator. So incrementing here really means decrementing here, and the other way around as well. Now let's look at a couple more examples. Here what we've got is a container we haven't used yet. We'll use it a lot later on. We're actually going to do a nice little challenge with it. It's a list. A list is basically a doubly linked list. So remember how a vector was a bunch of data contiguous in memory? Well, a list is some items that kind of look like that, or elements, and then we've got pointers back and forth so that we can move from one to the next one really easily. So that's all it is. We don't really have to worry too much about how it's implemented behind the scenes to use it, which is really cool. So look what I'm doing here. I'm declaring name. I should call that names, but that's okay. Name is a list of strings, and I'm initializing it to Larry, Mo, and Curly. Now what I'm doing is I'm setting IT2, and this would be Larry here, this would be Mo here, and this would be Curly over here. Then I'm saying IT2 is a constant reverse iterator. That's the CR. So right now, IT2 is pointing right over here at the end because it's a reverse iterator. If I dereference it, it's going to print out Curly. Now I'm going to increment it, which simply means move it over here. Remember, incrementing means going reverse. So in this case, I'm coming over here, and I'm pointing to Mo, and right here, I'm going to display Mo. Over here, I displayed Curly. So that takes care of that one. And then let's do a few more. Now, this is a data structure that we haven't used yet, a container we haven't used. It's a map. What is a map? A map is, think of a map as a key and a value. So it's a pair. And I talked about this earlier. There's a class called stdpair, and that's basically what's happening. The first item in there is called first, and the second item in the pair is called second, and we can access them directly. So look what I'm doing here. I'm creating favorites, and favorites is a map of string pairs, and I'm just initializing them. So all we're doing here is creating an association between two strings. So Frank likes C++, Bill likes Java, James likes Haskell, or Frank hates C++, Bill hates Java, whatever makes sense here. So that's the map. And now what we're going to do, we're going to have another iterator, in this case IT3, and it's favorites.begin. So it's going to go to the first item in that map, which in this case is Frank. And I'm going to loop while IT3, while that iterator is not pointing to the end of that map. Now, how is a map stored behind the scenes? It's a complex data structure. It doesn't matter. I don't need to know that. To use this kind of logic, that's the beauty of this. It really doesn't matter how it's implemented behind the scenes. So in this case, while I haven't hit the end of that map, for each one of those guys, I'm going to take IT3 first and IT3 second. Makes sense, right? So we're basically using the arrow operator, dereferencing the iterator, getting to that pair, and then taking the first item and the second item in the pair, and then we're incrementing the iterator. So let's run this. And here are our results. Let me scroll up just a little bit here. Here we're displaying this reverse iterator. We're using the reverse iterator to display this vector vec, and we're getting 4, 3, 2, 1. Over here we got Curly and Mo. Remember, we're starting at the back, so we're getting Curly, and then we're incrementing, which means moves to the left, and I've got Mo. And then I'm just iterating over this map, so I'm getting Bill Java, Frank C++, James Haskell. Now notice the order here. It's not the order I put them in. The last one we'll do test 5. And test 5 is pretty easy. So far, everything we've done, we've iterated through an entire container. Well, what we're going to do here, we're just going to iterate over a subset of the container. So we have a vector of integers, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And here's the end. And now I've got two iterators. I'm using auto for both, so the compiler can figure out the type. And I'm saying start, that's the name of my iterator, is equal to vec.begin plus 2. Well, vec.begin is this guy, plus 2 would be the 3. And finish, vec.end minus 3. Well, here's vec.end minus 1, 2, 3. That's what we've got. That's start and finish. So now what I want to do is I just want to display the elements between them. So right there's the logic. While start is not equal to finish. Display what start is pointing to. So it's going to display 3 and then increment start. Display 4, display 5, display 6, display 7. Now they are equal, so this fails and we're done. So this will display this subset of that vector. All right, so let's run this. And you can see 3, 4, 5, 6, and 7 being displayed right here. Okay, so play with these examples. I've broken them up into these small test cases. That way you can tweak them a little bit rather than having one huge main that's going to get really complicated. So come in here, comment them out, add your own logic, play around with reverse iterators, constant iterators, regular iterators. You saw how I created the map so you can kind of figure out based on my code what I did. Now, obviously, I'm going to talk about lists and forward lists and maps and vectors and sets and everything else in the upcoming videos. In this video, I'd like to go over the basics of algorithms in the standard template library. The STL algorithms work on sequences of elements that are obtained from STL containers using STL iterators. It's really a beautifully designed library. The STL has many common and useful algorithms. Once you learn how to use them, you'll keep coming back to them over and over again. There are many algorithms, and the algorithms themselves have many variants. Way too much to describe in a single section of a course. I'll go over some useful algorithms, but more importantly, I'll teach you the techniques involved so that you can use any STL algorithm. You can refer to online references such as cppreference.com for details about the entire algorithms library. Many of the algorithms in the STL require the programmer to provide extra information in order for them to work. For example, suppose we want to display all the even numbers in a container. We can use an algorithm called forEach that will apply a function to each element in the container. But it depends on the programmer providing that function. So there are 3 main ways in the STL to provide such information to algorithms. They are functors or function objects, function pointers, and lambda expressions. I'll show you a simple example of each so you know them, but I'll be using lambda expressions for the examples in this section. You should also use lambda expressions in your code, since this is how to do it going forward in modern C++. So what do these algorithms look like and how do we use them? We saw a simple example of using the accumulate algorithm a few videos back. But in this video, I want to show you a few more, and then we'll code some in the IDE. First, in order to use the STL algorithms, we must include the algorithms header file. It's also important to understand that different containers support different types of algorithms. And since algorithms depend on iterators, this determines the types of algorithms we can use with certain containers. I know this sounds complicated, but it's really not so bad. As you become more experienced with the STL, it all becomes second nature. So before I show you some examples of STL algorithms in action, let's talk about iterator invalidation. This topic can get quite complex, but let's look at it in its simplest terms. We know that iterators point to container elements. We need to understand that it's possible that an iterator may become invalid during processing. Let's see a very obvious example. Suppose we have an iterator and we're iterating over the elements of a vector and displaying the elements as we go. Then, as we're doing this, we call the vector's clear method. This deletes all of the elements from the vector. But the iterator doesn't know that. The iterator will happily continue iterating until it sees the end of the vector, but this is no longer valid. If something like this happens, then the behavior is undefined in C++. Every STL container has documentation about when iterators become invalid. We won't worry too much about it in this section, but it's something to be aware of as you move on to more advanced STL work after this course. Okay, so let's see some examples of STL algorithms. First, let's look at the find function. The find algorithm tries to locate the first occurrence of an element in a container. Like most STL algorithms, there are many variants available, so let's keep it simple. If the function finds the element, it returns an iterator that points to the element it just found. If the function does not find the element, it will return an iterator pointing to the end of the container. Pretty simple. So let's see this in code. First, we declare a vector of integers, we'll call it vec, and we initialize it to the integers 1, 2, and 3. We then call stdfind and pass in the iterators we need to get the sequence of elements we want. After that, we pass in the element we want to find. In this case, we call find with vec.begin, vec.end, and 3. So we want to find 3, and we want to search the entire vector. The result of the function will be stored in a variable LOC. I'm using auto to let the compiler deduce the type of LOC, but you know what it must be, an iterator to a vector of integers. That's it. Now we can check the value of LOC, and if it's not vec.end, we know LOC is pointing to the first occurrence of 3. And we can do whatever we want with it. In this case, I'm just displaying it. Okay, so let's take a breath here and understand the power we have. We just found the first occurrence of an element in a vector. What if we wanted to find the first occurrence in a list or another type of container? It works exactly the same way. That's the power I'm talking about. We don't need to know the details about how the container is implemented or how complicated finding an element might be behind the scenes. Remember, find needs to be able to compare two elements in order to see if they're the same. In order to do this, it will use the equality operator. For primitive types like ints, we don't have to do a thing since the compiler knows how to compare primitive types. But if we're using our own user-defined objects and containers, then we must provide the overloaded equality operator for our objects, since that's what the algorithm will call. In this case, you can see we have a vector of player objects. Let's assume it's initialized to a bunch of players. And we define P to be the player we want to find in the vector. Notice the code for the find function. It looks the same as for ints, except for the P. The only difference is that the compiler will compare P to the container elements using the overloaded equality operator that you must provide in the player class. Also, we can define what equality means. We might want all player attributes to match, or only the name, or only the XP. We have all the power to decide. Now let's look at a more complex algorithm, the for-each function. This function applies a function to each element in the iterator sequence. Okay, but what function does it apply? Whatever function you tell it to apply. That's pretty cool. So how do we provide this function to the for-each function? There are 3 ways, and I'll show you each way in the following slides. We can use functors, function pointers, and lambda expressions. Functors and function pointers have been around since the beginning of the STL. Lambda expressions were added in C++11, and they're really the way to go in modern C++. So let's write a for-each function that displays the square of each integer element in the vector. First, let's do it with a functor. In this slide, we'll see how we can use a functor or function object. But let's start at the bottom first. In the last statement, we're using a for-each function and providing the iterated parameters as usual. So this will iterate over the entire vector vec. Okay, now look at the last parameter, square. In this case, square is an object, a function object of type square functor. You can see where I created the square object in red type. And square functor is a structure. It can also be a class that has a single public method. I know this might look a little strange. The method that's being overloaded is the function call operator. That's the open and close parentheses. It expects a single item that's the same type as the elements in the container we're processing. And in this case, it executes the code for each integer passed into it. Okay, I know this sounds pretty complicated, but let's walk through it. We're going to iterate through each element in the vector, and at each iteration, the overloaded function call operator function for the square object will be called, and the current container element is passed to it. In this case, we'll call square, and each container element will display. So in this case, we get 1, 4, 9, and 16 since they're squared. Note that the original container elements are not modified. Now let's do the same thing but using function pointers instead of a functor. Again, let's start at the bottom. Notice that the code for the for-each algorithm is exactly the same. But in this case, the square parameter is not a function object. It's the name of a regular function. And we declared that function at the top of the slide in red. What's being passed into the for-each function is a pointer to the square function, which is really the address of the function square itself. So at each iteration of the for each loop, the square function will be called and the current container element passed into it. So we get the same output as with the functor, 1, 4, 9, and 16. Notice that we only use the function name as the parameter. We don't place parentheses after it, since that would call the function. That's not what we want. Finally, in the next slide, we'll use a lambda expression to accomplish the same thing. In this example, we'll use the lambda expression directly in the function call. Lambda expressions were introduced in C++11, as I said, and they're widely used in modern C++. If you come from another language, you may know them as lambdas, closures, blocks, or anonymous functions. It's basically all the same. First, notice that we have no other code except the call to the for each algorithm. One of the benefits of lambda expressions is that we can define them right where they're being used. The first part of the for each function is the same. We're providing our iterators. The last parameter is what changes. In this case, we're using a lambda expression. The syntax of the lambda expression will become more clear with time and practice, but it consists of a pair of square brackets followed by the parameters that will be passed into the lambda expression in parentheses. In this case, a single integer which we'll name x. Then this is followed by the body of code we execute. That's it. It's really pretty easy and all in one place, so we know exactly what's happening at each iteration by looking right in the function call. I'll go over a couple of other STL algorithms, and I'll use lambda expressions and walk through them in the IDE next. So let's head over there in the next video. In this video, I'd like to go over some of the algorithms in the STL. Now, there are a lot of algorithms in the STL, and we're only going to cover a few of them, but the techniques you'll see apply to many of them, and you could be very productive with them very quickly. I'm in the Section 20 workspace, and I'm in the Algorithms project. And let me just go over these includes real quick. I'm including algorithm. We need that to use these algorithms. I'm also including vector, list, and cctype. Now, cctype we're going to use for the toUpper function that converts a character from lowercase to uppercase. That's the only reason we're going to do it. And most of the examples we use a vector, but there's one that's going to use a list just to change things around a little bit. Okay, so that's that. We're also going to use this person class that I created right here. It's a really, really simple person class. A person has a name and an age. I think we've used a class like this or very similar to this before. I have a default constructor that Pyler will generate for me. I've got an overloaded constructor that expects a name and an age. And then I've got these two operators. These are really important whenever we use the STL. It's got to have a way to compare our own objects. Now, these are all user-defined types, so I need to provide the less than and the equality operators. And all I'm doing here is I'm saying that one person is less than another person if their age is less than the other person's age. This is just totally arbitrary in this example. This really would depend on whatever business logic you're using. And how do I compare two persons? Well, their names have to be the same and their age have to be the same. So we've got that and here. So that's it, a real simple person class that we're going to use in here. So I've also divided this into functions just like I did with the iterators lecture. So let's take a look at this first one here. What is the algorithm we're using? The algorithm is right there. That function is the find function. It finds an element in a container. Okay, the first occurrence of the element in the container. So what are we going to do? Let's create a vector of integers, 1, 2, 3, 4, 5. Then I'm going to call std_find. I'm going to give it the beginning and the end. Now notice that this syntax here is a little different. I just wanted to show you that syntax in case you run into it. It's equivalent to vec.begin and vec.end, like we've seen before. But in this case, it's std_begin, and then you pass in the vector or the container. So it's just another way to do it. It means exactly the same thing. So let's get back to this. I'm calling the find function. I'm passing in where I want to start, where I want to end, right? That's the sequence that I'm going to get back from the container. And I'm using these iterators. And that's what I want to find. I want to find that element 1. I know it's there. It's right here. Okay, now, what does this return? Well, if it finds it, it will return an iterator pointing to it. If it doesn't find it, it'll return an iterator to the end. So it's really simple to check. Okay, so let me clear this and let's look at the logic here. So we're executing that function, and if the location, remember location, I'm using auto, but location is an iterator to a vector of integers. If the location is not equal to the end of the vector, then we found it. We found the number, and we could just dereference it and print it out. In this case, it'll print out 1. Otherwise, we couldn't find the number. So let's execute this, and then we'll change the code just a little bit. So let me run this real quick. We found the number 1. Absolutely, it's in there. Now let's change the 1 to something like a 7. We know that the 7 is not in the vector. So let's execute this again. Couldn't find the number, just what we expected. Now I'm going to change this back to 1 so that you guys can play with it when you have the source code on your end. That's as simple as it gets. And the really cool thing about this is I'm finding the first occurrence of an element in any container. That's mind-blowing, right? Because you're not worried about how this stuff is implemented. You've got all these different containers. How easy is this? I just want to find something. Just go call find. Where do I start? Where do I end? What do I want to find? That's real classic abstraction. That's pretty cool. That's using a primitive type, an integer. What would it look like if we're trying to find a player? So that's what this example right here is going to show you. So let's take a look at that. In this case, I'm not using a vector. I'm using a list, but it's all the same. I've got a list of persons. Right? I'm calling them player. I'm initializing it to Larry is 18 years old, Mo is 20, and Curly is 21. Remember that person class I showed you a little bit ago? I want to find that person in that list. Look at the code. Auto location 1 equals stood find. Where do I start? Where do I end? What do I want to find? The STL algorithms is going to use the equality operator that I've overloaded for my person class to compare these guys. So hopefully it'll find this guy right here, right? So if location 1 is not equal to the end, then I found Mo. Otherwise, I didn't find Mo. And how do I know that Mo is Mo? Well, Mo has to be, his name has to be Mo, and he has to be 20. Remember, our equality operator is checking for both. All right, so let's give this one a run. And we should see found Mo, and that's exactly what we get. Now, if I change Mo's age here, let's say I make him 18 or 12. That's not in there. I don't have a Mo 12 in there. So at this point, when I run it, I should not find Mo, and it says Mo not found. That's exactly what we expected. So let me change this again back to 20. Okay, so that is the find test. That shows you how to use the find function. Super powerful. I mean, when you think about it, how hard is it to write a find function for an array? It's not really. You start at the beginning and you move along, you found it, I'm done. But what about a list, a doubly linked list, a priority queue, a set? Wow, that's a lot of code you would have to write yourself. You don't even have to worry about any of that. You just call find, tell it where to start, tell it where to end, and tell it what you want to find, and you're done. It's as simple as that. Okay, so that's the find test. Let me show you the count test now. So I'll uncomment that out, and let's take a look for the count test. This one is really, really dead simple. All it does is it counts the number of elements in a container, but you can take it a little bit further. You can actually count the number of occurrences of that specific element. Remember, we could just use size for the count of the elements, but in this case, how many times does the 1 appear in this container? Well, I've got it here, here, and here. It occurs 3 times. So what's my algorithm? Count from the beginning to the end. And again, you can use a subset if you like. I'm always going to do beginning to end in these examples. This will return an integer. If we get back a 0, didn't find it. If we get back a 1 or a 2 or a 3, that's how many times the 1 occurred. So in this case, I expect back a 3. Let's run this. And there it is, 3 occurrences found. So the 1 was there 3 times. Again, if I put something that's not in there, like a 10 in this case, and I run this, it should get back 0 occurrences found. And that's exactly what we get. Okay, simple as that. So let's close this one down, and let's take a look at a more powerful one called the COUNTIF test. So here's the COUNTIF. The COUNTIF is a little bit different. We're going to use a lambda expression for it. This one's super powerful. We're only going to count how many times that element occurs if it matches some condition. Okay, that condition is called a predicate. It's something that returns a true false value. So here's my vector. And you can see that, what's my condition? Well, you can see right here. Look at the lambda. The lambda tells you exactly what I'm doing. I'm only looking for numbers that mod 2 or 0. I'm only looking for even numbers here, right? That's what that predicate right here is doing. So I'm starting at the beginning, and here's my lambda. I'll write it up here just so we understand exactly what's going on. There's my lambda, and here's the code for the lambda, which is this piece right here, and I won't write that again. That's my lambda. So what's going on? I'm starting at the beginning of that vec. I'm going toward the end of the vec. And for each element in that sequence, I'm passing it into here. And that's going to return true or false. Depending on what it's returned, it's going to include it in the count here. Okay. So in this case, what's being passed into this lambda here is 1, and then 2, and then 3, and then 4, and then 5, and so forth. And all it's doing is, if this is true, if this predicate right here is true, it's just counting them up. Okay, so in this case, how many even numbers do we have? We have 1, we have 2, we have 3, we have 4. So I would expect a 4 coming back. Okay. Over here, you can see it's the same idea, except this time, what am I looking for? I'm looking for odd numbers. How many odd numbers do we have? We have 1, 2, 3, 4, 5. So we've got 5. I expect a 4 from here. I expect this to print out a 5. Now let's write another function. We'll write this one together. How can we determine how many elements in the vec are greater than or equal to 5? So what do? Well, we write the statement. Real simple. Num equals std count if. That's my algorithm. We're going to do vec.begin. Let's search the entire vector. We're going to go to vec.end. Now we could have used a constant iterator here. We could have used a lot of things. I'm just going to do it real simple. So I'm going from beginning to end. And at this point, this is where I need my lambda. So all these elements are being passed into this. So what am I going to do? I'm going to put my lambda in here. It's going to expect a single integer. I'm going to write my code right in here. Then I'm going to close this and close it like that with a semicolon. So what is the predicate? I'm going to return true if x is greater than or equal to 5. Just like that. And let me just copy this line right here. I'll move it down here. So all I'm going to do is I'm going to output numbers are greater than 5. How many of those do we expect? Well, we've got two, greater than or equal to 5, sorry. So we have the 5 and the 100. So there's only 2. So let's run this. We have 4 even numbers, just what we expected. We've got 5 odd numbers, and 2 of the numbers are greater than or equal to 5. I'll change that. There you go. Pretty simple. These lambdas take a little getting used to, but you get used to them really quickly, and they're so powerful. It makes programming much, much simpler. Okay, so that's count if. The next one we'll do is a replace test. So let's take a look at replace test. Let me uncomment that out here. So what is this doing? Well, this is looking through a vector in this case, or any container, and it's going to replace one number with another. Pretty cool. So here I've got a std vec, and I've got 1, 2, 3. Notice the ones. That's all I really care about in this case. I've got 3 of those ones right in here. I'm just displaying them out right now, and we'll display them out. And then I'm calling std replace, and I'm starting at the beginning, going to the end, and I'm replacing 1 with 100. And remember, I'm using primitives here, but we can use our own objects if you like. So in this case, I'm replacing those 3 ones with 100, and then I'm just displaying it again. So let's give that a run. And we'll be able to see that we've got 1, 2, let me move this over just a little bit. 1, 2, 3, you can see the 3 ones here, and you can see that the 3 ones have been replaced with hundreds. Really cool, really easy. Okay, let's do a couple of more. And the point of this is not to show you these specific algorithms. There's, like I said, over 50, probably closer to 90 algorithms out there. If you look at the numeric header as well, they all work in a similar way. They all use iterators. Many of them use predicates. So this gives you a pretty good feeling for the power that's out there and the things you can do. So this is the all of test. This is really cool. Let me show you this one. So here's my vec 1, and I've got a 1, a 3, a 5, a 7, a 9, a 1, a 3, a 13, 19, and 5, just some arbitrary numbers in there. What this is doing, there's the function all of, it's going to see whether all of the elements in that container match this predicate. That's super powerful. So in this case, I'm saying if all of those elements are greater than 10, then this will return true. Otherwise, it will return false. So obviously they're not all greater than 10, right? I've got a 1 and a 3 and a 5. So I expect this to return false, and I expect this to print out. In this case here, I'm starting at the beginning, going toward the end. I'm checking to see if all the elements are less than 20. You can see in here they are less than 20. Every single one of them is less than 20. So I expect this guy to display right now. We have the all of. There's also another algorithm called any of, so if any of them is greater than 10, it'll be true. So you've got the power to compare them all or just compare one of them. So let's execute this. And we can see here, not all of the elements are greater than 10. Absolutely, we've got some that are less than 10, but all the elements are less than 20. And I can't impress upon you the fact enough times about how powerful this is. We don't really care about the container, and that's the cool part. I don't need to worry about it. It could be implemented in a really, really complex way. It doesn't matter. The algorithms library handles it for us. All right, so the last example is a string transform test. This is pretty cool. There's an algorithm called transform, and it works not just with strings. It works with containers, obviously, but it's used very often with strings. Let me show you what it does. And this is where that toUpper function comes in. So here I've got str1 is a std string, and it's initialized to this is a test. And all I'm doing is I'm displaying, before the transform, I'm displaying the string. So that's just going to display this is a test, just like that. Then I'm going to call the std transform function. I'm going to tell it where to start at str1 begin, where to end. In other words, it's processing the entire string, and then where to start placing its results at the beginning of the string again. And what do I want to do? Well, I want to make each character toUpper, and I can pass my own function in here, but we already have the toUpper function defined in CC type, so may as well use it. Whenever you put that scope resolution operator in the front of something with nothing here, just that guy followed by something else, that means global scope. And that's what's going on here. So I'm using the toUpper method, or function actually, that's in the global scope. So what do you think this does? It makes every single character in that string uppercase. Super powerful. We can process strings. If you remember that one example we did a while back way back in the course, right, where we encrypted a string, this makes it really easy because you can transform that string. You can play all kinds of games with it, and the algorithm becomes much cleaner. So let's run this example. And we should see the string in lowercase and then the string in uppercase. There it is. This is a test. This is a test. All right, so that gives you a little bit of introduction. And let me uncomment this out, set it up just like that. So I'll save it like that for you guys to be able to download it and play with this from the beginning. So here you can see the find, the count if, the replace, the all of. You can play around with the any of. And what I would encourage you to do is, let me just close this up a little bit. What I want to encourage you to do is play with these lambdas. Give yourself different conditions. Make them a little bit more complicated if you like. And just get used to the lambda syntax. One of the things that we're not going to do in this course, or maybe I will in a different section later on, I can add a section just on lambdas. That guy right there, those two square brackets, that's the lambda's capture block. That's a real important piece of the lambda that allows you to capture the context. So if I have variables in here, I can catch them in there and set them and use them. We're not doing that in here. We're just keeping the lambdas really simple. Hopefully you do understand these lambdas and how powerful they are. Play around with them, get comfortable with them. It's really the way to go with modern C++. All right, so that's it for the algorithms demo. Now we're going to start talking about the actual containers. The first one we'll talk about is std array. So I'll be right back to talk about that. In this video, I'd like to go over one of the most basic of the STL containers, the array container. I'll call it std array in this video so we don't confuse it with a raw array. In order to use the std array container, we must include the array header file. The std array container allows us to create fixed size arrays of any type. So, what makes this different from a raw array? A lot. First, it's an object type. Std array always has its size associated with it. Unlike a raw array, a std array doesn't decay to a pointer to the first element of the array when we pass it into a function. It's also very efficient. Element access happens in constant time. Constant time means that the time it takes to access an element is independent of the number of elements in the container. So if std_array has 5 elements and you wanted to access one of them, the time required would be the same as if it had 100,000 elements. Also, since a std_array is implemented behind the scenes by the STL as a wrapper class around a raw array, we can get access to that raw array address if we need to, and we can use it with libraries that use raw pointers. But the biggest benefit is that it's part of the STL, so we can use it with iterators and algorithms. The std_array class wasn't part of the original STL. It was added in C++11. You should always first consider using std_array in modern C++ when you have a need for a fixed size array. Don't use raw arrays unless you have a compelling reason to do so. All of the STL iterators are available with std_array, and they don't invalidate. And that makes sense because std_array is a fixed size structure. Okay, so first let's look at a few ways to initialize std_arrays, and then we'll see some of the common member methods. std_array is a very simple template class. Since the size of the array must be known at compile time, we have to provide both the type we want to store in it as well as the size. This is exactly what we did a few videos ago when we created a myArray class. In the first example in this slide, I declared ARR1 as a std_array of 5 integers, and I initialized these 5 integers to 1, 2, 3, 4, and 5. If we have more than 5 integers in the initializer list, we'll get an error. If we have fewer than 5, the remaining integers omitted will be set to 0. Now, there is a quirk with the initializer list. In C++11, you need to provide double curly braces. In C++14 and forward, you don't, just a single curly brace. So in the second example, I'm declaring stooges as a std_array of 3 strings, and I'm initializing them to Larry, Moe, and Curly. Note that I can use C-style string literals, and they'll be converted to std strings. There's also a very handy way to assign multiple values to an existing std_array. We can use an assignment statement and an initializer list. This is really cool and extremely useful. So now let's see some common methods provided by std_array. In this section, I'm not going to exhaustively go over all the methods provided by all of the STL containers. That would be pretty boring for me, and it would probably be even more boring for you. So what I want to do is I'll go over some of the most common methods used and some of the methods particular to specific containers. So let's start with the size method. This method is available to all containers. In the std_array, it's pretty simple. It's the size of the container and it's fixed. Arrays also let us access individual array elements. We can use either the subscript syntax or the .at method. Now, if you remember from the vector, subscript operator does no bounds checking, but the at method does do bounds checking, and an exception is thrown if we're out of bounds. You can see in the example code that ARR at 0 will refer to 1 in the array ARR, and ARR sub 1 refers to the 2. The std_array also provides front and back methods. Now, these methods return references to the element at the front of the array and of the element at the back of the array, respectively. In this example, ARR.front refers to the 1, and ARR.back refers to the 5. The empty method will return true if the std_array is empty and false otherwise. This doesn't mean how many elements out of the total elements you're using. It basically means it's the size of the array. This is rarely ever used with std_array, but it is with other STL containers. The fill method is very handy. It fills the std_array with whatever element is provided. Remember, I'm using ints here for these examples, but these could be almost any data type. We can also swap 2 std_arrays of the same size and type. All we have to do is simply call swap with one and pass the other in. And finally, we can use the .data method to get access to the underlying raw array. In this case, data returns the address of the raw array of integers, which we store in a pointer variable. As you can see, std_arrays are very straightforward. Now let's head over to the IDE and we'll see some more examples of using std_array. Before we head off to the IDE and run some examples with std_array, I'd like to refer you to this website, and I've mentioned this website a couple times in the course. It's cppreference.com. I'm here in the United States, so I'm getting the English version. I'm not sure if this is localized for other countries. It seems like it would be because you see the EN at the beginning here. In any case, go to cppreference.com, and it's got all kinds of good information about C++. Up to now, we really haven't needed it too much, but With the containers library and the STL, your algorithms and your iterators, this is a really useful reference. I'm right at the main page here, and you can see the containers library is right here. So I'll just select that. And it shows you all the containers in the STLs. For example, array, that's one we're going to talk about now. Vector, a deck, a forward list. We'll talk about all of these in this section. But let's just look at the array. And this gives you a lot of really good reference and documentation on the array. You can see it's implemented as a template class here. And if you scroll down just a little bit, all of these containers will talk about iterator invalidation. So if you're not sure about if you've got an iterator and you've removed an item, is it invalid now? It'll say it all throughout the documentation here. Also, the other important piece are these right here, these member functions. This tells you what member functions are available for this particular container. Now you can see here I can construct it and destruct it and so forth, but these are the real important ones here. This is a really simple container, the array container. So you've got the @ method, you've got the overloader subscript operator. Notice this one does bounds checking and the operator subscript does not. The front, the back, the data, the same things I talked about in the slides. We've also got iterators. You can see all the iterators are available to us here. And then we've got some capacity methods and the fill and the swap that I also mentioned. So this gives you a lot of really good information. Now, if you're not sure about what the front method does, I mean, it says here, access the first element, which makes sense, right? The front. But if you want more information, you can click on here. And not all of these things are going to be easy reads when you're first starting out with C++, but you'll understand this soon enough. And little by little, you'll understand more and more and more. And then these references become very, very handy. In this case, you can see, what does it do? Well, it provides a reference to the first element. That's kind of what I said earlier, right? The complexity is constant time, which is cool. Usually, most of these methods will have a complexity associated with them, and it'll be listed here. I mentioned before that with the STL, you know what you get. So when you're using these methods, you know their complexity. So if you're using something that's at linear time, you'll understand that. If it's constant time, it'll say it as well. And then it's got usually some kind of sample code here that you can run right inside your browser. So it's a very handy site. I think you're going to refer to this a lot. When I go to the IDE, I'll be playing with a lot of source code that you can play around with, and it covers the majority of these, but obviously it's impossible to cover them all, especially as the containers and the algorithms and the iterators all come together. The permutations just go skyrocketing. So play on your own and go through here, study this. This is the best way to really learn the STL, but watch the videos first, and then you'll be able to understand this a lot better. All right, so let's head over to the IDE. Okay, so I'm back in the IDE. I'm in the section 20 workspace in the array project. And what I've done is I've broken this project up into 9 test functions. And each one of these functions is independent and deals with specific methods or iterators or algorithms. That way you can really learn. My perspective on the STL is the more examples you can see, the better you're going to learn it. And the more you can apply what you're learning to other examples that you haven't seen yet. Okay, so why don't we start? Rather than jump back and forth and running and compiling and so forth, I've already run this. And the output is over here on the right. I've run all 9 functions over here on the right, and there's the output. And what I'll do is I'll go through them so that you can understand exactly what's going on. This will save a little time, and that way you can stop the video and look at them as well. So let's start with test 1. First thing we're going to do here is we're going to create 2 std arrays. They're both the same size, and they're both of the same type. So I'm creating an array right here called ARR1 of 5 integers. And I'm initializing it to 1, 2, 3, 4, and 5. I'm also creating array 2, same size, same type, but I'm not initializing it. And then I'm displaying both arrays. Now the display function is right up here. Let me clear this and show that to you. And the way the display functions work for std arrays, notice the parameter right here, the parameter type. You've got to supply the information. So you've got to supply the type and the size. And all it's doing is just using a range-based for loop to display it. All right, so let's get back to this. Let's go through test case 1 here. So we've got those 2 arrays, AR1, AR2. I'm displaying both of them. They're out right here. You can see there's my test 1 output right here. Notice the first one prints out 1, 2, 3, 4, 5, exactly like we expect. Now notice ARR2, we're displaying it right here. We've got 5 garbage values, so nothing is initialized. When we do something like this, we're initializing the std array, but we're not initializing the elements of the std array. That's important to understand. Now, what we have here is a really nice way to assign a bunch of values to a std array. And the syntax is dead simple and it's so handy. So what we're doing here is we're assigning 10, 20, 30, 40, and 50 to ARR2. That's the one that had all those garbage values in it. And then we're displaying those two arrays again. So you can see them displaying right here. 1, 2, 3, 4, 5, and now 10, 20, 30, 40, and 50, which is really nice. Here we're just displaying both sizes. Now they're both the same size, right? So we expect a 5 and a 5, and that's exactly what we get here. They're both size 5. Size isn't really used very often with std arrays. The size is fixed, right? So it is what it is. It's right here. But it's used a lot in other containers. Let me clear this a little bit and let me scroll up just a bit so we can get to these guys right down here, the last couple of lines. You can see here in this example that we can subscript into ARR1 or ARR2, any std array. This does not do bounds checking. So what we're doing here is we're storing 1,000 into ARR1 sub 0. Okay, that's this guy. We're basically replacing that 1 with 1,000. And then over here, what I'm doing is I'm replacing ARR at 1 with 2,000. So that would be the 2. So I'm replacing the 2 with 2,000. Okay. This does no bounds checking. This does do bounds checking. So if I'm out of bounds right here, I'm going to get an exception thrown, an out of range exception. And all I'm doing now is displaying ARR1, and you can see ARR1 displaying right here. Notice the 1,000 and the 2,000 have been updated. And I still have the 3, 4, and the 5. And then the last two examples are right here at the bottom, where I'm saying what is ARR.front and what is ARR2.front and ARR2.back. So what's the front element of array 2 and what's the back element of array 2? Well, array 2 is right here. The front element is a 10. The back element is a 50. That's exactly what we expect. That's exactly what prints right here. Okay, so some really simple examples. And again, I'm going to do a lot of examples in this section so that you can better understand how some of this stuff works. Let's take a look at the next one now. And you can see the output for test 2 right over here on the right here. All right, so what are we doing here? Same idea. I've got two arrays, array 1 and array 2. I'm initializing the first one 1 to 5 and 10, 20, 30, 40, and 50 for array 2. I'm displaying both of them. And there they are right there, just what you would expect. 1, 2, 3, 4, 5, and 10 all the way through 50. Now I'm using the fill method. I'm filling array 1 with zeros. And this could be any integer. I'm just passing a 0 into it. And again, remember, I'm using integers for these examples. These could be almost any type. So I'm using a 0 here. I'm filling array 1 with a 0, and then I'm displaying those guys again. Notice how array 1 right here is all zeros now. So it's a real handy way to fill an array with whatever value we want. Now we're coming here. And what we're saying is, let's swap those two arrays. Now I could say array1.swap array2 or array2.swap array1, right? I mean, swapping is swapping. So in this case, I'm swapping those two arrays and I'm displaying them again. And you can see that they have indeed been swapped, right? First it was a 0, then it was 10 to 50. Now it's 10 to 50 and the zeros are second. Okay, so let's move on to the third test. And let's take a look at this one. The results are right here. I had another line that printed that header right here, but I removed it. That's why you're seeing that test 3 twice. All right, so I've got array 1, 1, 2, 3, 4, 5. Again, it's a std array of 5 integers. Now, what's going on here? The data method returns the raw pointer that points to the behind the scenes raw array. What happens is, remember, ARR1 is an object. So it has some data associated with it. One of the pieces of data is 5, right? It knows its size. The other piece of data that it has is the actual array. In this case, 5. So this guy is what's returned, the address of that element. So when we say ARR1.data, what we're returning is the address of that first element in the raw array behind the scenes. Remember, the std array is really a wrapper around a raw array. And I'm storing that into pointer, which is a pointer to an integer, the address of an integer. Now, if I display pointer, you can see right there, that's the memory address being displayed. That's the memory address of that first element in the array. Now I can change that through the pointer. I could say dereference pointer equals 10,000, and I just put a 10,000 in here. And if I display AR1, you can see it right here. You see that 10,000 is being updated right there. Now, you don't do this very often. Obviously, the whole point of using a std array is not to use a raw array, but sometimes we use libraries that use raw arrays. So we can still use std arrays for our work. And then when we need to pass in the raw array, we can use the data method and send them what they want. But we can still have the safety and the ease of use on our end. And what's really cool about using the std arrays on our end is because they are STL containers. So we can use them with iterators, we can use them with algorithms and so forth. So that's the real power. We'll go to test 4. And test 4 is a real simple example. We're going to sort this array. It's really, really cool. Here's the array 2, 1, 4, 5, 3. Again, all of these are std arrays. And I've defined this one to 5 integers again. I'm displaying it right here. And this is test 4. So you can see the output right here. So I'm displaying array 1, 2, 1, 4, 5, 3. That's what we get right here, 2, 1, 4, 5, 3. Then I'm sorting it. Now this sort is an algorithm, right? That's my sort function, and it expects 2 iterators. Where do I start? Where do I end? Well, I'm starting at the beginning and I'm ending at the end. I'm sorting the entire array and then I'm displaying it. So you can see right here, it's displaying the sorted array, 1, 2, 3, 4, 5. Easy as that. All right, so let's take a look at test 5. And for each one of these tests, I tried to add a little bit different functionality. Again, the more examples you see, the better. Hopefully you'll start seeing the patterns of use and it makes it much, much easier to understand. All right, so here's test 5. You can see the output right here. It's just one line of output. Here's my array, ARR1, 2, 1, 4, 5, 3. And what we want to do is we want to find the minimum and the maximum in there. So we have an algorithm called min element, and we have another one called max element. It expects iterators, right? It's an algorithm. So array1 begin, array1.end. I want to search through the entire array for the minimum element. And this doesn't return the minimum element. This returns an iterator to the minimum element. So this is how you would declare that variable. Min_num is an iterator to a std array of 5 integers. Now that's ugly, right? That's really ugly looking code. It's readable, but it's kind of ugly. This is much nicer. Let the compiler figure it out. So I did it the long way for the minimum number, and I did it the short way using auto for the max number. So all I'm saying is auto max num, hey, compiler, figure out that max number is type based on the return here. And I'm doing the same thing. And remember, we get back iterators, so we dereference the iterators, and we get back the min number, which in this case is 1, and the max number, which in this case is 5. And that's exactly what we expected here. So let's move on to test 6. And test 6 is a real simple test. You can see it again right over here. There's only one line of output. There is another algorithm called adjacent find. And what it does, it searches through a container and returns the first occurrence of 2 adjacent values. Now, these 2 adjacent values are compared, right, with the equality operator, which we would overload if we had our own classes. But here we're using integers again. So you can see here it is right here. I've got 2 3s, one right next to another. That's what I expect. So this also returns an iterator. I'm using auto, and I'm saying adjacent equals std adjacent find from beginning to the end. Give me the first occurrence of any 2 adjacent items. It's possible there are no adjacent items, so I would check if adjacent is not equal to array end, I found something. If it is equal to array end, there were no adjacent elements. So in this case, we found them, and there's the iterator, which we dereference, and you can see right here, adjacent element found with value 3. Pretty cool and pretty easy and pretty powerful as well. Hopefully you're starting to see the real power of the STL. It's actually awesome. You can do so much with it. All right, test 7. Here's the output for test 7 right here. Real easy. We're using the accumulate algorithm. We've used this before as an example. In order to use this, you have to include numeric. Okay, it's not an algorithm, it's an include numeric, so make sure you do that. And all it does is it accumulates from this iterator to that iterator. And this is where it starts. If you started at 10, it would start adding from 10. In this case, I'm starting from 0. What's really important here is that this type and this type and this type are the same. So double, 0.0, make sure they're all the same. Otherwise, you can run into some really, really weird little errors. We do this, it sums them up, 1 plus 2 plus 3 plus 4 plus 5. We display it and we get the sum is 15, which is just what we would expect. And let's do a couple of more. We're almost done with these. Hopefully you're following along. I think you are, because it's pretty straightforward stuff. The last 2 we'll do is the count, and then we'll do a count if using a lambda in test 9. So here's test 8. This time I've got a std array of 10 integers. Now again, I called it array 1. And in this case, I've got 1, 2, 3, 4, 5, 6 threes. I just want to count them. So I'm going to use the algorithm count. So I'm going to say std count. They always use iterators from beginning to end. What am I looking for? The 3. That's it. What do I expect back? I expect back 6, right? I just counted them up here. So this is an integer. You get back the integer of the number of occurrences. It says I found 3 6 times. This same thing we would expect. And then the last one is the count if, which is very similar to count, except it's using a predicate. And what we're going to do is we're going to supply a lambda expression. So here's what I've got. I've got ARR1 again is 10 integers. It's a std array. And those are the 10 integers. You can see them right here. And what I want to do is I want to find out how many numbers are between 10 and 200. So there's 1, there's 2, there's 3, there's 4. I don't want to include 200 in this case. So I expect back a 4. So what do we use? We use count if. Where do we start? At the beginning. Where do we end? At the end. And what's the predicate? Well, I want to return true when x is greater than 10 and x is less than 200. That's it. And there's my lambda expression. You can see my x is being passed into here for each element. So the 1 will be passed in here as x, and we're going to check that. The 2, the 3, all the way from whatever our iterators say. So in this case, how many matches do we expect? 4. We'll display them right here, and that's what you get right there in the output. Okay, so again, a lot of examples. I did a lot of examples on purpose because I want you to have a lot of examples on your end in the source code that you can play with. And as I said, you're probably going to get tired of seeing these examples, but the more examples you see, the better. All right, so that covers std array. In the next video, we'll start talking about std vector, which you know a lot about already. In this video, we'll learn more about the STL vector container. We already know a lot about it since we've been using it since very early in the course. As you know, in order to use the vector container, you have to include the vector header file. The vector is probably the main workhorse of the STL. It's used in a lot of applications. The vector allows us to create dynamically sized arrays. The cool thing is that the vector can expand and contract as needed, and it's handled automatically by the STL. We don't have to worry about the details, but the vector does give us some control as to how it can grow. The vector elements themselves are stored in contiguous memory. So, as the vector expands, a new larger area in memory is allocated and the current elements are moved to it. Like the std array, the vector provides fast direct access in constant time. It also allows for rapid insertion and deletion at the back of the vector in constant time. However, inserting elements into any other part of the vector other than the back is not as efficient. It happens in linear time, which means that the running time increases linearly with the size of the vector. The vector supports all of the iterators, and the iterators may become invalid. This is especially true when the vector resizes and a new area in memory is allocated for the extra storage. In this slide, we see a diagram of what a simple vector might look like. We declare vec as a vector of integers and initialize it to 1, 2, and 3. The vector has a front and a back. The front in this case is element 1, and the back is element 3. We typically add elements to the back of the vector using the pushback method. So in this case, we're adding the element 4 using pushback, and the 4 is added to the back of the vector. We can add elements anywhere in the vector, but the back is the location where the addition of elements is most efficient. If there's no room and the vector needs to allocate more space, it will automatically. Usually twice the amount of the current space is allocated, and the current elements are moved over to the newly allocated area, and then the new element is placed at the back. Let's look at a few ways to initialize vectors, and then we'll see some of its member methods. In the first example in this slide, I declare vec as a vector of integers and initialize it to 1, 2, 3, 4, and 5. In the second example, I declare vec1 as a vector of integers, and I'm using an overloaded constructor here to create 10 integers and initialize them all to 100. Of course, the vector supports copy and move semantics for initialization and assignment. In the third example, I'm declaring stooges as a vector of std strings, and I'm initializing those strings with both std strings and C-style strings. Vectors also support assignment via an initializer list, just like we did with the std array. So let's look at some other methods provided by the vector. Again, please refer to the C++STL documentation for more detail on these and other methods. There's a lot there, and that's the place to look for information. But let's see some other methods. Let's start with size. This method returns the number of elements that are in the vector. That's pretty straightforward. The capacity method tells us the current capacity of the vector. When this capacity is exceeded, that's when the vector will expand dynamically. And max size tells us what the max size of a vector would be in our system, and that's the number of elements that it can hold. Usually this is a really large number. Vectors also let us access individual elements either using the subscript operator or the .at method. Just as we've seen before, the subscript operator does not do any bounds checking, and the .at method does. You can see in the example code that vec@0 will refer to the 1, and vec_1 will refer to the 2. As previously mentioned, the vector allows for efficiently inserting elements at the back of the vector. This is done with the pushback method. In this case, we have a vector of person objects. We can create a person P1 named Larry who's 18 years old, and we can use the pushback method to insert P1 at the back of the vector. Remember, all container classes make copies of the elements they store. So in this case, a copy of P1 is made. In the second example, we're creating an unnamed person object and adding it to the back of the vector using move semantics. The last method we haven't seen yet, and it's awesome. It's called emplaceBack. This method expects the parameters that would normally be passed into the person constructor. And that's what it does. It constructs the person object using a person constructor right in place where it's supposed to be in the vector. That's really efficient. No moves, no copies. It just puts it right where it's supposed to be. Use this method. It's awesome. The empty method will return true if the vector is empty and false otherwise. Just as we saw with std arrays, we can swap two vectors. But in the case of vectors, the vector elements have to be the same type, but the sizes can be different. And finally, we can use the sort algorithm and any other kind of algorithm to sort vectors with iterators to copy vectors. We'll see some of those examples in the IDE. So let's see how we can insert elements into a vector at a place other than the back. First, we'll create two vectors of integers, vec1 and vec2. Vec1 is 1, 2, 3, 4, 5, and vec2 is 10, 20, 30, 40, and 50. Now let's say we want to insert some data before the 3 in vec1. First, we need an iterator to point to the location of the vector where we want to insert the data before. In this case, the 3. We can use the find algorithm to easily find the 3, as we've already seen. Once the IT iterator is pointing to the 3 in the vec1, then we could call the insert method and pass in the iterator it and the element we want to insert before it, in this case the 10. That's it. Now vec1 contains 1, 2, 10, 3, 4, and 5. So we inserted the 10 before the 3. That was pretty easy, but we can also insert a sequence of elements. How? With iterators. Let's insert the entire contents of vec2 before the 4 in vec1. We first find the 4 and get an iterator to it. We'll call it IT. Then we can use the insert algorithm and pass in the iterator IT that we want to insert before, and the two iterators that will provide the sequence of elements from vec2 that we want to insert. In this case, all of vec2. That's it. Now vec1 will be 1, 2, 10, 3, 10, 20, 30, 40, 50, 4, and 5. We inserted a copy of vec2 before the 4. Very powerful and easy to do. All right, so let's head over to the IDE. We'll see these examples and we'll see some more complex examples as well. Okay, so I'm back in the IDE. I'm in the section 20 workspace in the vector project. And this project has a lot of examples. I really believe that the best way to learn the STL is through examples, a real example-driven approach. Make it a little boring sometimes as I'm giving you example after example after example, but I think it's really the best way to learn it. I've got a lot of examples here. I'm going to go through them pretty quickly, so please feel free to pause the video, look at the example, and then continue again. Let's get started. I'm including IOStream, vector, and algorithm. Obviously, I'm going to use vectors in this example, and we're going to use some algorithms as well. And I'm going to use integers mostly, but I'm going to use this person class in a few places. It's the same kind of person class we've used before. A person has a name and an age. It's a string and an integer. I've also overloaded the stream insertion operator just to make life easier. I've got a default constructor. I've got an overloaded constructor. And remember, when we're using our own classes with the STL, always overload less than and the equality operator. Okay, those are the two Boolean operators that are being used by the STL on your own objects. So that's it. I'm comparing two people, and I'm comparing whether one is less than the other. I'm not really using them in this demo, but it's a good habit to do. As far as the operator, the insertion operator, it's right here, same as we've always done. And then what I did was I created these two display functions. One is called display2, and one is just called display. I'm going to use display mostly, but I'm going to use display2. And the reason I did display2, just so you can see a different way to write this. Of course, I could use a range-based for loop to do this, and I'm doing that right here. But I wanted you to see the for each algorithm. We've seen this before as well. So give me a vector of integers, and I'm going to do for each. What's my sequence from the beginning to the end of the vector that was passed in? So in other words, the entire vector. At each iteration, this lambda expression is going to be called. X will be passed into it. X will be each one of those elements in that sequence. And all I'm doing is just displaying it. So it's really the same effect as a range-based for loop. This function here I wrote as a template function because sometimes I want to be able to print vectors of integers. Other times I want to be able to print vectors of persons. So it's nice just to have one function to let you do it. Here's my template parameter right here, t, so I can pass in a vector of anything. And I can loop through here using my range-based for loop, and the auto takes care of figuring out the type for me. So it makes life really easy. Okay, so let's start going through these examples. The first few are going to be really straightforward. I'm sure you've seen them before. What I've done is I've already run this, and the output is over here on the right side. You can see here in the console. But what we'll do is we'll go through these examples, and then we'll look at the console. And like I said, the first few are really straightforward. So let's look at this first one. I've got vec as a vector of integers, and I'm initializing it to 1, 2, 3, 4, and 5. And I'm calling that display function. That's the template function. It's going to display the vector, and you can see the vector being displayed right up here, 1, 2, 3, 4, and 5. Now what I'm doing is, remember, vector has already been initialized. So right now I'm using assignment. This is assignment using an initialization of this, which is really cool and handy. So now vec is 2, 4, 5, 6, and I'm displaying it using that other display function. So here I'm displaying vec again, and you can see vec is now 2, 4, 5, 6. And then in this case, I'm creating vec1. It's an object, and it's also a vector of integers, but I'm not using the curlies here, right? So I'm not using an initialization list. I'm using an overloaded constructor that's part of the vector class. This tells me how many do I want. This tells me what is each one going to be. So this is going to create 10 100s. And on a display vec1, you can see them right up here, all 10 100s. There are other constructors. There's a lot of different ways to do that. Refer to the documentation. Some of them are real interesting. These are the ones that I use all the time. Okay, so now let's look at test 2. Test 2 is all about the size, the capacity, so we understand how this works. So what I'm doing here is I'm saying vec is, again, a vector of integers, 1, 2, 3, 4, 5. I'm displaying it. You can see it's displaying right here. Then I'm asking what's the size of the vector, what's the max size of the vector, and what's the capacity of the vector. So you can see here the size is 5. I've got 5 elements in there right now. The max size is a really big number. That's how many elements that vector can hold. And the capacity is 5 in this case. What does that mean? That means that if I exceed that capacity, this vector will increase in size, right? In other words, the STL is going to allocate space for a larger vector. Remember, it's all contiguous in memory, and copy stuff into it. So that's exactly what I'm going to force right now. I'm going to push back 6. So I'm going to add 6 to the back of this vector. It's going to be a 6 right in there now. Then I'm going to display it again, and then display the size, max size, and capacity. We would expect max size not to change right now because I'm not doing anything else. So I'm pushing it back and displaying it. So right here, you can see the 6 at the end here. What's the size of the vector? 6. Max size is the same. But look at the vec's capacity here. Now it's 10. This is pretty typical. Whenever you exceed the capacity, what it'll do, it'll double. So the next time the capacity will be 20, and then 40, and then 80, and so forth. That's very, very typical behavior. Keep that in mind, because if you've got 10,000 elements in here, and you add that 10,001, it's going to go to 20,000 big when you only maybe need 10,000 and a little bit. So there's ways to help that. And I'll show you a couple. We've got this method called shrink to fit, which is pretty cool. And this just came about in C++11. So if I call shrink to fit, it'll shrink the amount of storage allocated to exactly the vector size. Okay, so remember, right now we had capacity 10. Then I called shrink to fit, and I'm displaying it again, and you can see what's happening here. Notice that now the capacity is exactly 6. There's one more method I wanted to talk about. We don't use it very often, but it's nice to know that it's there. It's reserve 100. What you're doing here is you're reserving 100 spaces for elements, contiguous in memory. And I'm displaying this memory, this vector again here. And you can see right here, the only difference is right there. This vector now has a capacity of 100, so it won't expand until it hits that 101 element. All right, so now let's take a look at test 3. I'll scroll both of these up. Again, I've got my vec 1, 2, 3, 4, 5. I'm displaying it, so you can see it displaying right here. And here all I'm doing is using the subscript operator and the .at method. Remember, the subscript operator does no bounds checking. The at method does do bounds checking, so if we exceed the bounds, we get an exception. So all I'm doing is I'm putting 100 here, and I'm putting 200 here, and I'm displaying the vector, and you can see that's exactly what we expect. So let's move on to test 4. And again, I know these are a lot of examples, but after doing this for many, many years, I think this is the best way to really learn this. For test 4, we've created stooges is a vector of person objects. Remember, we created that person class earlier. P1 is Larry, and he's 18. That's a person. Let's display stooges. Right now, it should be empty. Right there, it is empty. Now I'm going to push back P1. That's Larry, and display it again. So now you can see that the stooges vector has just one person in it, Larry. In this case, I'm going to push back Mo. Mo is 25. I'm not creating a named object here, so this is going to use move semantics, and it's going to push it in the back. When I display again, you can see that now I've got Larry and Mo. And then the last example, I'm using the emplace back, and this is awesome, as I said in these slides. What we do here is we pass in the arguments that we would have passed into a constructor. You can see right here, right? The name and the age. And what it's going to do behind the scenes is actually call the constructor for us and put curly at the back. And then when I display again, you can see now I've got Larry, Mo, and curly. Let's move on to test 5. In this case, I've got the stooges vector again right here. And I've initialized it to Larry, Mo, and curly. And I'm displaying it. And you can see it displaying right there. You can see Larry, Mo, and curly being displayed. We can have the front method and we have a back method. The front method returns a reference to the front element of the vector, the back to the back element. Well, the front one is Larry and the back one is curly. Here you can see front and back. So when we display that, we can see front is Larry, back is curly. We also have the pop back, and it removes the element from the back of the vector. For vectors, when we insert and delete from the back, it's very, very efficient. And that's typically how we use vectors. So we're going to get rid of curly in this case and then display the stooges. And you can see here, Larry and Mo are there, curly's gone. So here in test 6, there's my vector of integers, 1, 2, 3, 4, 5, and I'm displaying it right there. I can use the clear method to get rid of everything in the vector. So I just removed everything and I'm displaying the vector right here. It's empty. I'm assigning those 10 integers to the vector and displaying it again. You can see that being displayed right over here. And now what I want to do is I want to use the erase method to erase a piece of this vector. So I'm going to say vec.erase. And where do I want to start? At the beginning. Where do I want to stop? Right before that guy, vec begin plus 2. So here's vec begin. Here's vec begin plus 2. So what it's going to do is it's going to get rid of those two elements. And then when I display, you can see right here, the 1 and the 2 are gone. Great. Now, this example is a little bit more complicated, but it's really straightforward as well. And I'm just using a while loop here. I'm assigning 1 through 10 to the vec again. And then I'm getting an iterator to the beginning of it. And I'm calling it IT. And all I'm doing is moving along that vector. And if I see an even number, I'm deleting it or erasing it. So in this case, while IT is not equal to vec end, if what I'm pointing to with the iterator is even, then I'm erasing it. Now, I don't want to increase the iterator here, right? Because I just erased it, so that would kind of skip items. Otherwise, I do want to increase the iterator because I didn't see an even number. And then when I'm done, I just want to display vec, and you can see right there, vectors, even numbers are all gone. For test 7, we've got 2 vectors, and all we're going to do is swap them. So here's vec1, here's vec2. I'm displaying both of them, and you can see them right here. Then I'm just saying vec2 swap vec1, and I'm displaying those two again, and you can see that they've swapped. What's cool about vectors is they both have to be the same type in this example, but they can be different sizes, so it's a little different from the std array that we saw. In test 8, what we're doing is we're sorting. So we've got a vector of a bunch of integers. They are unsorted. I'm displaying that guy right here. You can see test right over here, test 8. So that's displaying the vector. I'm calling the sort algorithm, vec1.begin, vec1.end are my iterators, so the whole vector. And I'm displaying it again, and it's sorted. We can use reverse to sort it in reverse. Let's take a look at this one. This one's really cool. This is one of my, let me spell that right here, instructs. This is one of my favorite inserters to use. It's called a back inserter. So let me show you what's going on here. What we want to do is we've got vec1, which is 1, 2, 3, 4, and 5, and we've got vec2, which is 10 and 20. So what I want to do is I want to basically insert 1, 2, 3, 4, and 5 right after the 10 and 20. Now we can do this a whole bunch of different ways, but I wanted to show you the back inserter because it's a really, really cool inserter to use. First thing we do is let's display the 2 vectors, vec1 and vec2. Remember, we're in test 9, so we're right here. We've just displayed them. Now I'm going to use the copy algorithm. What am I going to copy? Well, I'm going to copy vec1 from vec1 begin to vec1 end. So I'm copying the entire vector 1. But where am I copying it to? Vector 2. And I'm using this guy right here, which is a really cool output iterator called back inserter. And what it'll do is it'll insert everything that's passed into it based on vec2. So what it's going to do, remember, the sequence we're going to get is every integer in vec1 here. That's what we're saying. Each one of those is going to be passed into the back inserter, and it's going to insert into the back of vec2. So when I display vec1 and vec2 again, look what happened right here. See the 10 and the 20? And now you see the 1, 2, 3, 4, and 5? This is really cool. Let's do the same thing now, except let's only copy if the elements are even. So in order to do that, we can start from scratch right here. So here's my vec1 and vec2. I'm displaying both of them. You can see them being displayed right here. And then I'm saying copy if. This is a little different from copy. This has a predicate. So I'm going to copy from vec1 begin to vec2. So sorry, let me say that again. I'm going to copy from vec1 begin to vec1 end. That's where I'm copying from. In other words, the entire vector 1. And I'm copying it to vector 2 using this back inserter. Now, what do I want to copy? That's where the predicate comes in. And we're doing it with a lambda. So what does that say? Even only, right? Mod 2 is 0. So even only. And then I'm displaying these 2 guys again. You can see right here, I'm displaying vec1 hasn't changed, but look at vec2. It had a 10 and a 20, but now it has the 2, the 4, the 6, the 8, and the 10 that came from vec1. These 2 guys, the back inserter and the copy and copy if, really get to know those things. And if you're ever in a technical interview or a job interview and you're asked one of these questions, blow the person away by using this. You'll get the job. Trust me. I do that all the time. There's just a couple left here. Test 10 is a real interesting one. We're going to use the transform algorithm right here. And the idea here is I've got these 2 vectors and I want to transform over both ranges. So what I want to do is I want to transform over the ranges. So I want the 1 and the 10 and the 2 and the 20 and the 3 and the 30 and the 4 and the 40 and the 5 and the 50 being handled at the same time. So this is what's going on here. I'm using transform and I'm starting at vec1.begin and I'm going all the way to the end of vec1. And I'm just starting at vec2 begin. You don't have to say the end here because it's only going to do this 5 times. This guy could be really long. So what's going to happen? Well, I'm going to use my back inserter and insert the results of this into vec3, which is empty. But what am I inserting? Well, that's the really cool part. This is going to be called, this lambda here will be called with both the 1 and the 10, the 2 and the 20. So that would be X and Y. And all I'm doing is multiplying them. And then I'm putting those back into vec3 using this back inserter. So when I display vec3, you can see right here, this is test 10. Check it out. 10, 40, 90, 160, 250. What is that? Well, that's 1 times 10 is 10. 2 times 20 is 40. 3 times 30 is 90. You can see what's happening here. This is really, really neat. We actually did a challenge that was similar to this when we did arrays way back when. You could tweak that to make this like a one-liner. It's not exactly the same, but you can certainly get it to work that way. All right, and the last one is inserting, and that would be test 11, and that's where we're at right here. We've got vec1 and vec2. Vec1 is 1 through 10, and vec2 is 100, 200, 300, and 400. And what do we want to do? We want to insert the contents of vec2 into vec1 before that 5 right here. So here I'm displaying the two vectors. You can see them right here, just as we would expect. So how do I do this? Well, I have to use an iterator to do this. And remember, it's not as efficient to insert things into the center of a vector as it is on the back of the vector. Back is really efficient. So what I'm doing here is I'm finding that 5 in vec1, right? Begin end, the entire vector. I'm finding the 5 and I get back an iterator. If the iterator is not equal to the end, I found the 5. Otherwise, I display this. So in this case, I did find the 5 and I'm outputting inserting. You can see that right here. And then what I'm calling is I'm calling vec1.insert. I'm passing in the iterator and I'm passing the sequence of elements I want to insert the entire vec2. So what that's going to do is it's going to insert all of vec2 before the 5. And you can see right here, 1, 2, 3, 4. Then there's vec2 and then 5, 6, 7, 8, 9, and 10. So that covers this lecture. There's a lot here to understand. Please take your time going through this. Pause the video, go back, try some examples, make these your own, and really learn from this. That's the best way to do it. In this video, we'll learn more about the STL deck container. In order to use the deck, we must pound include the deck header file. The deck acts like a double-ended queue. The deck size is dynamic and it's handled by the STL, so that's very much like a vector. But unlike a vector, the elements in the deck are not stored in contiguous memory. The deck allows direct element access using the subscript operator and the .at method. But unlike a vector that allows efficient insertion and deletion only at the back, the deck allows efficient insertion and deletion at the back and at the front. However, inserting elements into any other part of the deck other than the front or back is not as efficient. The deck supports all of the iterators, and the iterators may become invalid again, especially when the deck changes size. Let's first look at a few ways to initialize decks, and then we'll see some of its member methods. In the first example in this slide, I declared D as a deck of integers and initialized it to 1, 2, 3, 4, and 5. In the second example, I declared D1 as a deck of integers, and I'm using an overloaded constructor to create 10 integers and initialize them all to 100. Of course, like all the STL containers, the deck supports copy and move semantics for initialization and assignment. In the third example, I'm declaring Stooges as a deck of std strings, and I'm initializing it to Larry, Mo, and Curly. Now notice that Mo is a C-style string. Like vectors and std arrays, decks also support assignment via initializer list. So let's see some common methods provided by the deck container. In this slide, we'll see what a simple deck looks like. We declare D as a deck of integers, and we initialize it to 1, 2, 3. The deck has a front and a back. The front in this case is the element 1, and the back is element 3. With a deck, we can efficiently add elements and remove elements from both the front and the back. In a deck, the pushback method works very much as it does in a vector. The element to be added is pushed at the back of the deck. And the push front method adds the element to be inserted at the front of the deck. Now let's see how the elements in the deck might be stored in memory. Remember, the deck's elements are not in contiguous memory. So usually a deck is implemented as a collection of memory blocks, and these memory blocks contain elements that are in a contiguous memory. but the blocks themselves are not in contiguous memory. So a good way to think of a deck is as a linked list of vectors. So when we add an element at the front, it adds it if there's space. If not, it will allocate a new block, add the element to that block, and then link in the block. The same happens when we add an element at the back. Again, please refer to the C++STL documentation for details on all of the methods for the deck. There's a lot there, and that's the place to go to. The documentation is your friend. Don't think programmers keep all these details in our heads. We don't. We refer to the C++ docs very often. Generally, it's open on a second monitor. It's the same for Java programmers. Usually, they've got the Java docs open on a second monitor, and that's where all the good information is. So, let's see some of these methods. Let's start with the size method. This method returns the number of elements that are in the deck. The max size we've already seen with vectors and std arrays. It's a pretty big number that just says, how many elements can I store? Decks also allow individual access using either the subscript operator or the .at method, and the rules are the same here. If you use the subscript operator, no bounds checking is done, but if you use the .at method, bounds checking will happen and an exception will be thrown if you're out of bounds. In this case, you can see that I'm using d.at0. That refers to the 1 in the deck D, and d sub 1 refers to the 2. The deck also provides front and back methods that return references to the elements at the front of the deck and at the back of the deck. So in this example, d.front refers to the 1 and d.back refers to the 5. As I previously mentioned, the deck allows for efficiently inserting and removing elements at the front and at the back. Inserting is done with the pushback method and the push front method. We also have a pop back and a pop front, which efficiently remove elements from the back of the front. In this slide, we have a deck of person objects and we called it D. We can create a person P1 named Larry, who's 18 years old. And we can use the push back method to insert P1 at the back of the deck. We can also remove it using pop back. Similarly, we can add a person object to the front of the deck with push front and remove it with pop front. Remember, all container classes make copies of the elements they store. The deck container also supports in-place front and in-place back, which are super efficient ways to create and initialize objects and store them in the deck right in place. So now let's head over to the IDE. We'll see some examples, and then in the video after that, we'll have some challenge exercises that use decks. Okay, so I'm in the IDE. I'm in the section 20 workspace in the deck project. And this is a really simple example. The idea behind using a deck is that we're going to use the front of it or the back of it. We're not really going to be inserting things into the middle of it. If you need to do that kind of thing, you're probably better off using a list. We'll talk about the lists later. So I'm not going to go into any of the fancy stuff where you can insert things into the middle of a deck. I'm just going to keep it really simple because that's usually the way we use a deck. So let's start with looking at what we've got here. We're including a deck, a vector, and an algorithm. We're using the vector in a minute just to do a little simple example. And here I've got my display function that will display any type of deck. I'm only using decks of integers in this example, but it's nice to have this template function. You can play around with it and practice writing these actually. This is a really, really easy one to write. I went over this one in the previous video, the video for vectors. Okay, so let's take a look at test one. I've already run the program. The output is over here on the right in the console. And let's walk through these tests so you can understand what's happening here. So this is test one right here. You can see the output of test one right up here. First thing we're doing is we're declaring D as a deck of integers, and we're putting 1 to 5 in there, and then we're displaying the deck. So there it is right here, just as we would expect. Then I've got an assignment. I'm using the initializer list to assign, which again is really handy. So now D is 2, 4, 5, 6, and I'm displaying that. You can see 2, 4, 5, 6 right here. Now, just like we did with the vector, here I'm creating 10 100s, and I'm putting them in the deck and displaying them. You can see all 10 hundreds right here. And the last thing is right here. We're doing direct access to the deck. You don't often do this with a deck. Remember, the whole point of a deck is to be a doubly ended queue. So you're going to work on the front and you're going to work at the back. That's the idea. But it lets you have random access to the elements within it at in constant time, which is cool. So D sub 0 with the index operator this is D now. So it's going to put 100 in here. And D at 1 we'll put 200 in there. And when we display that, you can see right here, the 100 and the 200 replaced the 1 and the 2. All right, so that's pretty straightforward. Let's look at test 2. Test 2 is the real workhorse here. This is the way you typically use a deck. We're using push back and push front and pop back and so forth. So let's go over this one because these are the methods that you're going to really use a lot with the deck. So what I'm doing here is creating a deck called D again of integers, and it's 0, 0, 0. And the reason I put 0, 0, 0 in there is just so we can have these 3 zeros in the center. That way we can really understand how things are being pushed in. And we're displaying it. You can see right there the 3 zeros. Now we're saying push back a 10 and then push back a 20. That means at the back. So first I push back the 10 and then the 20. Remember, they're being pushed back this way. And display them, and you can see what we've got. 3 zeros, 10 and a 20. Now I want to push front. So now I'm going to push these guys at the front, 100, and then I push 200. So I'm pushing them this way. And I'm displaying it again. And I've got right here, 200, 100, the 3 zeros, and then the 10 and the 20, of course, are still there. We've got our front method, which returns a reference to the front element, which in this case is that guy right here. I've got my back method, which returns a reference to the back element, which is the 20 right here, and the size, which is 7. So when we look at the output right here, you can see the front is 200, the back is 20, and the size is 7, and we display it right after we pop a few things off it. So let's try that. So first thing we do is we pop the back, that guy's gone, and then we pop the front, that guy's gone, and we display it again. So now we're going to display 100, 0, 0, 0, 10. Notice how the 200 and the 20 are gone. So this is really the way you're going to use the deck. If you find yourself using a deck and fiddling around with the middle elements and inserting things into the middle and doing all kinds of stuff like that, maybe the deck is not what you should be using. Consider using a list, and we'll talk about a list in the next section of the course. Okay, so that takes care of test 2. Let's take a look at test 3. And what I've got here in test 3, this is what I want to do. I've got a vector of 10 integers right here, 1 through 10. And I've got a deck D, which is empty. And what I want to do is I want to insert all the even numbers into the back of the deck and all the odd numbers into the front. It's pretty easy to do. I could just use a range-based for loop right here, and I can iterate over that vector. Remember, we're coming from a vector to a deck this time. And if the element mod 2 is 0, that means it is even. And if it's even, I'm pushing it onto the back. Right? So where we start, we're starting with the number is even, we're pushing it in the back. The number is odd, we're pushing it into the front. So we're going to have the 1, the 2, the 3, the 4, the 5, the 6. This is what's going to happen. The 8, the 9, and the 10. That's the result right there. And when we look at the display for test 3, right here, that's exactly what we've got. We've got all the odd numbers here and all the even numbers right there. Now, let's take a look at test 4. Test 4 is simple, but important. It shows you the ordering of things. When we push stuff on the front versus we push stuff on the back, the ordering is obviously different, but this confuses people sometimes. And I've seen a lot of little mistakes from programmers that use decks this way, and it comes up a lot in code reviews. So let's take a look. Here we've got a vector again, 1 through 10. And what I'm doing is I'm going through the entire vector this time. There's no if statement. There's no odd even stuff. That's all I'm doing is I'm going through that vector and I'm grabbing each element and I'm pushing it in the front. So we're starting at the 1. So we're pushing it 1, 2, 3, 4, 5. Remember, we're pushing things on the front. So this is the result. That's a 9 right there. That's the result. So when I display this, and again, I'm in test 4, you can see it's 10, 9, 8 all the way down to 1. I'm going to clear the deck here. Then I'm going to do the same thing, except now I'm going to push back. This time we're pushing this way, right? So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And when we display that, you can see that that's exactly what we get. Obviously, the order is going to be different, right? One's going to be going from 1 to 10, the other from 10 to 1, depending on whether we do a push front or a push back. And as I said, this sounds simple, but I've seen a lot of little mistakes using this because somehow people get confused. Let's take a look at the last test, test 5. So what we're going to do now is we're going to do the same thing we did in test 4, except we're going to use copy to do it. So what do we have? We have the same vector and we have a deck that's empty again. And what we're going to do is we're simply going to copy everything in the vector from begin to end, and we're going to use the front inserter iterator to do it. So one line of code handles this really, really easily. So again, loop through the vector, the entire vector, and for each element in that vector, insert it to the front of the deck, D. So this is test 5. When we display that, this is what we get right here. Notice it's the same as test 4 because we're inserting at the front. And we can clear the deck and do it again. So copy vec.begin to vec.end, and this time we're going to do the back inserter. We're inserting at the back this way. And what we're going to get is the same thing we got with test 4. So which should you use? I tend to like this. This is much more expressive. Most programmers will understand this. A lot of programmers are not real familiar with the STL algorithms. So this kind of code right here is foreign to them, and they could really mess things up, especially junior programmers. Junior programmers, the STL is a complicated beast, and a lot of junior programmers just know the very basics of it. So when you get a lot of algorithms put together with iterators and inserters, it's likely a lot of the junior programmers haven't seen that. So there you go. That's it. So that takes care of the deck. In the next video, we'll do the first challenge for the deck. Hello, welcome to the first challenge of the STL section of the course. Now, I didn't give you any vector challenges because you've done quite a lot of vector challenges in the course. So we're going to start with a deck, and I know a deck is new to most of you. So I'm in the section 20 workspace, and here you can see the challenge_1 project and the challenge_1 solution project. The solution project obviously has my solution to this problem, and the challenge_1 has the source code to get you started. So let's talk about the challenge. The challenge is all about using a deck. So we know what a palindrome is. Some of you may not know what a palindrome is. A palindrome is a string that reads the same backwards or forwards. So a simple example is madam, bob, toot, radar, and there's very many, many more. So these are words that read the same forward or backwards. Now we can have entire phrases can be palindromes. For example, a Toyota's a Toyota, a Santa at NASA, a man, a plan, a cat, a ham, a yak, a yam, a hat, a canal, Panama. All these are great examples of entire phrases that are palindromes. For the purposes of this assignment, we're only going to consider alpha characters. We're going to omit everything else. So spaces, commas, exclamation points, and so forth, apostrophes as we see here, will all be eliminated or omitted. So when we read something like a Santa at NASA, what we're going to convert that to is a Santa at NASA, like that. All uppercase, and get rid of all the special characters. And obviously you know what to use. You can use the CC type header file for that. So how do you solve this problem? Well, a common method to solve the problem is to process the string. You end up with something like that. And then you reverse that string and you compare the two strings. Obviously, if the two strings are the same, right, the one that's normal and the one reversed, then it must be a palindrome. But we're not going to do it that way. We're going to use a deck. I'm providing a main driver for you that'll automatically run a bunch of test cases. And your challenge is to write one function. The function is called isPalindrome. It returns a true/false value and it expects a string. So I'm going to send you a string and you're going to return true or false. The function, as I said, determines whether that string is a palindrome. That function must take care of removing any spaces and any special characters. So here's a couple of examples. Is palindrome a Santa at NASA? That will return true. Is palindrome hello? Should return false because hello is not a palindrome. All right, and what I'd like you to do is to use a deck to solve the problem. After all, that's the section we're in, the STL section, and the deck is a perfect container to help us solve this. If you need a hint, please post something in the Q&A forum. This is a very common question that's used in coding interviews. And a lot of times they'll start the coding interview with solve this problem. The majority of the applicants will try to come up with the string, reverse it, and compare. And at that point, the interviewer will say, could you use a data structure like a deck to do it? And that gets a lot of people because all the books show you how to do it with reversing the string. But it's interesting to do it with a deck. Let me run my solution so you can see the sample output. And here's the sample output. I've got a result. And I've got the string. So in this case, you can see the lowercase letter a is true AA is true, ABA is true, ABBA is true. These are all palindromes, but obviously the AB is not a palindrome, nor is the ABC. Radar and Bob and Anna are, as are all these more complicated phrases. Even C++ is, right? Once we get rid of the plus plus, we're left with a C. That's definitely a palindrome. Okay, so there's your test cases. Let me show you what your main would look like. And this is the code that I'm providing for you. This is the function you have to write right here. It's called isPalindrome, expects a stood string, returns a Boolean. Right now I'm just returning false. You have to write this. And here's the main. I've got a vector of a bunch of strings, and these strings are my test cases. And that's it. You shouldn't have to do anything in the main. The main is basically going to loop through all of these strings and call the isPalindrome method right there, pass the string into it. You'll return true and false, and the main will display it. So your job is to implement this function right here. Remember, use a deck. Okay? So have fun. Think about it. It's actually a pretty simple problem, and don't go crazy with iterators. You don't have to use any of that stuff. Just use the front and the back of the deck. That's what it's all about. And when you're done, you can come over to Challenge 1 Solution and meet me in the next video. Okay, so welcome back to the STL Challenge 1 Solution. I'm in section 20, and I'm in the Challenge 1 Solution project. And this is the project where we had to write the isPalindrome function. So hopefully you were able to solve this problem. It's actually quite simple when you think about it, but so let's talk about it. The idea is we're going to use a deck. So the idea is, let's say that we have a string like AABAA. That's obviously a palindrome, right? It reads the same from the front or from the back. So and that's coming in here as my string. So what I want to do is I want to create this deck of characters right here. And I just want to push these characters in to the deck. So I'm going to grab that and I'm going to push back. So I'm going to basically create a deck that looks like this. I'm going to push the characters onto the deck. And then what I'm going to do is I'm going to check the front of the deck and I'm going to check the back of the deck. Grab whatever's there, compare them. If they are the same, then I process them, remove them, and move on to the next ones. Right? Compare them. If they're the same, I'm going to remove them. At that point, if I end up with an empty deck or a deck with just one item in it, then I know it's a palindrome. It's as simple as that. For something like, let's say, 4. So I'm going to grab that string, put it into the deck. I'm going to grab the first character here in the front. I'm going to grab the last character here in the back. They are not equal. So there's no way this can be a palindrome. So I'm out right there. Okay, so let's walk through the actual code. So now you know the algorithm's pretty straightforward. So let's look at the code right here. Here's the isPalindrome function. And I've got a deck, and I'm initializing it to an empty deck. I'm just calling it D. Then for each character in this string S, if the character is an alpha, right? So in other words, it's not white space, it's not a digit, it's not special characters. So if it is alpha, then what I'm going to do is I'm going to convert it to uppercase and push it onto the deck in the back. That's it. So once this loop is done, whatever was in this string is now in the deck, minus the special characters and the white space and everything else. That's it. Now I've got two variables here, C1 and C2. Those are the variables that I'm using to store what I'm reading from the front and from the back of the deck. And now I'm going to do something right here. This is my loop. It's really simple. While the size of the deck is greater than 1, then I want to keep processing. Once I hit 0 or 1, I'm done, right? It's got to be a palindrome. So I'm asking the deck, hey, give me your front element, give me your back element. And I'm storing those in C1 and C2. I'm getting rid of those two elements from the deck. I don't need them there. And then I'm comparing them. So if C1 is not equal to C2, then the characters can't be the same. There's no way this can be a palindrome, so I'm returning false immediately. If I get through the loop, I'm returning true. It's got to be a palindrome. So that's it. That's the solution. And as I said, this is a very common problem given in a coding interview. And what the interviewer wants is for the applicant to try to solve it a different way and then say, oh, by the way, can you solve it using a deck? And that's it. So you can see it's a real simple solution. No iterators, nothing fancy, no algorithms. They're just using the front and the back of the deck, just like we're supposed to. All right, so I hope you enjoyed this challenge. In this video, we'll learn more about the STL list and forward list containers. These are both sequence containers and store their elements in non-contiguous memory. They don't provide direct access to elements via the .at method or subscript operator, but they're very efficient when we need to insert and delete elements in the list once an element is found. Let's first talk about the list, and then we'll talk about the forward list after. In order to use the list container, we have to include the list header file. The list acts as a doubly linked list of elements, so we can go from element to element in either direction. Remember, lists do not support direct element access. The list has a front and a back, and we can use all of the iterators, but the iterators may become invalid when deleting elements. So let's see what a doubly linked list looks like conceptually. In this slide, we see a diagram of what a simple list looks like. Notice that the elements are not contiguous in memory. An element has a reference to the element after it and before it if they exist. That's why it's referred to as a doubly linked list. So there is some overhead involved with maintaining these links. We declare L as a list of integers and initialize it to 1, 2, and 3. The list has a front and a back. The front in this case is the element 1 and the back is the element 3. With a list, we can efficiently add and remove elements from the front and the back, and we can also efficiently remove and insert elements from anywhere in the list. All we really have to do is remove or insert the element and then relink the links to the other elements around it. Inserting and removing elements other than at the ends is very efficient, but in order to do that, we need to have an iterator to the element that we want to remove or insert before. This is usually done with the find method, and it's done in linear time. If you need a container where you will have lots of insertions and removals from the container, and you don't need direct access to the elements, then the list is a good choice. In the first example in this slide, I declared L as a list of integers and initialized it to 1, 2, 3, and 4. In the second example, I declared L1 as a list of integers, and I'm using an overloaded constructor to create 10 integers and initialize them all to 100. In the third example, I'm declaring stooges as a list of strings, and initializing them with stood strings and C-style strings. Like vectors, stood arrays, and decs, lists also support assignment via initializer list. So let's see some other common methods provided by the list. Let's start with the size method. This method returns the number of elements that are in the list. And max size tells us what the maximum number of elements a list can contain. Remember, lists do not allow direct access to elements, so we can't use a subscript operator or the .at method. These are not available for lists. The list also provides front and back methods that return references to the element at the front and the element at the back of the list. In this example, L.front refers to 1 and L.back refers to the 5. The list allows for efficiently inserting elements at the back and at the front. This is done with the pushback method and the pushFront method. We can also have popback and popFront, which efficiently remove elements from the back or the front. In this slide, we have a list of person objects called L. We can create a person, P1, named Larry, who's 18 years old, and we can use the pushback method to insert P1 at the back of the list. We can also remove it using popback. Similarly, we can add a person object to the front of the list with pushFront and remove it with popFront. The list container also supports InPlaceFront and InPlaceBack, which are efficient ways to create and initialize objects that we want to store in the list right in place. Inserting elements into a list works a little differently from what we've seen with other containers. We can insert an element before an existing element using the insert method, but the insert method expects an iterator that's referencing the element we want to insert before. In this example, L is a list of ints, and I initialized L to 1, 2, 3, 4, and 5. Now I need an iterator to point to an element in the list. We can do this lots of ways, but let's use the find function. We can call find with L.begin, L.end, and we're looking for the 3. In this case, the iterator IT now is referencing the element 3 in the list. If we now call L.insert and pass in IT, which is the iterator, and the number we want to insert, in this case 10, the 10 will be inserted very efficiently before the 3. The iterator will not be invalidated. It still references the 3. Now if we call L.erase and pass in the iterator, the 3 will be removed from the list and the iterator will become invalid now. Lists also allow resizing. We can resize L to a size of 2, in which case all the elements after the second will be removed. If we resize to a value larger than what we currently have, the list will be expanded to that many elements, and the default initializer for the type of object the list contains will be called, and those elements stored in the newly created element. So in this case, if we resize L to 5, we'll add 3 new elements to the list, and they'll all be initialized to 0 in this case because they're integers. Finally, how do we traverse a list? We can use a range-based for loop, or we can use iterators. Since lists are bidirectional, we can iterate in both directions. So in this case, we have a list L initialized to the ints 1, 2, 3, 4, and 5, and we have an iterator it that will be referring to the 3. When we dereference it and display the element, we get a 3. When we dereference it and display the element, we get a 3. Then we can increment the iterator, and now it refers to the 4. We can display the 4 in the same way. Finally, we can decrement the iterator, and we get right back to the 3. Now let's see what some of the differences are between a list and a forward list. The forward list was added to the STL in C++11. In order to use the forward list, we must include the forward list header file. The forward list acts as a singly linked list, so the list can only be traversed in one direction. The forward list incurs less overhead than the list, but the downside is that we can only use it in one direction. But in many cases, this is exactly what we want. Similar to the list, the forward list allows for rapid insertion and deletion of elements once we have an iterator to one of the elements. Also, the forward list does not support direct element access. As we'll see in a moment, the forward list has no concept of back, only front. It doesn't make much sense to get to the back of a list and then not be able to traverse backwards, so it's not available. Obviously, reverse iterators make no sense either, so they're not supported. So let's see what a forward list might look like. In this slide, we see a diagram of what a simple forward list might look like. We declare L as a forward list of integers and initialize it to 1, 2, and 3. The forward list has only a front, no back. The front in this case is the element 1. With a forward list, we can efficiently add elements to the front using push front. You can see the pointers are going in only one direction. So let's see some of the common methods used with forward lists. Let's start with the size method. It's not available. There's an interesting discussion about why the decision was made to not provide a size method. If you're interested, let me know in the Q&A and we can talk about it. The max size will tell us the maximum number of elements the forward list can store. Also notice that we have a front method but no back method. In this case, the front method returns a reference to the element 1. Since the forward list only uses front and not back, we have push front, pop front, and in place front available for quick insertion of elements at the front of the forward list. So since the forward list is a singly linked list, it makes sense to insert elements into the forward list after an iterator reference. So the forward list supports methods named explicitly like what they do. In this example, L is a forward list of the integers 1, 2, 3, 4, 5. And we have an iterator it that points to the 3. We can now use L.InsertAfter and pass in the iterator and the object we want to insert. In this case, the 10 will be inserted after the 3. Notice that there are no insert and place erase methods. They're all called insert after and place after, erase after. The iterator doesn't invalidate in this case. It still points to the 3. So we can also use and place after and erase after in the same way. And the forward list allows resizing in the same way that the list does. Okay, so let's head over to the IDE and we'll see some examples using a list, and then we'll have a challenge exercise using a list. Okay, so I'm back in the IDE. I'm in the section 20 workspace and I'm in the list project. And what I'd like to do here is do the same thing we've been doing in the previous videos, go over some examples of using the list container. Now, there's a couple of differences here. One is I'm including this iterator header file here, and that's for this advance function. I'll talk about that in a second. It basically allows us to advance an iterator. We can't really do a plus equals or minus equals on list iterators, but we can advance them using the advanced function. So I'll show you that when I get to it. We have the person class that we've had before. And in this case, the only difference from the person class that you've seen before is the default constructor. Before we just use the default, we let the compiler generate it for us. Here, I want the name to be unknown and I want the age to be 0 when nothing is provided. And you'll see why in a little bit. When we resize a list, it creates objects by using a default. And I want you to see that word and that age so you can actually see when that happens. Other than that, it's exactly the same. I've got the overloaded constructor here. I am overloading the less than operator and the equality operator. Those are the two real important operators for the STL. And I've got a friend insertion operator right here for a stream insertion. All right. I've got a template function right here that allows me to display any list of any type. So the template parameter is t, that's being replaced. Again, you've seen this before with dex and vectors, so it's just another example here with a list. So let's go through these examples. I've got some tests here, and I'll start with test 1. And you can see the output over here. As I said, I've already run this, so the test is right there. That's where we're at right now. Here we're creating a list of integers, and you can see the syntax is exactly as you would expect. I hope that by now you're seeing these patterns, right? And it's not like, oh my goodness, in order to use a list, I've got to learn all this new stuff. The patterns are the same. If you know how to use a deck, you know how to use a vector, you know how to use a list. It's just a matter of going to the STL documentation and see the nuances and the specifics for each container. But the general patterns are the same. So in this case, I'm creating L1 as 1, 2, 3, 4, 5, and I'm displaying it. You can see that being displayed right here. And now I'm creating L2 as a list of stood strings. And what I'm doing is I'm pushing back to the back and front to the front, and then I'm displaying it. You can see exactly what you'd expect. Remember, a list has a back and it's got a front. So we're taking advantage of that. It's very efficient inserting on both ends. Here I'm creating L3 as a list of integers, and I'm using the assignment using the initializer list, just like we've done with the other containers. And then I'm displaying L3, and you can see it right there. And then we're using the same constructor that we've used before. And again, I know this is becoming old hat, but I'm doing this. There's a method to my madness. I'm doing this on purpose so that you can see the consistency between all these containers. So that's the constructor. We've got 10 100s, and then we're displaying L4. There are the 10 100s. Okay, perfect. So let's move on to the second test. And that's right here. You can see the output right over here. In this case, I've got L as a list of integers from 1 through 10. I'm initializing it. I'm displaying it. There's the display right there. What's the list size? Well, it's 10. What's the front? The front is the 1. What's the back? The back is the 10. Remember, these are references we're getting to them, so we can actually change them if we like. There's the size is 10, the front and the back. We can clear the list. That removes all the elements from it and display it again. Now it's empty and its size is 0, as you can see right there. Okay, again, very, very consistent. So let's take a look at test 3. Now, test 3 has a couple of things that are going to be different for a list. Here's L, and we're displaying L, which is 1 through 10. You can see right here's test 3, and right there is the 1 through the 10. And now what we're saying is let's resize this to 5. So what happens here? Well, it's going to resize it to 5. Basically, it's going to stop it right here, and all this is gone. So at this point, if I display L, you can see 1, 2, 3, 4, 5 here in the output. Now, this is interesting. If I resize it to 10, what's going to happen? Well, it says, remember, right now it's 1, 2, 3, 4, and 5. So it's going to resize it to 5 new elements, 1, 2, 3, 4, 5. But what's it going to put in there? Well, what it's going to do is going to call the default initializer for each one of those objects. For integers and for primitive types, it's 0. So you're going to get something like that. And when I display it, that's exactly what we see, 1, 2, 3, 4, 5, and 5 zeros. But when we have object types, it's a whole different story. In this case, look what I'm doing. I've created persons is a list of person objects. Right now it's empty. But if I resize it to 5, now I've got 5 person objects. Which ones does it create? It uses the default constructor for them. So if I display it, you can see those strings that I talked about earlier in the person class. Unknown age 0, unknown age 0. It's exactly what's happening. This is one of the things that I talked about, I think, at the beginning of this section was it's very important when we use the STL that we overload the less than, that we overload the equality operator, that we overload the default constructor. This is why. This is a really important reason why. If we provide an overloaded constructor and we don't provide the default constructor, this will error out because the default constructor wouldn't be provided for us. So we've got to be sure that we've got all our bases covered there. Test 4, let's have a list here of integers 1 through 10 and display it. You can see test 4 is right down here. Actually, let me scroll that up just a little bit so it's a little easier to see. There we go. So here's test 4. Those are my integers 1 through 10. That's where I'm at right here. Now I've got an iterator. And obviously I'm using auto, but obviously if I had to declare that the long way, it would be stood list int iterator it. But in this case, the compiler is deducing it based on the return value of the find. So what am I doing? I'm finding that 5 in L from beginning to end. So my iterator it is going to be pointing to 5. Now I know it's there, but it's good practice to check. So if it is not equal to the end, that means I found it. And what I want to do is I want to call the insert method on the list L, and I want to insert 100 where I need the iterator. This is real important with lists, both list and forward list. So what do? I need that iterator. The iterator is pointing to the 5. In the case of a list, it's going to insert the 100 before the iterator. So it's going to stick the 100 right in there. And then when I display the list, you can see right here that the 100 has been inserted between the 4 and the 5, right to the left or previous or before the iterator, however you want to think about it. In this case, I've got L2, which is a list from 1,000, 2,000, 3,000. And now look what I'm doing. I'm inserting into L. Remember, L is this guy right here now. L is 1, 2, 3, 4, then 100. And then 5, 6, 7, 8, 9, and 10. That's L right here. So what I'm doing is and remember, my iterator is still pointing to the 5. It's not invalid because I haven't deleted it. So my iterator is still pointing right here. So what I want to do is I want to insert into L, starting at that iterator right here to the left of the iterator. What do I want to insert? I want to insert the entire list L2 from beginning to end. So what do you think that's going to do? Right in here, it's going to put in 1,000, 2,000, and 3,000. And it's going to do that super efficiently. Then when I display the list here again, you can see what's happening. 1, 2, 3, 4. There's your 100, and then 1,000, 2,000, 3,000, and then the 5. Where's iterator pointing to now? Still pointing to the 5. It's still valid. Okay, let me clear this because there's a lot of stuff here. And this is the advanced function that I was talking about. This is in the iterator header file. So what we can do here is we can advance any iterator, positive or negative, assuming it's a bidirectional iterator. In this case, it is. There's my iterator, and I want to advance it -4. So remember, iterator was pointing to the 5, right? So now the 5 is over here. I want to move it 4 to the left. 1, 2, 3, 4. It's going to be pointing to the 100. That's what the advance lets me do. I can also do +4, obviously, or +2, or anything I want. So in this case, it's going to be pointing to the 100. If I display what it's pointing to, there's the 100. And then I can say L.erase it. What's that going to do? It's going to erase the element that the iterator is pointing to. Then I'm displaying it again. You can see the 100 is gone. At this point, my iterator becomes invalid. I just deleted the element it was pointing to. So don't use that iterator again. If you need it, reset it. Okay, test 4 is good. Now let's take a look at test 5. In test 5, we'll do a couple of things. Test 5 just has a couple of pieces of input, and you'll see here it's actually waiting for me to type something in. So we'll do that in a second. In test 5, I've got stooges, which is a list of person objects, and I'm initializing it to Larry, Moe, and Curly, and I'm displaying them. Remember the person class overloaded the stream insertion operator, so that's what's happening here. And I'm displaying them. That's what I've got right here. Larry, Moe, and Curly. Now I've got a couple of variables here, name and age. And what I want to do is I want to ask the user to enter the name of the next stooge and then enter their age. And let's do that right now. I'm going to type in, right in here, I'm just going to type in James. And let's say that James is 50 years old. Now, when I press enter, what's going to happen is we're coming right in here on line 130 right here. And I'm in placing back. And remember here, I'm not creating an object here. I'm letting the list create the object for me. That's what the in-place does. So what's going to happen is James 50 is going to be passed into this method. this method will create that stooge object and insert it at the back for me. So when I press enter, I'll display stooges, and I should see James 50 at the back, right in here, right after curly. So let's do that. Let me come over here. I'll press enter, and you can see now that we've got Larry, Frank, Mo, Curly, and James right at the back. Super efficient. And then the last thing we want to do here is we want to insert Frank before Mo. Okay, so where's Mo? I need to find it. So I need an iterator that's going to point to Mo. I'm going to search stooges from beginning to end, and I'm looking for that object. Okay, what's it going to use? Operator, equality operator, which I've overloaded. So it's going to look for Mo 25. Mo 25 is right here. I know it's there. So my iterator, if it's not equal to stooges end, I found it. So what I'm going to do is I'm going to insert at that iterator, before the iterator. Everything on the list happens before the iterator. I'm going to insert Frank 18, and then I'm going to display stooges again. And you can see right here, Frank 18 is right before the Mo, which is exactly like I expected. All right, and then the last test is test 6. And this one's pretty cool. All we're doing is sorting. Real simple. So in this case, I've got stooges is a list of persons, and I've got Larry, Mo, and Curly. I'm displaying stooges, and you can see it right here, Larry, Mo, and Curly. Then I'm sorting it. I'm saying stooges.sort, and then I'm displaying it again. And look what happened. Curly, Larry, Mo. What operator is being used here? Operator less than. We overloaded that. And what we're doing in our operator less than, let me go back in case you don't remember. Look at our operator less than. It's comparing ages. So here we've got 17, 18, and 25. That's how we decided that we were going to sort. Right? We're not sorting by name. We could have written this as name, but we decided, oh, well, let's sort by age. So this is going to sort by that. Okay, so that's it. In the next video, we'll do a challenge where we'll simulate a music player using a doubly linked list. Hello and welcome to the Section 20 second challenge. This challenge is all about using a stood list, a doubly linked list. What we're going to do in this challenge is we're going to simulate a playlist. So imagine you've got a CD and you want to put it in your car, and you want to play it and move to the next song, and the previous song, and the beginning, and so forth. We're also going to be able to add songs to this. So that's the idea here, and we're going to model that playlist using a doubly linked list of song objects. So I'm in the Section 20 workspace, and here is the Challenge 2 project, and then there's the Challenge 2 solution project, which has my solution, and I'll go over that in the next video. So let's talk about this challenge a little bit. The idea here is that you want to learn how to use a stood list, and that's what we're going to use in this challenge. We want to create a menu-driven application. This would be really cool to do graphically, but we haven't learned how to do that stuff. So what we want to do is we want to simulate the user selecting the first song in the playlist and then going to the next, the previous, playing forward and backwards through the playlist. Simple as that. We're also going to allow users to add new songs to the playlist. And every time we add a new song, it's going to be added prior to the currently playing song. Okay, so here's the menu, and I've got a sample run coming over here on the right, and I'll go to that in just a second, but here's the menu. Play the first song, play the next song, play the previous song, add and play a new song at the current location, and then just list the current playlist, and that'll list the playlist, or in other words, the songs that are out there, and it will also list the currently playing song, and cue to quit. So that's it. It's real simple. The available playlist is modeled as a list of song objects. I'll provide the song class, and I'll go over that in just a second. And these are the songs that I put in the playlist just default. I just grabbed a bunch of them from the pop charts. You can change these to whatever you like, or just put song 1, song 2, song 3 to keep track of them. I got kind of bored doing song 1, song 2. I wanted to see some real song names. So here they are. Drake, Camila Cabello, and Maroon 5, Imagine Dragons, a bunch of popular songs. That's it. So let me go over the run first, and then what I'll do is I'll go over the sample code that I'm giving you. Over here on the right, you can see the program running. The first run, it just displays the playlist right here. That's the playlist. So you can see these songs right here are showing up right here. And the current song that's playing is the one by Drake, which is the first song in the playlist. You can see it right up here. So by default, that's our starting point. When we first run the program, the first song will be playing. Imagine you're putting a CD in your car. Here's the menu. Play the first song. So anytime you press F, it's going to jump to Drake's song and play it. Next, Obviously, it's pretty straightforward what's happening. If I'm playing Drake's song and I press next, then it's going to go to Camilla's song. And if I press next again, The Weeknd, Zed, Maroon 5, Imagine Dragons, and so forth. Now, since we have a doubly linked list, these songs are modeled as doubly linked lists, right? You've got your links coming back and forth. And then I've got something called current song, and that's an iterator. That is pointing to the current song. So when you press next, all we're doing is we're moving the iterator over here, and then press again. Next, we're going to move it over here. Now, what's going to be interesting is if I'm right here at the first and I press previous, I want to wrap around to here. And if I'm over here and I press next, I want to wrap around to here. So I always want to be in that playlist. Okay, so let's walk through this little demo. Right now, when we first start the program, you can see the playlist and you can see that Drake song is playing. That's the very first song in the playlist. If I press N or next, it says playing next song, and it says now it's playing the Camila Cabello song, which is this guy right here, Never Be the Same. If I press next again, and I'm going to scroll up so you can always have this in context here. Now it's playing the Pray For Me song, which is the third song. I'll press next again. Now it's playing the middle. When I press next again, it should be Wait, and then whatever it takes. So I'll press next again. Wait is playing by Maroon 5 one more time. And now Whatever It Takes by Imagine Dragons is playing. Now I'm at the end of my playlist. If I press next again, I want it to wrap around back to the Drake song. So let's do that. I'll press N. And you could see that. Let me scroll that up. You can see that Drake's song is now playing. Now, if I'm here at the beginning and I press P for previous, it should wrap around back down to the Imagine Dragons song. So I'll press P for previous. Now I'm right here. I'm right at the end here. Imagine Dragons is playing. Let me move that up for you so you can see a little better. Okay, so that's it. Now, of course, if I press previous here, it's going to go to the Maroon 5 song. And you can see it's just a linked list, and I'm able to go around it, which is pretty cool. If at any point you can press L, and that'll list what's currently happening. So you can see the playlist right here. That hasn't changed because we haven't modified it at all. But you can see the playlist right here. And the current song is the Maroon 5 song. So anytime you want some information, you press L. All right, so now let's get to the good stuff. Let's add a song. I'm going to scroll up just a little bit. Okay, now I'm going to press A. And when I press A, it says adding and playing a new song. Cool. So what's the song name I want to add? Let's say I want to add Imagine. Who's the artist? It's the Beatles. What's my rating for the song? I'll give it a 5. Now, when I press enter, that song will be added before the current song. And if you remember, the current song was Wait. That's the one that's currently playing. So Imagine will be added between the middle and Wait. So I'll press enter and it will play. It'll be the current song. So I'm going to press enter and you can see now it's playing Imagine by the Beatles. And if I list, let me scroll up a little bit. If I list my playlist now, you can see that Imagine is right here. Let me mark that for you with my pen. You can see that Imagine is right here now, and it's between Wait in the middle, just what I wanted. Now, suppose I want to press F and I want to go to the first song. So we're going to go here to the Drake song, and then I want to insert a new song before that. So let's do that now. So the first thing I'll do is let me clear this real quick, and I'll scroll up. So I'm going to go to the first song, which is the Drake song. I'm going to press F right here. I'm playing Drake's song, and now I want to add another song. So let's add. What's the song's name? Let's say it's New York. And let's say that this is Frank Sinatra. And I'll give it a 5. I'm giving everybody 5s. That's it. Now it's playing New York. Remember, we were at the beginning. So if I display my playlist, you can see that New York has now been added at the beginning of the list. And it's playing right here, current song New York. That's it. That's the program. You press Q to quit. Now, there's a couple of interesting things here that you can extend once you get this basic functionality going. Notice that in my menu, I have no way to play the last song in the list or the ending song in the list. You could certainly add that. You could add a whole bunch of other things. You could save this to file. You can read this information from a file. So you can extend this program in a bunch of different ways. Okay, so now let me show you the source code that I'm giving you. And that is right in here. I've gone ahead and included the include files that you're going to need. And let me show you what the song class looks like. It's a real simple class. Obviously, this is what we're modeling: the name of the song, the artist, and the rating, which is an integer in this case. I have a friend function here, which is my overloaded insertion operator, so that I can display this kind of stuff over here real easy. I've got a default constructor. I've got an overloaded constructor here that allows me to create whatever I need using name, artist, and rating. Then I've got some getters, and I don't even think I'm using the getters, but I put them in there anyway. Now, the most important thing we need to do here is, and it's not so important in this program, but it's just best practice to always do, we need to overload these operators, the less than operator and the equality operator. Those are the only two operators that we must overload if we're going to use our own custom classes with the STL. So in this case, less than, I'm defining less than as this name of this song is less than that name of the other song. And the same thing with equality. If the two names are the same, then I'm considering them equal. Okay, so that's that. Here I'm overloading the insertion operator, as I mentioned. I'm giving you the code for the display menu, which is really, really easy. And then I've got a couple of methods here, or functions, I should say, that you're going to implement. One is play the current song. And all this does is it does this right here. Here we go. So I just went forward. It says playing and the song that's playing. That's all. It just displays that. And the song that's being played is passed into it. So that's a really one-liner, right? You basically just have to output that to an output stream. Display playlist. Here we're getting the entire playlist and the current song. And this is the one that you're going to call from the list functionality. It's just going to display all those songs. So in this case, we're going to see something like this right here. All that good information is going to display. Okay, and now here's the main. Probably just what you expect. Here's my playlist. That's my object, and it is a list of song objects, and I'm initializing it right here. So that's done. And I'm setting my current song. This is the most important piece here. That object right there, that current song, is an iterator that's pointing to some object in this playlist. And I'm setting it to the beginning of the list. I'm setting it right to there. It's going to start right there. From that point on, it's your logic to display the menu, get the input from the user. Depending on what they select, this is the guy that you're going to have to increment or decrement depending on how you want to walk across this list. That's it. Have fun. Get the basic functionality working before you extend it. And then you can extend it, like I said, a bunch of different ways. You can go to the end, go to the beginning, save it to a file. So next time you run this, you can just load the information, the song information from the file. Because remember, as it is now, every time I add a new song to the playlist, it's not being persisted. So the next time I run this, it's not going to be there. So it'd be kind of nice to be able to save that and then load it up again. Okay, so that's it. Have fun. It's a nice little challenge project. It's simpler than you would think. Think iterators, think STL. Don't think about, I's and J's and looping variables and things like that. Let the STL do the work for you. All right, have fun. And I'll see you in the next solution video. Hello, welcome back to the Challenge 2 solution for Section 20. So I'm in the Section 20 workspace, and I'm in the challenge_2_solution project. And what I'd like to do is just go over my solution. This is a really, really straightforward program. If you're not used to thinking abstractly with STL containers and iterators and so forth, then it becomes much more difficult. But once you really take advantage of using the power of the STL, it makes much, much easier. So here's what I've got going on here. I've got my song class, which we've already talked about. It's very straightforward. I talked about that in the previous video. And I'm going to scroll down to the methods that we're going to implement. So here is the display menu, which I gave you. And here's that very first method you had to implement. Play the current song. So I'm being passed in a song object. What do? I just say playing, and I display the song. Simple as that. The song class overloads my stream insertion operator, so it becomes basically a one-liner. The next one is displaying the actual playlist. And again, really straightforward. What am I getting? I'm getting the playlist, which is a list of song objects. And I'm also getting the current song because I want to display both of them. That way I have all the information I need in the display. all I'm doing is a range-based for loop over the playlist. I'm grabbing the song that's there and displaying it, just like we did here. So we're using the overloaded insertion operator. That's going to display all the songs in the playlist in the loop. And then I'm just going to say the current song that's playing is current song. This code is the same as this code. I could have called this function from there. Either way is fine. And now let's look at the main. That's the real workhorse. You can see that I am defining playlist right here. And this, of course, is main. I'm initializing it to these 6 songs. You could choose any songs you like. This right here is so important. If you forget to do this, you can run into issues. That's why I gave you that one line in the code. Current song is an iterator to a song in a stood list. And I'm setting it to the beginning. So in other words, I'm always starting right at that first song up there. And then I'm displaying the playlist. What am I passing in? I'm passing in the playlist and I'm passing in the song. Remember, current song is an iterator, so I need to dereference that iterator to get to the song that it's pointing to. To be double safe and to use defensive programming, you always want to make sure that that is actually pointing to the list and not off the list. But in this case, I'm sure I'm not off the list anywhere in this program, so I'm not doing it. But defensive programming probably would be a good idea to check to make sure that iterator is not pointing off the list. Okay, so now we're in the loop. And we've got a character variable. That's where I'm going to read the user's selection into. I'm displaying the menu. I'm reading their selection. I'm making the selection uppercase. That way I don't have to use ors here in my if statements. And if the selection is F, that means we're playing the first song. I'm just displaying this little message right here, just playing first song. And I'm setting the iterator current song equals playlist.begin. That's the first element in the list, the first song. That's it. And I'm calling play current song and I'm dereferencing that iterator and passing this song in. That'll display that that song is playing. And these little messages here, I've got one here and I've got one here. You really don't need those, but I just put them in there that way you can explicitly see these functions working. So let's look at next. I'll scroll up just a bit. So here we're going to play the next song. What do? I increment the iterator. Now it's possible that I was on the last song and now I'm off the list. So I really need to check here. So if the current song is equal to playlist end, that means I'm off the list, right? I just pressed next and I was on the last song. So what I need to do here is wrap to the start of the playlist and then set my iterator to the beginning. And then we press current song. Now, if I'm not at the end and I was somewhere at the beginning or in the middle, it's not a big deal. That's it. That's the logic right here. For previous, it's very similar. So I'm playing previous song. And I'm checking to see if the current song is equal to the first song. Then I need to wrap around, right? So in this case, I need to set the current song to the end. Now notice what happens here. Remember, here's my list. And this is the end of the list, right? This is just a placeholder. There's no song there. So I want to set it to there because in the next line, I want to decrement it and bring it right back to here. So that way I don't have to duplicate code all over the place. So that's it. I decrement the song and I call play current song with the song. And now it's going to be playing the last song if I was at the beginning of the list. Otherwise, it's just going to play the previous one. The addition right here where we're adding songs, I've got some variables. I've got my name, my artist, which are strings, and the rating. I've got this line of code where if I provided in your description, this just clears out anything that's in standard in or CN. In case you've got garbage characters in there or extra returns from processing, this is just a good practice to get into whenever you really need to just clear out stuff. I don't want anything in there. So I'm just clearing everything out. And then I'm adding and playing a new song. I'm displaying that message and I'm asking the user to enter the name of the song, the artist, and the rating. And once I have that, I'm creating a new song based on that information. And I'm inserting using playlist.insert and current song. Remember, that's my iterator. So I'm inserting it before that. That's the behavior. I could use in place here as well, whatever you like. Now, what happened was, remember, here was my iterator, which was current song. It's pointing here. And I just inserted that song here. So I need to decrement that operator to play it. So right here is where I'm doing that. I'm decrementing the iterator right here. And I'm playing the song that I just inserted. All right, now the last couple are just real simple. Here, list, I'm just calling display playlist, and I'm passing in the playlist and the current song. Q, I'm quitting. Anything else is an illegal choice. That's it. You can see it's really straightforward, right? I've got no looping variables. I'm not worried about keeping track of stuff. The only thing I'm keeping track of is I've got my list here. And all I'm doing is I've got that current song. That's the only thing that really concerns me. I've got that current song iterator. And all I'm doing is moving that guy back and forth along the list. Really, really simple. It never invalidates because when I'm inserting something, I'm inserting something before it. So all I need to do is just move it back. So I'm never going to invalidate that. And the way that the code is written, it's never going to go off the list. So that's why I'm not checking to make sure it's in the list, but I certainly could. All right, I hope you had fun with this. I hope you've extended it as well. If you have your solution, you think it's really cool, post it in the Q&A and we'll all comment on it. All right, I'll see you in the next video where we're going to start talking about sets. In this video, we'll learn about the STL set containers. These are associative containers. Associative containers are collections of stored objects that allow for fast retrieval using a key. The STL provides both sets and maps. In this video, we'll learn about sets, and we'll learn about maps in the next video. Depending on the type of the associate container, they're usually implemented behind the scenes as a balanced binary tree, something like a red-black tree, or as a hash set. These are very efficient data structures, so operations on sets and maps are very fast. The STL has 4 types of set containers: the set, the unordered set, the multiset, and the unordered multiset. We'll focus mainly on the set since it's the one most often used, but I'll also describe the others as well. Let's first talk about the set. In order to use a set, you must include the set header file. The set class is similar in concept to a mathematical set. The elements in this set are ordered by key, and no duplicate elements are allowed. All iterators are available for sets. Let's initialize a few set objects. In the first example in this slide, I declare S as a set of integers, and I initialize it to 1, 2, 3, 4, and 5. In the second example, I declare stooges as a set of stood strings, and I initialize it to some strings. Then at the bottom of the slide, you can see that sets also support assignment via an initialization list. But there are some differences with sets. On the first line, I'm initializing S as a set of integers, and I'm providing the initializers. But notice that the initializer list contains duplicate elements. That's not allowed in a set. This won't cause an error though. The duplicates are simply ignored, and we end up with a proper set. Also notice that the set is sorted. The size method returns the number of elements that are in the set, and max size tells us what the maximum number of elements a set can hold. Remember, sets do not allow direct access to elements, so we can't use the subscript operator or the .at method as we have with other containers. Sets also don't have a front and back, so methods like pushback and popback in the front versions do not apply to sets. So how do we add elements to sets? Simple, we use the sets insert method. We can also use the inplace method if we want. In the last statement on the slide, we insert 7 into the set. If 7 is in the set, it won't be added again. If it's not in the set, then it will be added, and it will be added in order. So let's talk a little bit more about the insert method. Suppose I have an object P1 that's a person object. In this case, Larry 18. I also have P2 as a person object, Mo 25. We can insert P1 into the Stooges set by simply calling stooges.insert and passing in P1. If the element is not in the set, it will be added, otherwise it won't be added. The set class uses the overloaded less than operator to determine if the element exists in the set. That's fine, but sometimes we want to know whether an element was inserted successfully or not. The insert method returns a stood pair. Remember stood pair, we talked about it a few times in this section, and we'll talk about it some more in the maps video as well. The pair object that's returned has its first attribute as an iterator to the element that we just inserted, or an iterator to the duplicate element that's already in the set. And then the second attribute is a Boolean that indicates whether the operation was successful or not. That's pretty cool. Now we have all the information we need, and we can do whatever we need in our program. We can also erase elements in a set very easily. S.erase3 will erase the 3 in the set S if it exists. We can use the sets find method to find the 5, and if it exists, delete it by passing the iterator to the erase method. Notice that the sets find method is different from the find function in the STL algorithms library. You should use the sets find because the sets find knows all about the internal implementation of the set, and it's going to be much more efficient. Finally, we can use the count method to see how many times an element appears in a set. If you think about that, it doesn't make a lot of sense, right? I mean, a set can only have an element in there once at most. But in this case, it's real handy to tell whether an element is in the set or not. If we get back a 0, we know it's not in the set. If we get back a 1, it is in the set. We're going to use this in multi-sets because multi-sets can have duplicates, so this method is real useful there as well. Finally, as with all other STL containers, s.clear removes all of the elements from the set, and s.empty returns true if the set is empty or false otherwise. Well, that's a quick summary of the set class. Please refer to the set documentation since there's more and many of the methods I show you have variants as well. So let's talk about the other set classes. First, let's talk about the multi-set class. It's also defined in the set header file. A multi-set is a set that's ordered by key, but it allows duplicate elements. All iterators are available. The unordered set is in the unordered set header file. The unordered set is a set that's unordered, and it does not allow duplicate elements. Due to the way that unordered sets are implemented, elements can't be modified in place. If you need to change an element, you have to remove it and then insert the updated one. Also, unordered sets do not allow reverse iterators. The last type of set provided by the STL is the unordered multiset. The unordered multiset does not order elements, and it does allow duplicates. Again, no reverse iterators are allowed. As you can see, the STL provides powerful set classes for nearly every need. However, by far, the most used is the set, and that's the one we're going to focus on. So let's head over to the IDE, and we'll look at examples of using sets. Okay, so I'm back in the IDE. Again, I'm in the Section 20 workspace, and I'm in the set project. And what I've got here is I've got the same person class, and I won't bother going over it again. We've gone over it a bunch of times. I haven't made any changes to it since the last time. But I do want to bring that to your attention again. The operator that we're using for the operator less than is comparing ages. Okay, so we're considering one person less than the other based on the age, not the name. And that's going to be important because the set uses that operator. So when we see these guys sorted, you're going to see them sorted by age rather than by name. And that's important to understand. A lot of people think that it's this operator right here that's doing it, and it's not. Okay, so let's get started. There's 4 tests, or actually 3 tests here, so it's not as long as the other videos. But let's start with test 1. And you can see the output right up here. On the right up here, you can see that's where the test 1 is right here. So let's start. I'm going to create a set called S1. And you can see it's a set of integers. You can see the consistency with the syntax across the entire STL. And I'm putting in 14352. Notice I did that on purpose. I changed the order. The sets are ordered by default. So when I display S1, you can see that it's being displayed in order. In this case, integer order. If I had put in the stooges with ages, then we get a different order. I'm doing that in the next test. In this example here, I'm assigning this initializer list to S1. But notice there are duplicates in here, right? There's duplicates all over the place here. Duplicates aren't allowed in sets. This will still work. This will work just fine. When I go to display S1, you can see that the duplicates were not handled. Of course, they're omitted. So it's not going to add duplicates to a set. That's not going to allow duplicates. Then we've got right here, we're inserting 0 and we're inserting 10, and then we're displaying it again. And you can see that right there, there's the output. You can see the 0 at the beginning and the 10 at the end. So they were inserted where they should have been inserted, which is exactly right. Now, let me just scroll up here just a little bit, and we're right about here on line 50. I'm seeing how many times does 10 occur in the list. This is going to return an integer. It's either going to return 0 or 1 in this case of a set, because the set either has the element in it or not. There is the multi-set, which allows multiple entries, right? Duplicates. in that case, this could return 2 or 3 or 4, depending on how many times that element exists. But in this case, I'm saying, is the 10 in the list? This will either return a 1 or a 0, 1 being true, 0 being false. So 10 is in the set or 10 is not in the set. We know 10 is in the set because we just added it right here. So I expect to get back 10 is in the set. Okay. And now I'm using the find method here. I'm using s1.find. I'm not using studfind, which is in the algorithms library. I'm using the sets version of find. A lot of people use the other one. The other one is a very generic type find that's going to use an iterator and just search through the entire set. This guy's real smart. This one understands how the set is implemented behind the scenes. So if it's implemented as a balanced binary tree, it's going to be pretty smart about finding things. So let's find the 5 in the set. Is the 5 in there? Absolutely, it's in there right here. So what are we going to do? We're going to assign the results of that to an iterator. If we get back the end of the set, obviously it wasn't there. If we don't get it back, then we found the 5 and it's pointing to it. So that's what we got right here. We know it's in there and that's what we got back. We can clear the set and then display it again. And obviously that clears out the set just like it does with all the containers. Okay, so there you go. Hopefully the consistency is paying off. Like I said, there was a method to my madness with all of these examples. Usually when you see a lot of them and more, you'll see the pattern and it just really clicks. So now let's see the test 2. What we've got here is a set of person objects. And we'll call them stooges. And we said the person had a name and an age. I just put 1, 2, 3 here because I want to show you the order that these are going to be put in. So now when I display stooges, look at them right here. That's the order. Larry 1, Mo 2, Curly 3. Notice that it's ordering by age, 1, 2, 3. It's not ordering by name. Otherwise, Curly would be the first one, right? So that's important to understand. It's using operator less than to do the ordering. All right, so that's what it's using right here. So we can place James 50 and we can display the stooges again. And you can see that at this point, James 50 was added at the end because the 50 is what it's using to order. So this really drives the point home. Suppose I want to place Frank 50. It won't let me because it's using the 50 to decide whether to put it in there or not. So it's, according to this, that 50 is already in there. Now, had I checked to see that the operator less than was the name and the key and the age, then this would have definitely worked. But when I display it again right here, there's no Frank in there. As far as this is concerned, it already exists. All right, so now we've got a couple of more output statements. Let me scroll up a bit and I'll show you how these work. In this case, I'm finding Mo 2 in the list. I know Mo 2 is there. I'm going to get an iterator back. And if it's not equal to the end of the list, then what I'm going to do is erase Mo. That's all I'm doing. I'm not displaying Mo. I'm erasing Mo. Then I'm displaying stooges. And you can see right here that Mo right there is gone, which is kind of cool. Now, this is the one that really shows you how the power of that operator. In this case, I'm finding a person whose name is X and whose age is 50. This doesn't come into play because I'm not using that in my overloaded less than operator. So it's going to find James there at 50, and it's going to erase James. And then I display stooges again, and you can see that James is gone. Okay. This gets a lot of people when you're first starting out with the STL. A lot of these containers, some of them use equality, some of them use less than. The set uses the less than, so be aware of that. The final test is this guy, and this is an important one because it shows you what happens when we insert some data into a set. Let's just start up here first. I'm creating a set of stood strings, and it's called S, and I'm putting in there ABC. Now, obviously, we're using strings, so it's going to use the string order to sort. I'm displaying S, and you can see ABC right here is displaying. Actually, you know what? Let me scroll that up just a little bit so it kind of aligns a little better. There we go. So we're displaying ABC right here. Now I'm inserting the D, and I'm displaying S. And you can see the D has been inserted in here. But notice at this time, I assigned the return value of the insert method to this guy right here, result. And I'm using auto. What I'm getting back here is a stood pair. Remember, the stood pair has two attributes, first and second. In this case, first is an iterator that's pointing to either the D that we just inserted or the D that's already a duplicate in there that didn't allow me to insert. In either case, I'm getting an iterator to the element that I'm inserting or its copy that's already in there. Hopefully that makes sense. Then the second part of the pair, the second attribute, is going to have a Boolean, true, false. Was the insertion successful? So I've changed this to bool alpha so it displays the true false value. And here I'm displaying first. And we expect a D. You see it right there. So we either got a D that we inserted or the D that was already there. That's when we look here. So if this guy is true, it is right here, that means our insertion was successful. Had it been false, that means that I already had a duplicate in there. Okay, I know it can be a little confusing, but it makes sense when you think about it. And this is pretty cool. If you think about it, what's going on here is I've got a return from a function that's returning multiple items, right? Which is kind of neat. It's really wrapping it up into one pair, but even so, I can still get to those pieces of the pair. Some other functions return tuples, which can have even more than two. Okay, so let's do that last one right here. And in this case, I am inserting the A. Okay, and I'm right here. This is where I'm at right now. I'm inserting the A and I'm displaying S. Now, the A was already in there. So I'm displaying it right here. And now what I'm doing is, what's first? Well, first was the A. It's the iterator that's pointing to the A that was already there. That's why I'm getting that. And when I display the results for the second attribute, now I'm getting the false. So right here, I know that that insertion was not successful because there was a duplicate in there already. So that covers sets. What we're going to do in the next video is cover maps. And then the challenge for the sets and the maps is going to incorporate using sets and maps together, which is kind of cool. All right, so in the next video, we'll talk about maps. In this video, we'll learn about the STL map containers. These are also associative containers. They're collections of stored objects that allow for fast retrieval using a key. The STL provides both sets and maps. We saw sets in the last video. In this video, we'll learn about maps. The STL has 4 types of map containers: the map, the unordered map, the multi-map, and the unordered multi-map. We'll focus mainly on the map since it's the one that's most often used. In order to use the map, you must include the map header file. The map is like a dictionary, where we have a key, a word in the case of a dictionary, and an associated value, which would be its definition. Maps store their elements as key value pairs using the stood pair objects. The elements in the map are ordered by key, and no duplicate keys are allowed. We can directly access an element in the map using that key, and all iterators are available. Let's initialize a few map objects. In the first example in this slide, I declare M1 as a map of string integer key value pairs. The key is the string and the value is the integer. Then I initialize M1 with 2 key value pairs, Larry 18 and Mo 25. In the second example, I declare M2 as a map of string key value pairs, and I'm initializing it to Bob Butcher, Ann Baker, George Candlestick Maker. We'll use the map M in this slide for the next several examples. The size method returns the number of elements that are in the map, 3 in this case, and max size will tell us the maximum number of elements the map can contain. Maps have no concept of front or back. We'll see how we can add elements in the next slide. So let's see how we can insert elements into a map. We can use the insert method. Remember, maps consist of stood pair objects, where the first attribute is the key and the second attribute is the value. We can create P1 as a stood pair object of type string and initialize it to James Mechanic. James is the key, Mechanic is the value. We can then insert P1 into the map M since M is a map of string key value pairs. Pretty easy. We can also use the stood make pair function to make it even easier for us to create those key value pairs, and we can insert them right into the map. You can see in the last example how easy it is. In this case, we're adding the key value pair Roger Ranger to the map. So let's see another way we can insert elements into the map. We can use the subscript operator and the .at method to make the syntax pretty easy. Suppose I want to insert the Frank teacher key value pair into the map M. I can provide the key Frank in this case inside the square brackets and assign the value to it. This will insert the key value pair into the map M if it doesn't exist. I can also modify existing map values in the same way, and the syntax is dead simple. If I wanted to change the value associated with the key Frank from teacher to instructor, I can simply use the subscript operator to do it. The .at method does the same thing with different syntax, of course, but it will throw an exception if the key is not in the map. We can also erase elements in a map very easily. m.eraseAn will erase the key value pair whose key is An from the map. We can also use the find method to get an iterator to a map's element. As with the set, for efficiency, use the member method find, not the find in the algorithm library. In the second example, I'm finding the key Bob in the map. If I get back an iterator that's not pointing to the end of the map, then I found the matching element. If I wanted to erase that element, I can simply call m.erase and pass in the iterator. In the last example, that's exactly what I'm doing. I'm looking for the key George in the map, and if it's in there, I'm erasing it. Finally, we can use the count method the same way we did with sets. It's an easy way to see if an element exists in the map. If it does exist, count will return 1, and if it doesn't, count will return 0. As we've seen with all the STL containers, the clear method removes all elements from the map, and the empty method returns true if the map is empty, false otherwise. Well, that's a quick summary of the map class. As I mentioned previously, with all the STL components, there's much more to learn. Please become familiar with the basics, and then take your learning to the next level by studying the STL documentation. Let's see some of the other map containers provided by the STL. The multi-map class is also defined in the map header file. A multi-map is a map that's ordered by key, but does allow duplicate elements. All iterators are available to the multi-map. The unordered map is in the unordered map header file. The unordered map is a map that's unordered. Unordered maps do not allow reverse iterators. The last type of map provided by the STL is the unordered multi-map. The unordered multi-map does not order elements, and it does allow duplicates. Again, no reverse iterators are allowed. These maps are very powerful and pretty easy to use. Let's head over to the IDE and we'll see some examples of using the map. Okay, so I'm back in the IDE. I'm in the section 20 workspace in the map project. And what I'd like to do is go over a couple of map examples, and one in particular that I think is going to help you out a lot with the challenge that's coming up in the next video. So let's start with test 1. And there's only, I think, 2 tests in this example. Test 1's a little long, but we'll go through it slowly. And then what we'll do is we'll talk about the display function I wrote. Okay, so we're here in test 1. And what I've got here is I've defined M to be a map of string integer key value pairs. The string is the key, and the integer is the value. These guys can be just about anything. I'm just going to use strings for the key because they're really easy to understand, but those keys can actually be our own custom objects as well. And the value can be more complicated as well. And what we're going to do is, in the next test, what we're going to do is we're going to have the key be a string and the value be a set of integers. So again, you can build these things up to get really complicated and very, very, very powerful. So again, M is a map of string integer key value pairs. Here are my pairs right here. These are not person objects. I don't even have a person class in this demo. So there's the string Larry, and there's the value in the integer 3. Mo1, curly 2. What this means, who knows? You're just associating a string with an integer. It could be how many times Larry went to the movies today. It could be just about anything. Okay, then I'm displaying M. And you can see that right up here. It's displaying curly 2, Larry 3, Mo 1. Now look at the ordering there. It's ordering by key. And the key in this case is the string. So you're going to get curly first, Larry second, Mo third. It's using string order. Perfect. Now let's add Anna 10 to that map M. Remember, what we're doing is we're adding stood pairs. So in this case, we're creating a stood pair object right here, and it's got to be of the same key value pair type. So it's got to be string int. It can't be anything else, or I can't insert it into this map here. So in this case, there's my key, there's my value. I'm creating a pair, and I'm inserting that pair into M, and then I'm displaying M. So when you see that next display statement here, you can see Anna is in there now with a 10, and Anna is at the beginning of the list because it's being sorted by the key. Now there's a handy little function called make pair that makes this really easy. So we can insert, call make pair. It's going to create that stood pair for us, and it's going to be the key is Joe, the value is 5. So that'll automatically do kind of what we did up here without all the template parameters or any of that. It'll figure it all out. So in this case, it's going to make the pair Joe 5 and insert that into the map. And then we're going to display the map right here. And you can see that Joe 5 is now in the map. Pretty easy, right? Now here, this is really easy here. In this case, I'm saying M, and I'm providing the key. This is the key inside the subscripts. So what it's going to do is it's going to insert, as Frank isn't in there right now, it's going to insert the key value pair Frank 18 into the map using this syntax, which is really, really easy to read. And then I'm displaying it, and you can see right here that there's Frank 18. Now, what's really cool is if I wanted to change the value associated with the key Frank, right now it's 18. Suppose I wanted to add 10 to it. All I have to say is give me the value for that key in the map. That's what I'm doing here, and add 10 to it. Display it again. So now you can see that Frank is 28 right here, right? So I've added 10 to the 18. Pretty cool. Let me clear this and let's scroll up just a little bit, do a couple more examples. Let's do this one right here. All I want to do here is erase Frank from the map. I'm just providing the key right here. Remember, this is all key based. So in this case, m.erase Frank, and then I'm displaying the map again. You can see the output right here on this line. Frank is gone. Frank was here, it was 28, and now it's gone. And then we can call the count methods here just so you see how those run. I'm displaying the count for Joe. How many times does Joe appear in the map? Well, it's either there or it's not there. In this case, Joe is there, so we're getting back a 1. And Frank is no longer there because I just deleted Frank right here. So I should get back a 0, and that's exactly what I get back right here. And then what we can do is we can call the find method. Remember, this is the find method for the map class, not the find method in the algorithms library. So I want to find Larry in this map M. I'm going to get back an iterator. That iterator is an iterator not to Larry, not to Larry's value, which is 3, but to the stood pair. So if I get back an iterator and I'm not at the end, then I've got a pair. So I can access the first element in the pair and the second element in the pair. Makes sense? The first element is the key. The second element is the value. So this right here will display Larry. This right here will display 3. And that's what's happening right here. Found Larry 3. Then, of course, we're clearing the map and displaying the map. And now we've got an empty map right here. Okay, so go through these slowly. You can play them with your own. You can modify this and learn from it. Let's take a look at test 2. And we're here in test 2. You can see the output. Actually, let me scroll that up as well. Perfect. You can see that test 2's output is right over here on the right in the console. Now, this one's a little bit more complicated, so let's go through this slowly. I've got a map. It's called grades, and it's a map of string is the key, and the value is a set of integers. So in this case, grades is a map. The key is a string, and the value is a set of integers. So I can have values in there like Frank is the key, and I could have a set of integers, 10, 20, 30, let's say. Make sense? So this is pretty cool. So in this case, let's say that I'm trying to model the top 3 grades that Frank got this semester. Remember, we can't have duplicates in here, so we're just having the 3 grades. So what we're doing is we're saying the key is Frank, right? That way I can identify that key value pair. Once I have that, I can get the value part of it. It's a set of integers, and then I can process the set of integers. So that's what we're doing here, right? So let's go through this again. Here is key value. Here's the key. Here's the key. Here's the key. There's the value. It's a set of 2 integers. Here's a set of 1 integer. Here's a set of 3 integers. And then what I'm doing is I'm just displaying grades. And I'll show you how that display function works in a minute. But you can see I'm displaying grades right here. And it's ordering rather by the key, which is a string. So Curly 80, 90, 100. There it is. Larry 90, 100, and Mo 94. Now, suppose I want to insert 95 into that set of integers for Larry. I can get Larry right here. That's going to return a reference to that element, and I can insert 95 into its value. Well, remember, its value is a set, so I'm actually inserting 95 into that set of integers. So now you can see that Larry originally was 190. Now Larry is 90, 95, and 100 right here. Right, so I just added that 95 right in here. And remember, that set of integers is ordered as well, so we get that benefit as well. So we've got the map is ordered and the set within the map is ordered as well. All right, so the last example here is, let's say that we want to find Mo. So let's look for Mo. We're going to get back an iterator, right? If that iterator is not at the end, then I found Mo. Well, Mo is in there. I know he's in there. He's right over here. Right? So now what I want to do is, using the iterator, I want to access the second attribute, right? Remember, the first is the key. I know what the key is. It's Mo. What I want is the second attribute, which is the set of integers, and I want to insert 1,000 in there. So it's similar to this example right here, except that in this case, we're using an iterator. So I'm going to insert 1,000 into the set of integers associated with Mo. Remember, Mo is the key. The set of integers is the value. And you can see right there is the 1,000. And that's where I'm displaying the grades. Now let me show you the display function. There's actually 2 display functions. I've got this one right here, which is a template function. That's just displaying any 2 types. This is the one that's really being called in this case. So again, in this case, I might be getting it's a map, right? It's a map of key value pairs. The key is this guy right here. That could be Curly. And the value is the set of integers associated with Curly. So that could be the set 80, 90, and 100 in this case. So that's the information I'm getting. What I have to do is display it out nicely like this. So the first thing I'm doing, I'm just displaying the left bracket, which is this guy right here. Then for each element LM, I called it, in that map, the first item is the key. So that's Curly, that's Larry, that's Mo. And then each time I get one of those, what I'm doing is here I'm iterating over the second, which is the set of integers. Make sense? So remember, the outer loop here is iterating over Curly, Larry, Mo. And then each time I have one of those, I'm iterating over their values, the set right here. So that's just displaying that information nicely. I know this may be a little confusing. If you sit down and walk through it, it'll be really clear, I hope. In the next video, we're going to do a challenge where we're going to use something that's almost exactly like this. We're going to use a map where the string is the key and we have a set of integers as the value. And what we're going to do is we're going to grab words from a document and we're going to figure out how many times they occur, and then we're going to figure out how many times what lines they occur on. So it's going to be pretty fun. So I'll see you in the next video. Hello, welcome to the third challenge for the Section 20 part of the course. I'm in the Section 20 workspace, and I've got 2 projects, the challenge_3 project and the challenge_3 solution project. So as usual, the solution is my solution, and the challenge 3 project is the shell that I'm giving you that has the beginnings of the project that you can work on. So let's talk about this project. This is a fun challenge. This challenge has 2 parts, and it's all about understanding stood set and stood map. We're going to use the sets and the maps together. We're going to be reading words from a text file provided, and I'm providing that for you. The text file is called words.txt, and I'll show that to you in just a moment. And it contains the first few paragraphs from the book, The Wonderful Wizard of Oz. So the idea here is, the first part of the challenge is you're going to read each word from that file and count how many times it occurs in the file and then display that information. So what we get is a listing similar to this. This is just the first few words. So you can see that the word aunt appears 5 times in the text, Dorothy 8, Dorothy's with an apostrophe S once, M5 even once, and from once. Now you'll also notice that these words are displayed just like this, A, D, E, F. They're displayed in ascending order. And then right next to the word, we have the number of times that it occurs. Simple. So please use a map for this and make sure that your key value pair is a string int. That makes sense. This is your key right here, the word, and the value is the count. And the functions that I've written for you assume this. So make sure you use the string int. So that's part 1. And let me show you the file real quick before we talk about part 2. Here's the file. You can see it right here in words.txt. There's the file, and it's the first, I think, 5 or 6 or 7 paragraphs from The Wonderful Wizard of Oz. So you can see Dorothy appears here, and it's really easy to check your work in CodeLight. For example, if I just double-click Dorothy, you can see that Dorothy appears once, twice, 3 times, 4, 5, 6, 7, 8, 9 times. So it's really easy to tell just because it highlights it in yellow. And it also gives you the line number that it appears on, which is really cool because that's what part 2 of the challenge is all about. All right, so let me get back to the description. So that's part 1. And then in part 2, what I want is, same idea. I want to read all the words from the file. And I don't really care how many times they occur. I've already got that up here. What I want to know is what line numbers do they occur on? I want to see all the line numbers. So in this case, we can do this one. Aunt appears on line number 2, 7, 25, 29, and 48. Now, it might appear more than once on each line. I don't want you to say 2, 2, 7, 7, 7, and so forth. Just the line number should appear only once. So again, the word should be ascending in order, and the line number should be ascending in order in here as well. So one more time. Aunt appears on line 2, 7, 25, 29, and 48. So we can come over here to words.txt. We can find aunt, which is right there. So there it is, 2, 7, 25, 29, and 48. It's a nice, easy way to test your output. That's the challenge. So let me go back to the description and we'll talk a little bit more about this. For this part, for part 2, please use a map of string set int key value pairs, right? So the key is the word, the string, and the value is a set of integers. We did this in the description for the map video. This is just going to apply it now. For this one as well, for part 2, consider using a string stream to process your words. So in other words, read the line from the file into a string and then use a string stream to process that string so you can extract the words from it really, really easily. I've also provided the basic shell for both of these, and I'll show you that in a second. And I've provided a function called cleanString, and you can pass a word into that function, and it's going to return the clean version of it. So it's going to remove any trailing periods or semicolons or colons and things like that. And you can tweak that function however you like. I'll show you the code in a second. That's it. Let me run this program so you can see the output. And you can see all the display. I'm going to scroll all the way up to the top. It's running part 1 and then it's running part 2. Here's part 1. Aunt appears 5 times. Dorothy appears 8 times. M appears 5 times. And you go all the way through. Aunt and lowercase aunt would be different words. You can choose to make them all upper or lower or do whatever you like with that just to have fun. So in this case, let's look at some of the common words in English. The A appears 20 times. And appears 32 times. The is a very popular word. And there is the, it appears 43 times. So that's part 1. Again, notice that this is sorted in ascending order. Now here's part 2. We have the word and the occurrences of that word with line numbers. So aunt appears on lines 2, 7, 25, 29, and 48. Here you can see that Henry appears on lines 2, 6, 35, 45, and 50. There with the capital T appears on line 2, and you can see the rest. They're all here. So that's the challenge. It's not that hard. Don't overthink this challenge. Let the STL do the work for you. Don't start messing around and trying to get into the details of this. Just let the STL do the work for you. Think abstractly. So that's a sample run. And let me show you the code that I'm giving you. It's right in here in challenge_3 project main CPP. So I'll double click there. And let me just scroll down to the main real quick. There's your main right here. It's running part 1 and then part 2. And for each part, here's part 2, for example. There's the file. I'm opening the file. I'm closing the file. So think of part 1 and part 2 as unique little functions that each one opens the file, each one closes the file. So you could see in part 1 right here, my map is called words, and it's a map of string int key value pairs. I've got some variables here. I've got my file, which I'm opening. I'm checking to see if it was opened successfully. And if it is, then you write this code. And then when you're done with your code, you call that function right there, display words. Pass it in the map, and I've written the code that's going to display that all in a nice little format. But this is the code you need to implement here. For part 2, same idea. Here's my map words. This time it's a map of key value pairs where the key is a string and the value is a set of integers, as we discussed. I'm opening the file. I'm closing the file here. If it was opened successfully, you implement this code. When you're done processing the map, pass the map into display words, and it'll display all that information for you. Now, those 2 functions I wrote up here, this is display words for part 1, and this is display words for part 2. The only difference is this one expects string int key value pairs. This one expects, obviously, a map of those. This expects a map of string and a set of int key value pairs. You can totally erase these and do them yourself. I would actually encourage you to do that, but they're there for your benefit. Get rid of them and do them when you're on your own if you like. And then here's the clean string function. It expects a string, and you can see the code is dead simple. For each character in the string, if it's a period or a comma or a semicolon or a colon, I'm just not processing it. Otherwise, I'm just appending the character to the new string and returning it. So that's it. I'm just filtering on those characters. You can add some, remove some, or do whatever you like. That's it. That's the challenge. Again, have fun. This is actually a fun challenge, and it's really easy to do. You'll be surprised how easy this is to do. It doesn't seem so easy, but it really is. And as I said, the best advice I can give you is don't overthink this. Let the STL do its job. That's what it's good at. Okay, so I will see you in the next video in the solution. So have fun. Welcome back. I hope you had fun doing that challenge. I'm in the section 20 workspace and I'm in the challenge 3 solution. This is an example of explaining something is going to be much easier than explaining the actual problem to begin with. This code is so simple. Hopefully you did it similar to the way I did it. Let the STL do its thing. The STL is super powerful. Let's take a look at part 1. Here's the solution for part 1. And let's walk through this one line at a time. We've got our map here called words, and it's a map of string integer key value pairs. I've got a line. That's what I'm going to read the line from a file into. I've got a word, and this is how I'm going to process my words. Here's my file. My file is words.txt. If I can't open it, I'm down here, and I'm out. If I can't open it, then what I want to do is I want to process the words from the line I just read. And that's not so easy to do there. It's much easier to do if you use a string stream. And if you look at the IO videos, I talked about string streams in that video. So in this case, I'm creating a string stream called SS over line. So remember, we just read a line. Let's say we read, and this is a test. And we don't want to deal with new lines. We don't want to deal with any of that. So we just read that line. And then what we're going to do is we're going to create the string stream from that line. So that's going to put in that buffer. So now I can read words from the string stream. And it makes it really, really easy. So you can see right there, while I'm going to extract a word from the string stream. So I'm going to extract this word, and then this word, and then this word, and then this word. For each one of those words, I'm going to pass it into clean string so it can get rid of the periods at the end. And suppose I have something like commas and so forth, it'll get rid of that. So in this case, I will end up with a clean word. And all I have to do is just say words. That's my map. I'm using the subscript operator, right? So in this case, it's equivalent to saying something like this, words, this. Let's assume that we're working with that guy right there. That is my key. If it doesn't exist, the value is going to be added with the key, right? So in this case, that's my key. What do I want to do? I want to increment the value at that key. Simple as that. So now I just put that word in once. The next time I see that same word, it will already be there. So it's going to increment this to 2 and so forth. That's it. That's the code. It's really one line right there that does all the good work. I commented this line out right here, and you can use that for debugging purposes if you like, to make sure that you're reading these lines correctly from the file. That's it. That's part 1. I told you it was pretty simple. I'm closing the file, and then I'm calling display words, and display words will come up here for part 1, and it's going to call this function right there. And all it's doing is it's just doing a lot of formatting, which is just to look nice. But for each pair from the words map, I'm dealing with the first and the second. The first is the key. The second is the value. So this is just displaying Aunt 8, Frank 3, and so forth. Okay, let's look at part 2. Here's part 2. Very, very similar, the idea. We've got our map is words, and this is a little bit different, right? Because I've got a key here, and my value is not an int. In this case, it's a set of ints. The whole point of this exercise was to show you how you can build these things up. I mean, it's really, really powerful. Many times we need to solve a problem like this, and you'll see some programmers creating classes for words and for lines, and you create a new class that's going to model the occurrences of a line. You really don't need to do any of that because the STL does this for you. This is a real powerful concept. I mean, I'm already modeling key value pairs right here. Why do I need to create another class to do this when I just need to solve this problem? Okay, so in this case, I've got the same variables. I've got the same file. I'm opening my file right here on line 88. I need to have a running count of line numbers because I need my line numbers. So I'm just starting line numbers at 0. I mean, I haven't really read anything yet. Now what I'm going to do is I'm going to read, let me clear this a little bit. I'm going to read the line into this variable from the file. And now I want to increment line number because I just read a line. So line number now would be 1. Again, I'm using the string stream to process words, cleaning the string. And this is the only difference here. So now I'm doing something like words. Again, let's assume we're using that word we just read. This piece right here, that's the key. This will return the pair, and I can access the value right there. So what am I doing? I'm inserting line number into the value, which is that guy. Right? So I'm using the sets insert method, which is really, really easy. The first time through, the line number is the line number. I'm just inserting that key value pair. The next time, it's just updating that value. And that's it. Let's run this one last time. Here's my output. And you can double check it in the code light editor, but it's really, really straightforward. Here's part 1 where you've got your word and the number of times it occurs. And down here is part 2, where we've got the word and the line numbers that it occurred on. Okay, so hopefully you had fun with this one, and hopefully you can see how easy it is now. So in the next video, we'll talk about the container adapters, stack and queue, and then we'll have another challenge for those. In this video, we'll learn about our first STL adapter container, the stack. The stack is a last in, first out data structure. It's an adapter because it's implemented in terms of already existing STL containers. Since all operations on a stack happen on only one end, the top, we can easily implement a stack based on any container that has a back. These are vector, list, and deck. So the way that the stack methods work is they use delegation and they call the back, pushback, and popback methods of the underlying container. Stacks have wide applications in computer science, and the STL provides a simple, concise implementation. You can think of a stack as a stack of books or a stack of plates. If we stack plates one on top of the other, we can't pull out a plate from the middle or from the bottom. Instead, we add plates at the top and remove them from the top. Since stacks are limited to insertions and deletions on only one end, iterators really don't make sense and they're not supported. So we can't use stacks with STL algorithms. In order to use the stack container, we have to include the stack header file. The stack provides a handful of methods that have well-defined behavior. The push method inserts an element at the top of the stack. The pop method removes an element from the top of the stack. The top method accesses the top element of the stack, but it doesn't remove it. Finally, we have the empty and size methods that we've already seen in the other STL containers. Since the stack is an adapter class, we can choose what underlying container will be used when we create our stack objects. In the first example, I'm providing no information about the underlying container, so the STL will use a deck by default. You can see in the next 3 examples that I'm explicitly stating which underlying container to use in the template parameter. So let's see how the push method works. Suppose we have a stack of integers named s, and it's empty. When we push 10 onto the stack, we add 10 at the top of the stack. You can see the top of the stack as the shaded box in the diagrams. We then push 20. Now 20 becomes the top of the stack. Finally, we push 30, and the 30 becomes the new top of the stack. Once we have a stack that contains elements, we can access the element at the top of the stack with the top method. This returns a reference to the element at the top. It does not remove it. In this example, s.top returns 30, which we display. Now, if we pop the stack, the element at the top is removed. In this case, the 30, and now the 20 becomes the new top of the stack. If I pop the stack again, the 20 is removed, and now the 10 is the new top of the stack. If we call the size method for s here, it will display 1 since there's just one element left in the stack. As you can see, the stack API is very straightforward, but a stack is extremely useful and it's used in computer science to solve many types of problems. Let's head over to the IDE and we'll see some stack examples. Okay, so I'm back in the IDE. I'm in the section 20 workspace in the stack project. And this is a really simple example. There's not really a lot we can do with a stack. Push, pop, and top, that's about it. So let's go over a few examples here. I'm including stack right here because I'm going to use it. I'm also including vector and list. Just I'm going to show you how you can create those stacks based on vector and the list underlying container. So that's the only reason I'm including them. I'm really not using it. I just wanted to show you how you would declare it here. But let's talk about this template function. This is the one that's going to display a stack. We can't use iterators with stacks, so there's no real way to display a stack easily. The only way to display a stack is to, let's say we've got a stack here with a 10 and a 20, and I want to display it. I need to get the top, display it, pop it, get the top, display it, pop it. So it's a destructive process. Because of that, I'm passing in this stack by value. I don't want to upset the stack that's being passed into me at all. I don't want to modify it at all. So that's making a copy. And what I'm doing over here is I'm destroying that copy, which is fine. Once I finish this function, the stack that's being passed into me has not been modified at all. And you can see the code. It's pretty straightforward. This is a template function. There's the type right here. We're using integer stacks in this example. And while the stack is not empty, I'm getting the top element of the stack, then I'm deleting it from the stack, and then I'm displaying it. That's it. So that's just going to display my stack. You can see the output over here, and I'll go over that in just a second. All right, so let me scroll up, and there's no tests here. It's just a main, which is pretty straightforward. Let's go over these examples here. Here I'm creating a stack of integers. I call it S. That's the one we're going to use in these examples. But I can also create S1, S2, and S3 that are stacks of integers, but the underlying container would be a vector, a list, or a deck, whatever you choose. On line 25 here, you can see that I'm just not providing anything, in which case it defaults to a deck. All right, so let's push some values on the stack and pop them off and play around with it a little bit. Let me just scroll up just a little bit right about there. Okay, so I've got that stack S that I've already defined. And what I want to do is I want to use a range-based for loop that's going to loop over this range right here, 1, 2, 3, 4, 5, and it's going to push those numbers onto that stack S. Remember, let's assume that this is my stack right here. The numbers are being pushed this way and then popped off. So first I'm going to push 1, and then 2, and then 3, and then 4, and then 5. So that's the situation right now. Then I'm going to call display. Remember, display is going to make a copy of this stack. It's not going to mess with this one. And what it's going to do is it's going to pop the elements off the stack. So it's going to pop off the 5, the 4, the 3, the 2, and the 1. Remember, everything happens up here at the top. So it's going to display exactly what I just said. 5, 4, 3, 2, 1. You can see 5 was the top of the stack in that copy. Now if I pop two elements off of this stack, the 5 and the 4, oops, sorry, I missed one step right here. Let's back up to that. In this case, I'm pushing 100 onto the stack. So I'm pushing 100 onto here. And then I'm displaying that stack again. And now you can see that the 100 is there. The 100 is now at the top of the stack. Now I'm popping off two elements off the stack. The 100 and the 5 are being popped off the stack. So the top of my stack now is the 4. And when I display my stack right here on line 39, you can see it's displaying 4, 3, 2, and 1. In this code here on line 41, I'm just looping while the stack is not empty. So as long as the stack is not empty, I'm deleting stuff in it. This is how we can clear a stack. There is no .clear method for a stack. So this is how you would clear it. You would just have to pop everything off of it. Then when we display the stack here on line 43, we get the empty stack, which is exactly what we expected. What's the size of that stack? It better be 0, right? Because it's empty, and that's exactly what it is right here, 0. And the last thing I wanted to show you is, suppose I push 10 onto the stack. Remember, that stack is gone. It's empty now. So let's say I wanted to push 10 onto the stack, just like I did right here. And then I display the stack, I get back a 10. Top returns a reference to the top of the stack. The top of the stack right now is the 10. It's a reference, so I can modify it. I could say s.top is 100. So I can change that top to 100 now. So when I display the stack, you can see it's displaying 100 right here. Okay, I think that's about it. That's really all there is to a stack. It's a very, very specific data structure that we're going to use. When you use it, all you care about is pushing, popping, top, checking to see if it's empty. That's it. You're not concerned with anything else. Those are the only methods that are important, and those are the only methods you actually want. If you've got a stack that gives you a bunch of other methods, it's not really a stack, and be careful, because you don't want to have a stack of integers, let's say 10, 20, and 30, and that whatever thing you're using that you think might be a stack is letting you have access to these guys. That's not a stack. A stack, everything happens right up here at the top. Okay. Sometimes you'll see these data structures defined by programmers that have pushes and pops and insert stack and all kinds of things, and it's not really a stack, it's just a mess. Okay. In this case, this is a true stack. It supports exactly what a stack is supposed to support. All right, in the next video, we'll talk about the queue, which is a waiting line. And of course, here you can see that the last one in was the first one out. That's why the stack is called a LIFO data structure. The queue is called a FIFO data structure. So the first one in is the first one out, like a waiting line or a waiting queue. And that's what we'll talk about in the next video. In this video, we'll learn about the queue. The queue is a first in, first out data structure. Like the stack, the queue is an adapter class because it's implemented in terms of already existing STL containers. Since operations on the queue happen on both ends, the front and the back, we can easily implement a queue based on any container that has a front and the back. These are the list and the deck. So the queue methods use delegation and call the methods of the underlying container. Like stacks, queues have wide applications in computer science, and the STL provides a simple, concise implementation. You can think of a queue as a waiting line. Elements enter on one end and are removed from the other. As with stacks, iterators really don't make sense with queues and they're not supported, so we can't use the STL algorithms either. In order to use the queue containers, we must include the queue header file. Like the stack, the queue provides a handful of methods that have very well-defined behavior. The push method inserts an element at the back of the queue. The pop method removes an element from the front of the queue. The front and back methods access the front and back elements of the queue, but does not remove them. Finally, we have the empty and size methods that we've seen with the other containers. Since the queue is an adapter class, we can choose what underlying container will be used. Same thing we did with the stack. In the first example, I'm providing no information about the underlying container, so the STL will use a deck by default. You can see in the next two examples that I'm explicitly stating which underlying container to use as the template parameter. Now let's see how the push method works. Suppose we have a queue of integers named q and it's empty. When we push 10 onto the queue, we add 10 to the back of the queue. In this case, the queue was empty, so 10 is both the back and the front element in the queue. Then when we push 20, we push it at the back of the queue. So now 10 is at the front of the queue and 20 is at the back of the queue. You can see the front of the queue as the shaded box in the diagrams. The back of the queue is the other end. We then push 30 at the back of the queue. Once we have a queue that contains elements, we can access the elements at the front and at the back without removing them with the front and back methods. In this example, queue.front will display 10 and queue.back will display 30. Now, when we pop elements from the queue, they're removed from the front. The first queue.pop removes the 10 from the front of the queue, and now 20 becomes the new front of the queue. The second queue.pop removes the 20 from the front of the queue, and now 30 becomes the new front of the queue. If we call the size method for the queue here, it will display 1 since there's one element in the queue. As you can see, the queue is really a very simple data structure, but like the stack, it's used extensively in computer science to solve many types of problems. So let's head over to the IDE and we'll see some queue examples. Okay, so I'm back in the IDE. I'm in the section 20 workspace and I'm in the queue project. And just like the stack, the queue is really simple. So let's go over some of these examples. First thing you'll see is I've already got the run over here on the right, and I'll discuss that in just a second. First thing you'll see is I've got this template function that displays the queue. Very similar to what we did with the stack. In this case, I'm passing by value because I don't want a reference to the real queue and I don't want to destroy it. So this is going to make a copy of the queue that's passed in, and that's the one I'm going to process. So how do I display this? Well, while the queue is not empty, I'm going to get the element from the front. Remember, with the queue, we push on the back and we pop from the front. So this is first in, first out. Right, so it's like a waiting line. Someone gets in at the back of the line, they come off in the front of the line. So I'm getting the element from the front, I'm removing it from the queue, I'm displaying it. That's it. Really simple. Okay, so let's talk about the main. Again, there's only one test here right in my main. First thing I'm doing is I'm creating a queue right here, and it's a queue of integers. Again, this could be just about any type. And I'm pushing 1, 2, 3, 4, and 5 onto the queue. Now remember, I'm pushing at the back. So when I push 1, I'm pushing it at the back, then 2, then 3, then 4, then 5. I display the queue, and this is what I'm getting right here. Now, what's the front, what's the back? Let's be sure that we understand what's going on here. We can say queue.front, queue.back, and you can see that the front here is the 1. Makes sense, right? It's the first one that I pushed on. First customer in line is the first customer out of the line. So that's the front. The back is the 5. Now I want to push 100 onto the back of the queue and display the queue again. And you can see the output right here. You can see the 100 here is at the back of the queue. I want to pop 2 elements from the front of the queue. So what happens is the 1 and the 2 get removed from the front and they're gone. So now what's left is 3, 4, 5, and 100. 3 is at the front, 100 is at the back. If I want to remove everything from the queue, I need to use some sort of loop like this. We can't use iterators with the queues. So while the queue is not empty, pop the front element out of there. And when I'm done, it'll be empty, and I display the queue, and I will get an empty queue, just like you see right there. When I display the size of that queue, I'm right here on line 42. I will get a 0 because it's empty right now. And let me just clear this, and I'll scroll up. And there's a few more lines, not too many. So we're right here. We're on line 44. I've got an empty queue at this point. I just printed out the size right here. So I'm going to push 10, 100, and then 1,000 onto the queue and display the queue. There you go. You can see 10 is at the front, 1,000 is at the back, and you can see that being displayed right here. 10 is at the front, 1,000 is at the back. Now, I have access to the front and the back. The front method and the back method return references. So if I wanted to change the front or change the back, I can. So in this case, I'm setting whatever element it is at the front to 5 and at the back to 5,000. You can see them change right there. Right? There were 10, now it's 5. It was 1,000, now it's 5,000. And you can see again that the front of the queue is the 5 and the back of the queue is the 5,000. So that's it. In a nutshell, that's the queue. So remember, this is first in, first out. as opposed to the stack, which was the last in, first out. And there's uses for all of these. First in, first out queues are used all the time for scheduling, job scheduling, task scheduling, and operating systems. Stacks are used a lot in compiling. They're used a lot to solve problems where you have to calculate expressions and you have to figure out how many parentheses are there, do they balance, and things like that. Okay, so that's it. In the next video, what we'll do is we'll do a challenge that's going to use stacks and queues. And you remember that palindrome example we did a while back with a deck? We're going to do the same thing, except we're going to use a stack and a queue to solve it. Hello, welcome to the Section 20 Challenge 4 video. This you've already seen before. We did this challenge in Challenge 1. This is where we decided whether a string was a palindrome or not. We used the deck in Challenge 1. What we're going to use here in Challenge 4 is we're going to use a stack and a queue to do the same thing. It's actually exactly the same main driver. The only difference is your function is going to be different, obviously, because it has to use a stack and a queue to solve the problem. What I would ask you to do is go back to Challenge 1 and play the description video where I go into what a palindrome is and so forth, rather than repeat it here. But if you're here already and you don't want to go over there, I'll do a real quick review. A palindrome is a string that reads the same backwards or forwards. So we have a couple of examples here: Madam, Bob, Toot, Radar. So no matter how you read it, from the left or from the right, it's the same word. And we can have entire phrases that are palindromes as well. So a Toyota is a Toyota, a Santa at NASA, a man, a plan, a cat, a ham, a yak, a yam, a hat, a canal, Panama. It's amazing that this actually is a palindrome. For palindrome phrases like this, what we're going to do is we're going to remove all the spaces and we're going to remove all the special characters and we're going to make those uppercase. So in the case of a Santa at NASA, what we're going to do is we're going to create that string from it. You can see it says a Santa at NASA right in there, but no spaces, everything's uppercase. And if there are any apostrophes or anything else, we're going to get rid of it. So we're only going to process alpha characters, and you can use the CC type header file for that. That's it. Good luck with this one. Like I said, go back to Challenge 1 description, and I talk a lot more about that. Actually, let me show you a sample run so you don't have to go back there. I'm going to show you a sample run of my solution here, and I'll build and run. The main driver, I'll show you the code also in a second. The main driver has a bunch of test cases that they run. All you have to do is write one function. It's called isPalindrome, and it returns true or false. I pass you a string, you return true or false. So in this case, A is a palindrome, AA is a palindrome, ABA is a palindrome, and so forth. Obviously, AB and ABC are not. Radar and Bob and Anna and Avadiva, and there's a Toyota's a Toyota, Santa at NASA. C++ is also a palindrome because what we're doing is we're removing the plus plus and just using the capital C. We're getting rid of the special characters. So there's some test cases, and here you can see the man, the plan, the cat, and so forth is a palindrome. You can read it the same both ways. So that's the sample run. And let me show you the main that I'm giving you. This is the main I'm giving you. It's the same exact main that I gave you for Challenge 1, except what I want you to do is I want you to use, you can see right there, use a stack and a queue before we use the deck. So this will give you a little bit of experience with that. You can see the main here. And all I'm doing in the main is I've got a vector of strings, and those are my test cases. And I'm just looping through that vector, and I'm calling your function isPalindrome right here. I'm passing in the string, and you're returning true or false, and I'm displaying that. Right, it's as simple as that. Here's the function you have to implement. It's called isPalindrome. It expects the string, and it returns true, false. Right now, I'm just returning false for everything. So if you run this right now, you're going to get, actually, I'll run it right now so you can see what it looks like. If I run this guy right now, it's going to say false all the way down the line because there's no real logic in that function. But it all runs and compiles and no worries at all. So that's it. If you solve the problem with the deck, you kind of know how to approach it. I'm not going to give you any hints here. If you have, if you want a hint or if you have questions, please post in the Q&A and I'll be glad to answer them there. All right, so good luck. I'll see you in the next video and I'll show you my solution. Okay, welcome to the Section 20 Challenge 4 solution. This is the challenge where we're trying to determine whether a string is a palindrome using a stack and a queue. So before I go into the code, let's talk about the process that we can use to do this. Suppose we have a word like radar. That's the string. Obviously, that is a palindrome. What we can do is we can have a queue over here, and we can have a stack over here. We can take these letters and push them to the queue. So it's going to be the R, the A, the D, the A, and the R. That's the order we're putting them in. So this is the front of the queue here. And then we can take the same word and push it on the stack. So in this case, we've got R, A, D, A, R. So I think you know what's happening now. This is the top of the stack. This is the front of the queue. What we can do is we can take those elements and compare them. Now, if they're the same, we can knock them off. Then we can go to the next one. If they're the same, we move on to the next one. And as you can see, it's pretty easy, right? At the end, we're done. If everything matched, we've got a palindrome. So that's it. Let's take a look at another example. So let's say that the word is rear, R-E-A-R. Obviously, that is not a palindrome. So we can have our queue over here, and we can have our stack over here. And what we'll do is we'll enqueue rear. So it's R-E-A-R. This is the front. And then we'll push rear onto the stack. So again, we'll say, and I'll separate those so make it clear, R-E-A-R. We'll look at the front of the queue and the top of the stack. They match, so we can get rid of those. Then we'll look at the front of the queue, top of the stack. They don't match. That's not a palindrome. Okay, so that's it. That's the solution. It's pretty straightforward. Now let's see how we do this in code. Here is the function. And let me walk you through it really quickly. So what I'm doing here is I'm using a range-based for loop to iterate over that string S that's being passed into me. And for each character, I'm checking, is it an alpha character? I'm not interested in anything else. If it is, I'm converting it to uppercase. I'm pushing it on the queue and then pushing it on the stack. That's it. That's going to set up those two data structures so that I can process them easily now. Now I'll scroll up. And there's the rest of the code. You can see that I've got two variables here, C1 and C2. That's where I'm reading the characters into. And all I'm doing is, while the queue is not empty, I could have used the stack as well here. It doesn't really matter because they both have the same number of elements. So while the queue is not empty, I'm assigning the front of the queue to C1, and then I'm getting rid of that character from the queue. I'm assigning the top of the stack to C2, and I'm popping that off the stack. Then I'm comparing the two characters. If they're not the same, I'm out. It's not a palindrome. When I finish this, if I loop and everything is done and I've processed all the characters, it must be a palindrome, I return true. That's it. And we'll run it just to be, let's build and run. And there you go. Those are the results. You can see the A is true, the AA is true, ABC here is false. A bunch of these phrases are true. And then obviously this is a palindrome and palindrome are not palindromes. So we get a false. So that's it. You can see a whole bunch of different ways to solve this palindrome problem. We did it with a deck earlier. We did it with a stack and a queue now. And there's other solutions as well. So I hope you had fun doing this. You can see that using stacks and queues and decks and all kinds of data structures are pretty fun, actually. All right. So I'll see you in the next video. In this video, we'll learn more about the priority queue. The priority queue is a container adapter just like the stack and the queue. The priority queue allows insertions and removal of elements in order from the front of the container. Elements are stored internally in vectors by default, but a data structure called a heap is used behind the scenes. Don't confuse a heap data structure with the heap that we used to store dynamically allocated data in our program. They're totally different. Elements are inserted in priority order, so the largest priority element will always be at the front of the priority queue. That's pretty cool. We can insert elements at the front, and when we get an element from the front, we're guaranteed that it will be the largest element in the container, and it's super efficient. Iterators make no sense with priority queues, so they're not supported, and neither are the SCL algorithms. In order to use the priority queue, we must include the queue header file. The priority queue has just a couple of methods that are super powerful. The push method inserts an element into the priority queue in sorted order. The pop method removes the top element from the priority queue, and the top method accesses the top element without removing it. The top element will always be the highest priority element, which defaults to the element with the greatest value. Finally, we have the empty and size methods as we've seen before. So let's see a simple example of using the priority queue. First, we create a priority queue and we'll call it PQ. Behind the scenes, it's using the vector as the underlying container. Then we push 4 integers onto the priority queue. And then we display the top with pq.top. In this case, 20 will be displayed because 20 was the largest element inserted into the priority queue. We can remove the element from the top with pq.pop. And if we display the top again, we'll display 10, since 10 is the next largest integer that was added to the priority queue. That's it. It's really very simple and very powerful. Let's head over to the IDE and I'll show you an example of using a priority queue. Okay, so I'm back in the IDE. I'm in the Section 20 workspace and I'm in the priority queue project. So what we'll do here is we'll play around with a priority queue. We'll do it both with integers and we'll do it with an object here, a person objects. So I'm including queue. That's where the priority queue lives. So I need to include that to make sure that we have access to it. We've got our good old person class that we've been using throughout this section. And again, it's same as it has been before. This is the really important one right here, that operator less than, that overloaded less than operator. That's one we're going to use in a moment. So remember what it's doing. What we'll do is we'll use it and then we'll change it. So remember what it's doing here. It's comparing ages. So that's the ordering that it's going to use. And that's what the priority queue uses as well. And let's see, we've got the overloaded insertion operator exactly like we did before. I've got a template function here that expects a priority queue of any type and it displays it. This is destructive, so I'm passing by value. You've probably seen this a bunch of times now with queues and stacks and you're getting used to it. So I'm just getting the free, while it's not empty, I'm getting the top, which is the biggest element. I'm popping it and printing it until it's empty. All right, so that's what's happening there. So let's take a look at these 2 tests. Test 1. I'm creating a priority queue and I'm looping through this collection of integers here and I'm pushing it on to the queue, to the priority queue, I should say. Remember, what's happening here is when they're being pushed in, the pushing all happens at the top, but behind the scenes, it's ordering. So it's using a heap data structure behind the scenes, so the top of this priority queue will always be the largest integer. Now, in this case, notice I have 357 here and I have 357 here. The duplicates will be put in there. It's okay to have duplicates in priority queues, so that's why I put them in there. So that's what we're doing here. We're pushing all of those integers. And then what's the size? Well, I pushed 12 of them. What's the top one? It's the biggest one. It's that 100 right there. When I display the priority queue, you can see 123, 12, 12, 7, 7, all the way down to 0. You can see the ordering. It's exactly as we would expect. The top, which is right there, it's that 100 right there. That is the greatest or the largest integer in the priority queue. So let me clear this up. So now what I'll do is I'll pop that max element from the priority queue. So that's going to take the 100 off. And then when I display the priority queue, now the new top is 23. It's the next largest number that was there. That's really all there is to a priority queue. Super powerful. A lot of times we have needs for something like this. Let's say we're doing operating systems and we're scheduling jobs and they have to run based on a certain priority. This is awesome. We use priority queues all the time because they make a lot of sense and they're super efficient. So let's take a look at test 2. In test 2, I've created a priority queue right here, PQ again, of person objects this time. And I'm pushing a bunch of person objects. Now, I named these people A through F just so we can see the ordering with the string. And then I've got some just random numbers here. We can see that the largest number is 27. Remember before we said that the operator less than for the person class was checking age. That's the discriminant. So in this case, when we put these things on these person objects on the priority queue and we display the priority queue, look what we're getting here. Notice that it's not ordered by name. We've got F and D and C and A and E and B. It's ordered by that age. So the person with the largest age is at the top of the priority queue. So we've got 27, 18, 14, 10, 7, and down to 1. That's it. That's pretty cool. So if I decided to, let me just stop this. And if I decided to change the order, remember right here it's ordered by age. So if I decided to come up here to my person class, let me scroll up a little bit right here. And let's say that I want to change this. So it doesn't check age. Instead, it'll do, let's say name. So we're going to return this dash name less than the right-hand side's name. Something like that. Now when we run this again, you can see the output right over here. Let me move that over just a little bit so I can write. You can see the output right here now is no longer by age, right? It just happens to be 27 there because of the F, but it's F, E, D, C, B, A, right? So F is the largest name. If we go the other way, we've got A, B, C, D, E, F, right? So there you go. So if I remove the top, it's going to remove F27 right there. That's it. That's it for the priority queues. Very useful data structure to know about. Dead simple to use in C++ with the standard template library. A lot of other programming languages have libraries that support just about everything that's in the STL, and they're all pretty easy to use, actually. What's really important is that you practice and you understand the STL. You just do a lot of examples. I did a lot of examples in these videos, and I did that, as I said, for a reason. It's really the best way to learn this is to just go along with me and tweak yours and make yours different and change like I just did right here. You know, change this and see what the effect is. And that's how you really, really learn this stuff. All right. So that is actually the end of the STL. Hooray, right? It ended up being a lot longer than I thought it was going to be. I re-recorded some videos, and I hope it's useful to you all. In this video, I'd like to go over the content in this section of the course. This is a very important section since we describe the installation of the tools necessary to create, build, and execute C++ programs. We wanted to make this course accessible to as many students as possible who want to learn C++. So if you're running Microsoft Windows, Mac OS X, or Ubuntu Linux, we have videos detailing the steps necessary to get set up and running on your platforms. The following section includes videos for installing the C++ compiler, the CodeLight IDE, and how to configure the CodeLight IDE for each specific operating system. Then we go over how to create a default CodeLight project template that you can use when you want to create a new C++ project. This makes it really easy to start new projects quickly since all the required settings will be ready to go. In all the videos, we use a real simple C++ program to test the installations. All of the elements of this C++ program will be explained in detail as we progress through the course. In this section, just type along and follow along to ensure that your installation is complete. In addition to using the CodeLight IDE, we want to be sure that students can learn and build C++ programs even though they may not be able to install an IDE due to hardware limitations. So we created a section that uses just a simple text editor and the command line tools to do just that. If you're unable to use an IDE, then please don't let that stop you from learning C++. You can still use the command line just fine. So we created a video for the command line for Windows, for Ubuntu Linux, and for Mac OS X. Finally, we include a video that uses a website that has a C++ compiler available that you can use to write and execute basic C++ programs. This has some limitations, but it's great if you're on the road or away from your own PC. All you need is a web browser, and you can run much of the code presented in this course. As the course evolves, we'd like to include videos for Xcode on Mac, Microsoft Visual Studio on Windows, Eclipse, NetBeans, and other major IDEs. We want this to be the most complete beginning C++ course available. In this video, I'll take you through the steps necessary to install the C++ compiler on the Windows operating system. We're going to use the minimalist GNU for Windows. Now, GNU stands for GNU's Not Unix. It's basically a compiler collection called GCC that includes the C compiler, a C++ compiler, a Fortran compiler, and an Ada compiler. Now, we're only going to be using the C++ compiler in this class. So we'll only install that. You open up your favorite browser and you go to mingw.org. You'll see a page similar to this. And what you want to do on this page is click on the button at the top right here called Download Installer. So I'm going to select that. And that'll automatically start a download of the MinGW installer. It's a pretty small file, so it should be a quick download depending on your internet connection. Okay, so I'm finished downloading here. And what I want to do is just run that installer. So I'm just going to double click on it and I'll close down the browser. Okay, so what we're going to do here is we're basically just going to follow the installation wizard. I'm going to install, and I want to install in C:*MinGW. Now, certainly this could be a different drive letter, but don't change the name of the installation directory, and certainly don't put spaces or anything in there. I'd suggest that you just keep the default if you can. Keep all the default settings and press continue. And this will start the download of the installation manager. Now, once the installation manager is downloaded, then we can continue and we can start downloading and installing the actual compiler. Okay, so when the download is complete, you can see that on my system it processed 113 items, and it only took a couple of minutes. I sped up the video so you didn't have to wait through the installation. Once you're finished, just press continue. And now you're going to be shown a window which is the installation manager. Now here, what you want to do is you want to click Basic Setup on the left, and you want to select 3 of these packages on the right. You want to select the msys-base down here at the bottom, and you select Mark for installation. You want to select the MinGW32-GCC G++ package. That package contains the C and the C++ compilers. And we'll mark for installation as well. And you want to select the MinGW32 base package. And we'll mark that for installation. Now once you've got those 3 selected, you can come back up here to the installation menu and press Apply Changes. Now at this point, we can click Apply, and it's going to download and install the GNU compiler. Okay, so that's the installation. It only took a couple of minutes on my machine. I'll select the close. And at this point, we're done installing the compiler. Now there's one step that you should take. In this case is we want to set the path variable on our Windows system to the binary directory. So let me show you how to do that. Open up your control panel. You can open it up down here, or you can open it up right here. I've just got a shortcut on my desktop. And you can search your control panel for env for environment variables. I'll just type env, and you can select Edit the System Environment Variables. Okay, now at this point, you want to come down here to where it says Environment Variables, and press that, and then down to System Variables and select the path right there, and you want to edit the path. And what you want to do is you want to add a new variable to the path. So I'm going to select New, and at this point you want to browse and find the directory where you installed the compiler libraries. So in this case it was my C drive, and it was the MinGW directory, and you want to go to the bin subdirectory and select that. That's where the binaries are, the executable files, and then press OK. And OK one more time, and just finish off and close everything up. That's it. The compiler system is now installed, and we're ready to compile. The next step is, if you're going to install an integrated development environment or IDE, now your compiler is all set up and you can proceed with that step. In this video, we'll go over the steps necessary to download and install the CodeLite Integrated Development Environment for C++ on the Windows platform. CodeLite is a free open source cross-platform integrated development environment that works across Windows, Mac, and Linux. And this is the IDE that I'm going to use in this class. In order to download it, open up your favorite browser and go to codelite, codelite.org. You'll get a page that looks similar to this, and what you want to do is find the download link. Now you can find it up here on the menu bar, or you can find it right here as well in the big blue button. So I'll select that, And it takes you to a page where you can make a donation to the developers if you wish. If not, just take me straight to the downloads and I'll select that. And you've got a couple of options here for Windows. If you want to download the weekly builds, you can download that for the 64-bit Windows machines right here at the top. And currently it's CodeLite 10.0.7. That's the one I've been using, and it's very, very stable. You can also download the stable release 10.0 for Windows 64 or 32-bit. Now, if you're not sure whether you have a 64-bit machine or a 32-bit machine, go over to your control panel and select System and Security, and then System. And in the system information right here, you'll see system type, and it will say 64-bit operating system or 34-bit operating system, depending on what you've got. So I'll close this down. And in my case, I have a 64-bit system, so I'm going to use the stable release for Windows 64-bit. And I could just click the direct link, and that'll start the download. The download can take some time. It's not a big file, but the connection tends to be slow to the site. So I'll pause the video while that occurs. So the download is now complete. What I'm going to do is open it up in the folder. And it's basically a compressed file, which I'm going to extract right to here. And then I'm going to run the installer. But before I do that, I'm going to close the browser. And let's run that installer. I'm going to allow the app to make changes to my device. And I'm going to close this folder just to clear up some of the clutter. Now, what you want to do here is just basically follow this setup wizard. So I'm going to select Next. I'm going to accept the GNU license agreement and press Next. I'm going to install this to the default location, C Program Files Code Lite, and press Next. I'll press Next again. And I want to create a desktop icon just to make it easier for myself. And I'll press Next one more time. And then finally, we can install. The installation is really quick. And once it's done, it's going to ask you if you want to launch CodeLite. I'm not going to launch it yet. I'm just going to finish the installation. And in the next video, we'll go over the launching and the configuration of CodeLite. In this video, we're going to configure the CodeLite IDE that we just installed to work on our Windows system with C++. So the first thing we want to do is we want to start CodeLite. So I'm just going to double click on the icon. And the first time that you run CodeLite, you'll probably get a little setup wizard pop up. And here it is. You may also get a window that says you want to update to the latest version, which you can certainly do. I'm going to cancel for this video. And here's the setup wizard. Now, it's important that you run through this setup wizard. If this does not show up for the first time, you can always find it up here. You can select Help, and then you can run the setup wizard here. But in this case, it does show up. So I'm going to go through this, and you only have to do this one time. I'm going to select Next. Now here, the way that CodeLite works is it uses a lot of plugins to support PHP, C, C++, and so forth. We only care about C++ in this case. So what we want to do is we want to clear these plugins. So you can see all the check marks are gone. And then we want to toggle the C++ plugins only. So I'm going to select that until only the C++ ones show up. Okay, so that's what we need to do. Just make sure that not all of them are set up, just some of them. You can use the toggle to do it. I'll select Next. Now we want to set up the compiler. Now, remember, if you've already installed the MinGW compiler, then you can just click Scan. If you haven't, go back to the video and install it. I wouldn't install it from this option because it installs an older version of the MinGW compiler. Okay. So I'm going to Scan, and it should find it. There it is. So I want to select it and press Next. Now here you can customize the colors to whatever you like. This dark Monokai theme is kind of nice on the vision. It's not so hard on your eyes. But for the video, I'm going to choose the classic Eclipse look. That way I think it shows up a little better on video. So I'll select Next. We'll leave these defaults as is, and we'll press Finish. Okay. Now at this point, you want to save and exit. It's going to ask you this every time you make a change, and it gets pretty annoying. So I'm just going to say, remember my answer and don't ask me again. And every time I make a change, I want to save and exit. So I'll save and exit. Okay, so it saves it and it opens it up again, and now the settings that I set were applied. And again, I'll cancel the new download here. Okay, so let me make this full screen here. And as I mentioned before, if that setup wizard does not show up, you can start it here. Run the setup wizard. Okay, so now what we want to do is we want to create a new workspace. And once we create the new workspace, we'll have a couple settings to do, and then once that's done, it'll be all set. So let's create a new workspace. A workspace is basically an area where you can have different C++ projects in. So the first thing we want to do is create a new workspace. I'll select that. You can also say File, New Workspace. Okay, so I'll do it right here. And it's going to ask me for the name of the workspace. So I'll just say CPP Workspace. You could do this whatever you like. If you want to have a workspace for all the Section 1 exercises, Section 2, Section 3, or whatever you like, whatever makes sense for you. I'm going to put it in my Documents folder, and I want to create the workspace under a separate directory. That just helps me organize my files. I'll select OK. Good. Now you can see here on the left pane on my workspace view, I've got a workspace. Now the workspace in and of itself isn't real useful. I need to create a project within the workspace. So I can right-click on Workspace and say New Project. So I'll do that, and I'll select New Project. At this point, we've got some options. We're going to select the console option, and then Simple Executable G++. That's basically the C++ compiler. It's called G++ because it's from GNU. So I'll select that, Next. And then you give your project a name. This could be, again, any name you like. Avoid spaces just to be safe, just simple name. So I'll say Test1, let's say. And again, I want to create a project in a separate directory. I'll press Next. Here you can choose the compiler. It's probably already chosen it for you. If you've got multiple compilers, you can set individual compilers on a per project level. But we're using the MinGW compiler, and we're using the GNU debugger. The build system will be default, and select Finish. So it's gone off and created a new project. You can see it here on the left side. It's called Test1. And as I explode these, you can see that there's my main CPP file. That's the program that it's created for me by default. The .cpp extension means that it's a C++ file. I'm going to double click on that. And you can see my font is pretty small here because I just installed this. Let me increase my font. You may not have to do this on your end, but it's going to show up better on video if I do it. So I'm going to go to Settings, Colors and Fonts, and I'll just set it to 16. I think should be nice. Apply, okay. There we go. That way it's much easier for you to see. Now what we want to do is we want to delete all this. This is actually C code, not C++ code. So let's delete all that and let's write a real simple test from scratch. So the first thing we'll do is we'll include IO stream. This allows us to do input and output. And we'll talk much more about what these include directives mean in a future video. In this example, just type along and make sure that the environment is working. So you want to say #include and IO stream in angle brackets. Then we want to say int space main. This is our main function. 2 parens. And we'll create a couple of curly braces. And then in here, all we're going to say is std : cout, the insertion operator, which is 2 less than signs, followed by hello testing, or anything you like, and then a semicolon at the end, and then finally return 0. That's it. That's a simple test. Again, there'll be a separate video where I go over the anatomy of a C++ program, and we'll go over all this in detail. So in this case, again, we're including IO stream. We've got our main function, and we're printing hello testing to the screen. We're returning 0, which means program successful. Okay, I'm going to save this, and I'm not going to do this on the videos, but you can certainly do this at home. If you come up to View, and you can toggle the minimal view, when you do that, you'll get some icons up here. And you can use these icons to build and save. For example, that's the save right there. I'm not going to do that because I want as much screen real estate as possible on the videos. So I'll just toggle that off. Okay, so I'm going to File Save. And at this point, we're ready to run the program, but we need to make a couple of changes just because we want to use modern C++. So what we can do is we can click on the project, Test1 in this example, and I'll right click, and down at the bottom you'll see Settings. So we'll select settings. And you can see right down here at the bottom where it says global settings, I want to select that. And where it says C++ compiler options, you can click right in there, and then you'll see these three little dots here on the button. So it gives us another menu. So you can select that. And we want to make sure that a couple of things are set. We want to be sure that C++ 14 is checked. That means we're using the latest version of the standard, which is modern C++. We also want to be sure that the WALL, all warnings, is checked. Okay, so that's it for now. That'll be fine. We'll select OK. And we'll apply and OK. Perfect. Okay. Now, I also want to click on the workspace itself and right-click on that and come down to workspace settings and select that. And when you come to code completion, you want to be sure that C++ 14 standard is enabled. Okay. Code completion is something that the IDE does. As you type, it's trying to figure out what you want to do and help you out, so you don't have to do a lot of typing. And in this case, we want to tell it to use the C++ 14 standard when it's trying to figure things out. So I'll select OK. Now at this point, we should be ready to try this out. So I'm going to expand this little window down here at the bottom, and I'm going to come up to where it says Build, and then we'll select Clean Project. And then we'll go back to Build and just say Run. At this point, it's going to say, what do you want to do? Do you just want to run it, or you want to build it and run it? In this case, I want to build it and run it. And I'll talk more about the workflow that's used for cleaning and compiling and so forth a little bit later on in the course. So in this case, I want to say build and execute, and it will compile and run the program. If there are no errors, it'll run, and you'll get a window pop up with the output hello testing in there. If there are errors, let me show you what they might look like just in case you do see them. Suppose I forget that semicolon at the end there. And I'm going to say build, run, build and execute, and you can see this red down here that says error expected a semicolon before the return. You also get a red error here, and it says again semicolon expected. So basically you just put the semicolon in there, save it, and then go back up to build and run, build and execute. You can click on here for it to remember to always build and execute, or just execute. Again, don't do that yet. We'll do that as the course progresses, and I'll show you the different workflows we can use. So build and execute. There we go. Now, if at this point you get an error that says that some DLL can't be found, then what you want to do is you want to go back to the project, right-click, and go down to Settings. And remember, you only have to do this if you get some kind of runtime error that says some CPP DLL file is not found. And go to Global Settings. And then what you want to do is you want to go to the Linker Options and just select right on there and click that little button. And down here at the bottom, what you want to do is you just want to add a couple of lines. You could say -static -lib_gcc, and then press enter, and that -static -lib_std C++. Okay, so what will happen here is now the linker is going to statically link the files and not have to use dynamically linked libraries or DLLs. Again, you only have to do this if you get that error. If you don't get the error, you can do it also, and it's not going to hurt. But I'll select OK, apply, and let's do a build, rebuild. Let's do a clean first. Whenever you change any kind of settings, you want to clean the project, which really just cleans everything up and gives you a starting place. So we'll clean the project, and then we'll just say run, build and execute. In this case, it's going to statically link it, which is just as good. And hello testing, we're all set. At this point, we've got a good install, it's configured, and we're ready to use CodeLite to start learning C++. In this video, we'll go over the steps necessary to install the command line tools, which includes the C++ compiler on the Mac OS X platform. In order to do this, we need to have a terminal window. So let's go over to Spotlight Search and type in terminal, and we'll get a terminal window running. At this point, we want to type xcode-select --install and press enter. If you get a dialog box that pops up, as I do, that means that the command line tools and the compiler are not currently installed. If you get a message saying that they are currently installed, then you're done. You can move on to installing the integrated development environment. In this case, I have the choice of installing the full Xcode integrated development environment or simply install the command line tools. I'm only going to install the command line tools, which again includes the compiler. So I'll select install. I'll agree to the license agreement. And the software will be downloaded and installed. It's a pretty quick process. After a few minutes, you'll see a message saying the software was installed and the installation is complete. You can test out the installation by simply typing G++ --version at the terminal. And you'll see the version number of the C++ compiler, which means it's all set and good to go. At this point, you'll keep the command line tools up to date through the App Store. So you could select App Store, Updates, and you can see your command line tool updates will appear here. Right now I've got no updates available because I just installed the latest. That's it. We've installed the command line tools, our compilers are all set up, and we're good to go. The next step is to install the integrated development environment. Now that we've downloaded and installed the command line tools and the C++ compiler, we'll now install the CodeLite IDE. CodeLite is an integrated development environment that's cross-platform, open source. It runs on Mac OS X, Linux, and Windows. In this video, we're going to install it on Mac OS X. So open up your favorite browser and go to codelite.org. That's codelite.org. And you'll see a web page similar to this. You want to find the download link. You can see one here at the top bar menu, and there's also this big blue button, which is the one I'm going to click on. I'll select that, and it takes you to a page where you can contribute to the developers if you wish, or you could just go straight to the downloads, and I'll do that. So I'll select right here, not now, take me to the download. Now here we've got some options we can install for Windows, for Mac, for Linux, and so forth. We're interested in Mac in this example. So the third one down says CodeLite 11.0 app bundle for OS X. That's the one I want. And I'm going to select the direct link to begin the download. The file is not very large, but the download's quite slow from this site. I'll pause the video while the download occurs. Once the download is complete, you can see that it's downloaded a compressed archive file. So what I'll do is I'll open that, and I'll double click on it to uncompress it. There's my CodeLite app, which I just dragged to my applications folder. That's it. CodeLite's now on our system. In the next video, we'll run CodeLite and configure it to use C++ compilers on Mac OS X. In this video, we'll run and configure CodeLite on Mac OS X. Now, we've already installed the compiler tools and we've installed CodeLite. So let's run CodeLite. We'll come up to Spotlight Search and type CodeLite and double click on the icon. We'll allow it to run. Now, the first time that CodeLite runs, a couple of things will happen. You'll get this small CodeLite window show up, and then you'll get a setup wizard. We can just leave that window small. We'll make it larger in a minute. It's not really going to get in our way right now. What's important is that we run this setup wizard. If the setup wizard does not start, come up to CodeLite's menu and go up to Help, and then run the setup wizard and run it manually. Okay, but here in this case it did pop up, so let's select Next. CodeLite uses a bunch of plugins to allow support for PHP and Node and other technologies. We don't really want all that. We only want the C++ plugins. The rest are just going to clutter up our interface. So what we can do here is we can press clear and then just toggle the C++ plugins. That way only some of these will show up, which is exactly what we want. We just want to concentrate on C++. Select Next. Now we can scan our computer for any installed compilers. We can press this button here, and you can see it's found GCC, Clang, and across GCC. We're going to use GCC. They're really the same, but we'll use GCC here. And press Next. Now the customization of the theme is really up to you. This is your personal preference. The Monakai dark theme is real nice and easy on the eyes, but it doesn't show up too well on video. So I'm going to select the classic Eclipse theme and select Next. We'll keep these defaults and press Finish. Now what we can do here is we can say save and exit. You want to be sure that you save so we can save the changes we've made. And we can run CodeLight again. Okay, so this time I'm going to make this window nice and big. And we've got a couple of options that we still need to configure. But before we do that, we need to create a workspace. You can create a workspace by clicking this button here, or by coming up to File, New, Workspace. Either place works fine. A workplace is just an area where we can have our C++ projects. So we can have multiple projects in a workspace. So I'm going to select New Workspace. And the workspace name could be anything you like. I'm going to say CPP Workspace. Don't use any spaces here, just keep it all together. And I want to create the workspace under a separate directory so I can keep my files organized. I'll select OK. And you can see that it's created the workspace over here on the left pane. Now we need to create a C++ project. So you can right-click on that and select New Project. Or you can select the workspace and then come up to File, New Project. Either way. Now we've got some options. We're going to create console project and simple executable G++ right here. And that's the compiler we're going to use. And we'll select Next. The project name, again, don't use any spaces here, just create your name, the name for your project, whatever you'd like. I'm going to create a separate directory for each project, and I'll select Next. As far as the compiler, we want to use the GCC compiler, but the debugger, we don't want to use the GNU debugger, we want to use the LLDB debugger. That's the Apple debugger. We'll select Finish, and you can see over here on the left that we've created a project called Test1, and it's got a source directory, and it's got a file there called main.cpp. Now, before we run that file, there's a couple of things that we need to set up. First, click on the project, in this case Test1, right-click, and then come down to Settings, and select that. Then down here toward the bottom where you see Global Settings, come up to Compiler Options, and select the right side, and then you'll see this little button right here with the 3 dots. Select that, and what we want to do here is we want to check a couple of options. I'm going to scroll all the way up, and I want to select Enable All Compiler Warnings, WAL, and I want to enable C++ 14 features. That's the latest standard, that's modern C++. I want to make sure that that's enabled. And this guy doesn't come on, but you can see that it is there. Sometimes it doesn't check on. You can see that the command line is correct. So just click OK. I'll apply and click OK. Perfect. Now go to the workspace, select it, right-click on it, and come down to Workspace Settings. And you'll see we have Environment and Code Completion. Select Code Completion and check the Enable C++ 14 standard. The integrated development environments use code completion. They try to figure out what you're typing and what you want to do and where you want to go, and really help you out with suggestions. In this case, we're simply telling CodeLight to use the C++ 14 standard for those suggestions. I'll click OK, and that's it for the setup. Now let's modify this C++ file and run it. Let's double click on that, and that font is really small, so what I'm going to do is I'm going to make it a little larger so it shows up better on the video. Most likely you won't have to touch it at all, but I'm just going to come to Settings, Colors and Fonts, and I'll set the font to, let's say, 18. And I'll apply that, and that should be much more readable. Okay, so now let's modify this file. This is actually C code, not C++ code. So let's get rid of all this, and we'll type a simple C++ program that'll test our installation. During this course, I will go in detail through the anatomy of a C++ program, and everything that I'll be typing here will be explained. But for now, just follow along, type along to make sure we've got a clean install. So the first thing we want to do is we want to type #include, and we want to put IOStream in angle brackets and press enter. Then int space main, left paren, right paren. Then we want to open up a left curly, and you can see that the IDE has closed it for me. And then what I want to do here is I just want to say std, 2 colons, side by side, no spaces, and then cout, the insertion operator, which is 2 less than signs, again, together with no spaces. And anything you want to type here as far as hello, testing. We want to type a string inside double quotes and a semicolon at the end. And then the next line will be return 0. That's it. That's the entire program. When we run this program, what we want to do is we want to display hello testing to the console. That's all it's going to do. I'll save this under Save File. At this point, on your end, you may want to do View, toggle minimal view, and that'll display, let me do that again. That'll display some buttons and things up here, which you might find useful. I'm not going to do that because it clutters up the screen, and I don't want any distractions when I'm teaching the class, so I'll toggle that away. And what I'll do is, rather than click on the buttons, I'll be really explicit as to, let's click on build, run, build, clean, and so forth. That way you can see exactly what's going on. Once you get familiar with the IDE, you can use those buttons. That's it. So I've saved it. Now I want to run this. First thing I want to do is I want to go to build and clean the project. When we clean a project, we're basically just wiping out everything that's been done in the past except the source code. So the project is in a state that's ready to go. So I'm just going to clean it. And then I'm going to come back up to build, and I'm going to say run. Now it's going to give me an option that says, would you like to build the active project before executing it? Of course I do, because I haven't built it yet in this case. So I'm going to select build and execute, and that will compile the program and open up a window, and there's the output right there. Hello testing. So this terminal window is running the program that I just wrote. That's it. It's as simple as that. Some things could go wrong though. Suppose that you forgot this semicolon here, and I'll save it, and then I'll do the same. I'll do run, build and execute. And you can see if I move this window just slightly up, you can see that I've got a compiler error. And this is what compiler errors look like. You see the red text here, and it says error expected a semicolon after an expression. Also, you'll see that little red arrow right here telling you that there's something wrong here. And basically what you need to do is put a semicolon there. Just type the program really carefully, exactly like I did, and you won't have any problems. But you know, you could have things missing, like this quote, this first quote is missing. You might have 3 less than signs. There's all kinds of little things that could go wrong with the program. But if you just be very careful, type it in, save it, and come back up to build and run, build and execute, and you can click on there if you like. That way you don't have to keep doing it all the time. And there's the run. That's it. We're all set on Mac. We've installed the command line tools. We've installed CodeLite. We've configured CodeLite, and we're good to go. Now let's start learning C++. In this video, we'll be installing the CodeLite IDE, or Integrated Development Environment, on the Ubuntu Linux platform. CodeLite is a free open source cross-platform IDE that works with C++ and it works across Windows, Linux, as well as Mac. So we'll start by opening up your favorite browser and going to CodeLite, that's CODELITE.org, and you'll get a web page similar to this, and you want to find the download link. Now, there's one at the top menu, and there's also this big blue button here. That's the one I'm going to use. So I'm just going to select CodeLite to download. And you can give a contribution to the developers if you wish, or you can go straight to the downloads, which is what I'll do here. Now we're going to download CodeLite 11.0, which is a stable release. and we're going to download this for Ubuntu. Now you can see here you've got a Windows installer, an OS 10 installer, and so forth. And you can refer to those videos if that's the platform you're on, but this specific video is for Ubuntu Linux. So you can see here it says set up CodeLite repository for Ubuntu. That's the one I'm going to select. A word of caution, these commands are run as super user, as you can see here with the sudo. So be very careful when you type things in, make sure you're typing things exactly correctly. What I'm doing is I'm not even going to type, I'm simply going to copy and paste. That way I know that I'm making no mistakes. Okay. So first step is to copy this one line right here. And basically what we've got to do, there's a lot of information on this page regarding official and unofficial and so forth. And I'll show you the one that worked great for me. So what we're going to do is we're going to copy this line of code here. Then we're going to copy this line of code here. And the version I've got is Xenial Universe, so that's the one I'm going to, it's 16.0 for Ubuntu, so that's the one I'm going to choose. And then we're going to do a couple more lines and that's it. Now the install takes quite a while. The last time I did this install, it was about 10 minutes, 15 minutes on my machine. So I'm going to pause the video as the install happens. And we're going to do the install in a terminal window. So you can see the terminal window is here. I've opened it up. So I'm going to make this just a little smaller so we can do both at once so you can see what's going on. Okay, perfect. So let's get started. Let's copy this first line right here. And I'm going to copy and paste it over here. Press enter. And it's going to ask you for your password. Obviously, you have to have root access or be super user to install this code. So I'm going to press enter. And that takes care of the first line. Now I'm going to scroll down and get the second line. Now make sure that you replace this string here with the correct distribution of your Ubuntu. Mine is Xenial, so that's the one I'm going to use. I'm going to copy this just like that. I'll paste it. This time it won't ask me for my password. Then I'll go down to the third line, which is the update. I'll copy that and paste it as well. And that'll just take us a few minutes. Okay, that's done. Now the last line is the one that takes a long time to install, so I'm going to copy, I'll paste, I'll press enter, and I'll go have a cup of coffee in a little bit. It says here, after this operation, we need 451 megabytes of disk space. I've got plenty of disk space, so that's fine. And I'll just say continue, yes. And I'll pause the video now and be back in about 10 minutes. At this point, CodeLite has now been installed. In the next video, we'll run it and configure it. Now that CodeLite is installed, we need to run it, configure it, and then run a little test program to make sure our configuration is correct. So the first thing we want to do is we want to find CodeLite, and you can just type code in the search and you'll find CodeLite, and double click. Now the first time it runs, you may get a small window like this, and it's probably a good idea just to make it a little larger. Okay, now, sometimes when you run it the first time, you'll get a setup wizard that runs. Sometimes you don't. We'd like to run the setup wizard. So if it doesn't show up, you can go to Help, Run the Setup Wizard, and select that. And you get a window that pops up. So I'll select Next. Now here, CodeLite supports PHP and Node and a few other technologies. We really don't want all that clutter on our IDE. We want to strictly concentrate on C++. So I would suggest that we clear all the plugins and then turn on only the C++ plugins. So you can see now that not everything is checked. Only the C++ plugins are checked. And we'll select Next. Now we'll scan our computer for any installed compilers. So we'll scan the computer and it's found GCC and cross GCC. I'm going to select GCC. GCC stands for the GNU Compiler Collection, which includes C, C++, Fortran, Ada, and a few others. I'll select Next. As far as the editor theme, this is really a preference for you. This dark Monokai theme is really easy on the eyes, but it doesn't show up too well on video. So I'm going to select the classic Eclipse look for the videos. You can choose whatever your preference is, and I'll press Next. I'll leave these defaults as is, and press finish. Okay, now sometimes it opens up two windows like you see here. So I want to save and exit, and I want to shut down all the versions that I've got going. I don't know why it does this, but it does it a few times, and I'll save and exit again. All right, so now we're back to normal. Let's try that again. So we'll run CodeLite, and let's make this full screen again. Perfect. Okay, so now what we need to do is we need to create a workspace. A workspace is an area where we can have our C++ projects. So we can have many C++ projects in one workspace. We can do that by selecting this button here called New Workspace, or we can go up to File, New Workspace, either place. So I'm going to select this button here. And it's going to ask you for the workspace name. This could be any name you like. I'm going to say CPP Workspace, and I'm going to put this on my desktop. You can store it anywhere you like as long as you remember where it's at. So I'm going to put this on my desktop. I want to create the workspace under a separate directory that'll help me organize my files better, and press OK. That's it. Now we've got a workspace, which you can see here on the left side. I can right click on that now and create a new project. Again, I can also go up File, New Project. So I'll do that. Now we've got some options here as to which template to use to create the project. We're going to stick to the console template, which is just basically a terminal window. And we want G++. That's the C++ compiler. It's called G++ because it's the GNU C++ compiler. I'll select Next. What's my project name? It could be anything you like. Don't use spaces for any of these project names. So I'll just say test1. And again, I want to create a project in a separate directory under the workspace. So I'll select Next. Now it's going to ask you which compiler do you want to use. You may have a lot of different compilers on your system. Just select the one that you used in the setup wizard and you'll be fine. And these defaults are perfectly fine. We'll select Finish. And that creates a test project under the CPP workspace, and you can see it's created a source directory, and in there it's got a main CPP file. That's our C++ source code, and we'll get to that in a second. We need to do a couple of bits of configuration though before we do anything else. Let's go to our project, test1 in this case, and we'll right click and we'll go down to the bottom where it says settings, and we'll select that, and then we'll go to where it says compiler options. And notice I'm in the global settings. That's pretty important. I'm in the global settings, compiler options. And then I'll select these three little dots here on the button. And I want to make sure that W all is selected. That way we always get warnings. And I want to make sure that the C++ standard, C++14 is selected. That's the latest standard for C++. That'll make sure that we're using the modern C++ compiler. At that point, you can click OK, Apply, OK. Good. Now we can go to our workspace and right click on that and come down to workspace settings. And you'll see environment and code completion. Go to the code completion and select enable C++14 standard. The code completion is a tool that the integrated development environment uses that tries to figure out what I'm typing and what I want to type. And it helps predict what I want to do so it can help me so I don't have to type so much, and it can do some checking as it goes. In this case, I'm just telling it to use the modern C++ compiler. I'll select OK. And that's it. Now we can run a simple test program. We'll double click the main CPP file. And this is actually C code, not C++ code. So we'll delete this in a minute, but that font is a little small. So in my case, since I'm doing this on video, I'm going to go to Settings, Colors and Fonts, and I'm just going to set that to about 16. And let's see. That's much better. You should see that much better. Okay, so let's delete all of this. And we'll write a really simple C++ program. As we go through the course, I'll talk about the anatomy of a C++ program, and we'll go into detail as to what everything I'm going to be typing here means. But for now, just type along and let's get a clean run so that we know our environments are set up. So the first thing we want to write is we want to write pound include and iostream inside angle brackets. Then we'll press enter. Then we'll say int main and open and close parens. Then we'll type a left curly, and the integrated development environment will automatically close that for me. And here, all I want to do is say std 2 colons and cout. Then the insertion operator, which is 2 less than signs with no space in between, and just some string saying hello testing or anything else you like. That has to be in double quotes. And then finally, we'll put a semicolon on the end of that to terminate. And then finally, the last statement will be return 0. That means that the program terminated correctly. That's it. That's our first really simple C++ program. And like I said, in the beginning of the course, I'll go through what all of this means, and we'll go through the anatomy of a C++ program in great detail. I'll save this. Another option you may like is if you come up here to the menu and you say View, and it'll say Toggle Minimal View. And you can see it's put in a bunch of buttons up here. If you like this, this is great because you can run and compile and do all kinds of things just by clicking on a button. I'm not going to use that because I find that's pretty distracting to the video. So what I'm going to do is I'm just going to shut that off on my end, but feel free to use it. I'm going to use command keys, and I'll also just come up here and say, build, and that way it's very explicit what I'm doing rather than just clicking on a button. So that's it. So let's run this now. What we'll do is I'll say build. First thing I want to do is I want to clean this project. That way there's no remnants of anything left over. It'll put it into a stable state that's good to go. So I'll clean the project. Any messages will show up down here. Then I'll say build, and I'll just say run. And it's going to ask me, do I just want to run it or do I want to build it and run it? Well, in this case, I have to build it and run it because I haven't built it yet. So I'll select build and execute. And if all goes well, we'll get a window that pops up that says, hello, testing, exactly what we typed here. Press any key to continue, press enter to continue, which I'm going to press now. The window goes away and we're done. Now, several things could go wrong here. You may have an error in your program. You might have forgotten to type this exactly right. So you may have forgotten the semicolon. In which case, when you go to build and run, you'll see this red line here. That's a compiler error. You'll also see a red arrow over here telling you there's something wrong here. And the compiler's telling you it's expecting a semicolon before the return. So put it in there. Just be really careful. I'll talk about debugging and fixing syntax errors throughout the entire course. But at this point, save it, make sure it's right. Again, be very careful. You may have extra quote marks and the compiler won't like it. You might only have a single less than sign here and it's not going to like it. So just be sure it's exactly like this. Once you've got it set up, build, run, build and execute. There's a clean run and there's my terminal. Okay, so that's it. We're all set to learn C++. In this video, we'll go over the steps necessary to create our own custom project template. The idea here is that we can create our own project template, so when we create our projects, we can use this template as the starting point. That way, we'll have a proper main.cpp file, we'll have all our switches set, we'll have our environment set. All right, so let's get started. First thing you need to do is open up a workspace. I've got a workspace already open. I already created, I should say. I'm going to open it now. I'm going to say open workspace. If you don't have a workspace at all, you could just say File, New Workspace. So I'll open the workspace that I've got. It's on my desktop, and it's called CPP Workspace. So I'll open that. And the first thing you want to do is you want to add a project. So you want to right-click on your workspace and say New, New Project. Now here you've got the New Project wizard. And you've got different examples. You can create GUI applications, console applications. You can have user templates and so forth. What we want to do is we want to use the simple executable G++ template that comes with CodeLite. And we want to tweak that our own way. And then what we want to do is we want to create our own template in here that we can choose. And we could put it in console, or we can put it here in user templates. We could put it wherever we'd like. Okay. But before we do that, we need to create a project. So let's do that. I'm going to select console, and let's use the G++ simple executable console template. I'll press next. The project name, it doesn't really matter. I'll just say sample, since we're going to save it as a template anyway. And I'll select next. We want to make sure our compilers is set up correctly. Here I'm using MinGW and the GDB debugger. I'll select finish. And that creates our project. You can see here's the source file, and here's the CPP file, which is really C code and not C++ code, but we'll fix all this in a minute. So first thing we want to do is we want to get rid of this. And let's write a simple C++ program. So the same one we've been writing all along. So we'll say include IOStream. We'll include IOStream since we're going to probably use it in most of the projects that we write. Then we have our main function. And again, it's int main, open, close, parens, and then an open curly, which will be automatically closed by CodeLight. Here we can indent in by just pressing tab, and we could say std, : cout, and then the insertion operator, followed by the string hello world. And you can type anything you like here for hello world. And we'll do also an std, : and endl. This prints a new line. That way when we display hello world, the cursor will go to the next line on the console. And then finally, we'll just return 0 like we always do. That's it. I'm going to save this. So I'm going to press Control S here. So I've just done that and saved it. Now we'll set some compiler settings. We'll do this the one time, and then we'll save it as a project template. So let's go to the sample project, the actual project name, and we'll right click, go down to settings, global settings, and we want to make sure we've got those two compiler options set. So we're going to right click on those three little dots here on the button. You want to select that button and click. And we want to make sure that we've got our all warnings enabled on and our C++ 14 standard on. Press OK. Then you want to come to where it says code completion and select that and select enable C++ 14 standard, apply. And that's it. Now what we can do is we can come to the project again, right click and say save as template. So I'll select that. And what's the project name? This could be anything we want. We could just say Frank template or template for course or any name you like. Rather than that, I'm just going to say Frank, let's see, G++ console template. I think it's pretty picky about spaces, so I'm just going to use those dashes. And it is a console application. We could, that if you leave it as console, it'll be in the console group. I'm actually going to change that to user template. And then you can give it a description you want. I'll just say Frank's console template. That's it. I'll select OK. And now we've got a new template that's stored. So if I go back to my workspace and I want to create a new project now, let me close all this up. I'm going to right click and say new project. And now you can go down to your templates and go down to your user templates right here. And you should see that one we just created right here. So we can just select that. Next, I'll just say project 1. Select next. Keep the defaults for the compilers and finish. At this point, you can double click here to make that project the active project. And we'll look at the main CPP. You can see it's the main CPP that we just typed. Also, if you right click on the project and you go down to the settings, you can see code completion is C++ 14 and the global settings have the appropriate compiler flags that we need. That's it. We'll test this real quick. Let's run, build and execute, and hello world. That's it. So now you've got a project, you're all set up. You can create as many of these as you like, tweak the settings as far as you like. It's really up to you to decide what you want to do with the project templates. But for this course, include IOStream, give yourself a main. You may or may not want this line right here since, you're probably going to get rid of it anyway when we start writing other code. But at a minimum, do something like that. When you create a new project, you'll be ready to start coding. Hello everyone. In this video, I'd like to show you how to use the source code that's provided with the course. Each section of the course contains a compressed zip file that contains a workspace and all the projects that I've created in that workspace. So for example, suppose that we're working on section 8. There'll be a section 8 zip file. It may be a different name, but it'll have everything that you need in there. And what you can do here is just extract that file, and I'll extract here. And I'm simply going to extract it right to my desktop. As you can see, the folders have all been extracted. So if I double click on section 8, you can see all the projects in there. Now there's one special file you'll see down at the bottom here. It's called section 8, and it's a workspace file. If you right click on that, you can open with CodeLight, and that'll open up the workspace in CodeLight. And once the workspace is open, you have access to all the projects in there. So that's one way to do it. Another way to do this is, once you've extracted the file, just open CodeLight. Okay, so now once CodeLight is opened, you can choose to open a workspace right over here. So I'll select that, open workspace, and then you can just navigate to the workspace you want to open. In this case, it's section 8 workspace. You can just simply select that file, and you can see the workspace opens up right here with all your projects. Now I'm going to close the workspace and show you another way to do it. Would be right up here. You just come to workspace. If you have a workspace that's already open, you can simply workspace close. It wouldn't be grayed out. It would be right there. In this case, I just want to open a workspace. And again, you navigate to the workspace you want to open, select it, and there it is. So now I've got section 8 workspace with all the projects that I created and provided for you. In order to run these projects, you simply double click the project you're interested in. So suppose I'm interested in this Euros project. You can see the source code. And all you really need to do is build and run. But I'd suggest that you clean it first, especially if you're going from Windows to PC to Linux. I'm developing on Windows, so if you're on a Mac or a Linux machine or even a Windows machine, it's always a good idea to clean the project. And what you can do, you can right click and clean, or you can come up to here where it says build clean. So we'll clean the project. That removes all the object files, the exe files, and just gets rid of a bunch of stuff that you may not need depending on your system. Now that we've got that ready, we can simply build and run. And we should be good to go. Euros to US dollars, so we'll type in 100. $119 is 100 euros. So that's it. It's really pretty straightforward. What I would suggest is that you create, obviously, your own way of organizing your files. I'd use folders or directory structures. And also, something that's important to understand as well with CodeLight. CodeLight does things a little differently. So suppose that you've got projects in another workspace, and then you select the workspace here, and you say add existing project. Well, what happens here is it doesn't actually copy that project into the workspace. It'll create a new project in this workspace, but the files will still be where they were before. So your .cpp files and your header files and everything will still be where they were. So think of this more of a logical project rather than a physical copy of it. Okay? But once you play around with it, you'll understand exactly what's going on. So really straightforward. You've got the zip files that we're providing. Unzip them. You'll have a folder structure, and then just open that workspace file in there. All your projects should come in, no problem at all.
Congratulations on reaching the end of this course. I'm Tim Bachalka from the Learn Programming Academy, and the Learn Programming Academy is the publisher of this course. So this quick video is designed to get some free and valuable development information into your hands today. You know, when I was studying way back in the 1980s, which I know was a long time ago, it was hard to succeed as a programmer. There was no internet for starters, but also other than books or universities or colleges, there really was no way to basically talk to anyone or get access to the information you needed to succeed. So you're largely on your own, in other words. So I wanted to change all that and give you all the tools and information you need to succeed. And as such, I'm trying to pass on my wisdom and experience to make your goals of becoming a programmer or getting a better programming job, make that goal a reality for you. So I'm going to promise you here and now that the information that I put together is really useful to you as a developer, and it will make a difference. So let me explain the information I'm giving away to you free today. So firstly, I'm giving you free access to my Learn to Code course. And in this course, it's different to the courses that I've been producing on Udemy because it's designed to help you understand how programming works, but how computers work under the hood. So we're talking right down to circuits and switches, how the hardware works, but also how computers talk in only one language, binary and machine code, things like that nature which you don't normally learn in a particular course. So all of this though is designed to teach you the information you need as from a perspective of a programmer. So it's going to help you and make you a better programmer long term. That's the sole aim of that course. So you'll get access to that free. Next, I'm going to give you free access again to my Programmer's Guide in ebook format. Now that also has over 100 related videos which you'll get access to if I can get it out, access to as well on all aspects of your programming career. So the ebook and videos collectively answer pretty well all the important questions, certainly the majority of them relating to basically programming careers. And some of the sample questions that it actually answers is how long does it take to become a developer? Whether you need a degree to make it as a developer? What's the number one skill you need to have to succeed as a programmer? You know, are you too old to become a developer? And one other one, do you need to be good at math to succeed as a programmer? But there's a ton more, over 100 as I mentioned. I think there's 106 videos as of the date that I'm recording this video. And you'll get all of those, the answers to those questions. And look, I even take requests for future videos. So if you've got a particular question and it's not answered in the over 100 that I've already answered, send me a message and I'll actually do a video on that as well. So basically, anything you need to know about your programming career is answered in the ebook and also the related videos. What else? You still want more? Didn't I say this is all free anyway? I'm selling something that's for free anyway. But look, seriously though, I'll also give you access to my Programmer's Career Paths ebook. Now this is something that is really important because it shows you the exact courses that you need to study to achieve your career goals. So in other words, as an example, do you want to be a web developer? I'll give you the lowdown on the specific courses you need to become a web developer. Do you want to say, write cross-platform apps for mobile apps for iOS and Android? Study these courses. Again, I'll go through those particular courses. Perhaps you want to get into the Java enterprise space. You want to do that? Study these courses. So on and so forth. So I'm putting the finishing touches now to that guide, and depending when you're watching this video, it may already be available, but if not, it won't be far away. Either case, you'll be getting that access to that particular ebook for free as well. Alright, and lastly, because I know this video is dragging on a bit, the Learn Programming Academy's channel has 40 other courses here on Udemy. So I'm going to give you the information, a bit of a summary on what each of those courses are all about, but also with a big discount link to get them at the best price possible as well. So what's the catch here? How much to pay? Seriously though, I'm not really a salesman. No catch, it's 100% free. Right, so how do you access this material? Well, download the ebook that's right in this lecture that you're watching right now. Just click on the resources that you can see on screen now on this particular lecture and click on the bonus PDF, which you can see there. Open it up and it's got everything you need to access all the information that I've talked about here today. So thanks for watching, and you may find you need to be logged onto a computer to get the ebook because it may or may not show up if you're on a mobile device. So if you don't see it showing up when you're clicking on resources, or in fact resources doesn't show up, log into a computer and you should have access to that, and just click it as I said, open it up, and the information's in that PDF. But if you do get stuck, drop me a message on Udemy and I'll get back to you and make sure that you do actually get the access to that PDF today. Alright, so get to it, download the ebook right now while you remember, and thanks again for watching, and I look forward to hearing about your future success.